Hello, everybody. It's 3 o'clock. I guess it's 2 o'clock, 3 in Athens, so 2 p.m. CET. So I guess we can start so that we are on time. So I would like to welcome you to the online conference of the European Chemical Society Division of Computational and Theoretical Conference. So thank you all very much for registering. It's a real pleasure to be able to host this event even virtually. And I will have a short presentation introducing the conference and some more information. So as you all know, we unfortunately had a change of plans. The event was originally planned to take place in Thessaloniki in Greece this past September, but as you are all very well aware of, due to this unprecedented situation that we are finding ourselves in the pandemic, we had to cancel this event and instead move to a virtual shorter event, a 2-day event in the afternoon, today and tomorrow. However, we are hoping that we will be able to welcome everybody to the European Conference of Computational and Theoretical Chemistry in 2023 in September. Originally, as we had suggested today, that it takes place in Thessaloniki in Greece, but which is, you can see a picture here of Thessaloniki and its White Tower, but we're changing the venue to a place called Chalkidiki, which is very close to Thessaloniki. So this is Thessaloniki, this is Greece, and this is Thessaloniki in northern Greece, and Chalkidiki is this place here. So you can see it all. So we think that we deserve a nice venue after all that everybody has been through. So a few words about the registration for the virtual conference. The registration is free. You've received a Zoom link by email. This will be the same Zoom link for both of the days. And the Zoom link is linked to the email that you have registered, and please don't share this link. If people want to still register that have not registered, we are keeping the registration open for the entire duration of the conference. So you can still register and alert your colleagues that they can still register if they're interested in any of the follow-up sessions. For September 2023 in Thessaloniki, we will be having an in-person meeting. So the registration there will be up to with a fee, and we will be happy to inform you of the upcoming deadlines for this conference and other information by email for register to the conference. So before starting the conference, I would, of course, like to thank our sponsors for the generous sponsorship of this online event, which had quite a few of logistics due to quite a number of participants that we had registering for this online conference, as I will show in a bit. So thank you very much for the generous sponsorship to IBM Research Europe, to the Journal of Chemical Information and Modeling of the American Chemical Society, and Sanofi from Germany. Also, we would like to thank our hosts. So the European Chemical Society is hosting the Zoom webinar, and the Hungarian Chemical Society has been hosting our website. Of course, many thanks go to our organizing committee, who spent the past few months organizing this event tirelessly. So I'm Zoe Kournia from the Biomedical Research Foundation of the Academy of Athens, and I'm chairing this conference today. Hans-Peter Luthi from ETH Zurich in Switzerland is my co-chair. Benoit Champagne from the University of Namur in Belgium is also a member of the organizing committee. Merced Omal from Universitat de Barcelona in Spain. Evelina Georgieva from the Bulgarian Academy of Sciences in Bulgaria. Stefan Kast from TU Dortmund in Germany. Tanya Van Murik from the University of St. Andrews in the UK. Katarina Nikolic from the University of Belgrade in Serbia. Radu Silagi Dimitrescu from the Universitat Babes Polei in Romania, and Peter Salai from Eötvös Loránd University in Hungary. You've all received the conference schedule, so we have a very rich program. So today, after the opening remarks from me and Peter, our president of the division, we will continue with the first session of the Artificial Intelligence in Chemical Research, chaired by Benoit Champagne. And then we will proceed to the second session on materials, chaired by Tanya Van Moorik. And after that, because we received really so many interesting abstracts that we could not possibly host them for an oral short talk, we will continue with the flash presentations in artificial intelligence in chemical research, chaired by Hans-Peter Lüthi. Continue the flash presentations in materials, chaired by Mercedes Omal. And last but not least, the flash presentations in biomolecular systems. That will conclude the first day. And in between, of course, we have short breaks, which I didn't mention. So the second day on Friday, tomorrow, we will start the conference with some opening remarks on logistics, continue with the first session in biomolecular systems. We will continue with the second session on electronic structure, chaired by Evelina Georgieva. Continue then with the flash presentations in biomolecular systems, chaired by Stefan Kast, and the flash presentations chaired in electronic structure, chaired by Peter Salley. Right. Let me share now some conference statistics, because we were really happy to receive over 350 registrations, which was great. And let me share some statistics that we gathered for you. So for the attendees, we had approximately 50-50 male and female participation, and a really rich presentation of many countries that shows the global nature of computational chemistry across the globe, I guess, because we also had international participants and not only Europeans. Regarding our speakers, again, the participation in female and male is approximately equal. And also we cared for diversity, and I think we managed to succeed in having presenters, short talks, invited speakers, as well as flash presenters from as many countries as possible. And you have noticed in some of the emails, but also in the program, that during the coffee breaks, we announced some awards, some award voting. So 2 awards will be given in each session. I mean, by session, meaning the short talk sessions of artificial intelligence in chemical research, materials, biomolecular systems, and electronic structure. And 1 prize in these sessions of the short talks will be awarded by the scientific committee. 1 prize will be awarded by the audience via Zoom poll. So after each session, we will have a Zoom poll where everybody will be able to vote for their favorite presentation. So stay with us during the coffee break, because we are going to have the Zoom polls. Also, the awards will be announced at the end of each day. So today we will announce the awards for the artificial intelligence in chemical research and materials. And tomorrow we will announce the awards at the end of the day for the electronic structure and for biomolecular systems. So finally, let me share some information about the webinar. By being in this webinar, you agree to our code of conduct. You have to send your questions in the Q&A box, and each speaker will answer them at the end of his or her presentation, either in person or in writing. Please do not copy or photograph any information displayed during the webinar. If you have any technical issues, please message the administrator via the chat box. We do not tolerate harassment of conference participants in any form. And the audio or video recording of lectures, by any means, photography of slides or posters, materials, and printed or electronic quotes from papers, presentations, and discussion at a conference without explicit consent of the contributing member is prohibited. And please remember that this webinar is being recorded. For the speakers, please remain muted with your camera off when you are not presenting. Flash presenters will be promoted to panelists from the audience when it is their time to present and demoted back to attendee mode when they are finished. Please don't exceed your allocated time. The program is really tight. And if you have any technical issues, please message the administrator via the chat box. And finally, let me bring your attention to the Q&A and how we are going to ask questions. You have to use the Q&A function of the Zoom webinar and not the chat. So essentially, you have here, the chat is only for the technical help, not questions for the speaker. Using the Q&A, you can type your questions and then presenters can respond to your question in writing in this Q&A panel after their talk has finished. Or if there's time, we will also do it during the talk. And finally, we know that many people use Twitter to disseminate information for the conference, so we're really thankful about that. But we'd like to ask you to use a hashtag e-EuCo-CTC 2021 at EuChemS. And just to reiterate, don't share any content from presentations without explicit information, and contact a member of the organization committee if you have any questions, and any details can be found on our website. And with that, I would like to give the floor to the president of our division, Dr. Peter Salai, who will say just a few words about our division. And let me share the screen for that. So, Peter.
Thank you, Zoe. Can you hear me?
Yes, we can hear you very well.
Okay, good. So I welcome you in the name of the EuChemS Division of Computational and Theoretical Chemistry. I am the chair of this division, and in this position, I would like to tell you a couple of words about the organization behind this conference. You all know your national chemical societies, GDCH or Bunsengesellschaft in Germany, Società Chimica Italiana in Italy, the Hungarian Chemical Society in Hungary, and so on. So these societies have an umbrella organization, and this is the European Chemical Society, with members from 50 national chemical societies as members from 33 countries. The professional work is done in so-called professional networks. There are 19 such professional networks within EuChemS, and one of that is our division, the Division of Computational and Theoretical Chemistry. Next slide, please. Our division was founded in 1988 by Fernando Bernardi. Probably you know his name from the Boyce Bernardi correction, but of course he had much more contribution to theoretical and computational chemistry. The first name was Working Party of Computational Chemistry, and after, well, I think 15 years ago, approximately, we were promoted to a division within EuChemS. Right now, 31 national societies are represented in the division from 29 countries. Our division encourages communication and cooperation with conferences, education, and training in our field of theoretical and computational chemistry. The main event of the division is the European Conference on Computational and Theoretical Chemistry. As Zoe told you already, we planned the 13th of this 13th conference in this series for this year, but we had to postpone it by 2 years. By 2 years because in the other, so next year we will have the big conference of EuChemS, and we have to avoid that conference. So we saw that 4 years break between the previous conference in Perugia, and the conference in Greece is too much, and we decided to organize this online conference. And the number of registered, I think, proved that that there is a need for this type of meeting. So with this, I would like to thank the organizing committee, and in particular Zoe, for the tremendous work. I think when we decided to organize an online conference, we didn't know that actually that's requires so much work. With this, I wish you a good conference and enjoy the talks, and I hope that we can have some discussion, although I know that this online platform is not the best, but then in 2 years we can fix this too. So thank you very much, and enjoy the conference.
Thank you very much, Peter. And now I will give the chair to Dr. Benoit Champagne, who will chair the first session on artificial intelligence in chemical research.
So thank you, Zoe. Thank you, Peter. My name is Benoit Champagne from the University of Namur. It's a pleasure to be with you and to chair this session. And I would like to call the first speaker. This is Teodoro Leno from IBM Zurich. And the title of his talk is The Power of Language in Chemistry and More. Teodoro, are you there?
Absolutely, yes. Hi,
okay.
and
the floor is yours.
Thank you so much. Thank you so much for the introduction. And it's really a pleasure to be here with such a very interesting and diverse audience. So in the next 20-25 minutes, I wanted to give a very quick and dynamic overview to some of the activities that we have been doing in our team using language models applied to chemistry, and as I will show towards the end of the presentation, even more. So let me start by giving a little bit of context. And one of the before we start with the context, one of the most important things is that I may be addressing the topics in first person. Please always refer to the entire team that made these achievements possible. So a big thank to all of them, even before I will start. Now, let's start with the context. The context is, of course, something that, a vision that we had a couple of years ago. From a computational chemistry perspective, we were always thinking, how can we blend the technology in the space of machine learning with the work that experimental chemists have to do every day in the laboratory. And so we were thinking of building a system, building a series of data-driven models that were supporting the chemist in laboratory experimental operation, like designing the synthesis of specific molecules, but even going a step further, from the design of the synthesis, even supporting the chemist in building the entire experimental protocol that they had to follow. And of course, because we are somehow geeks, we didn't want to have people to execute this protocol, but we thought of integrating commercial automation hardware within this equation. And what you see in these slides is basically, in summary, what I will be presenting, the different technologies that I will be presenting in the next 20 minutes. So starting from the design of a molecule that has been generated either with the chemical intuition of the single individuals or with generative models, for instance. And then using data-driven approaches for designing the synthesis of that molecule, using the same data-driven approaches for compiling the experimental protocol, And then finally, monitoring the entire execution that is implemented on a commercial automation hardware remotely. So in essence, the summary of this entire work is to study, develop, and construct machine learning architecture that are capable of programming an hardware that you can purchase commercially on the market for chemical operation. So one of the key aspect of this research activity is the fact that in our team, and this is somehow our signature, we like extensively to experiment with language models applied in the context of chemistry. And I will give you an example in the next slides for different type of chemical prediction tasks that are important, of course, to the objective that I presented in the previous slides, but that are opening new scenarios where the use of machine learning can really be very helpful for the operation of chemistry in their daily research. Now, of course, whenever we talk about machine learning, we have always to start from the data. The data is actually the most important part, the part that is fueling the entire construction of these models. And I will give you more details on how we gathered, where we gathered the data, and also on the type of architecture that we are following. The most important thing is that in order to construct all these models that are usable by chemists, we have been treating chemistry as a language. And again, I will give you a very clear explanation of what that means. The remaining components that we will see towards the end of the presentation are, of course, the integration. This is a little bit more of an engineering work rather than purely research, but nonetheless very important in order to bring the technology that we computational scientists are producing, are putting together into a large user domain and make that really usable in different contexts. Now, let me start. What does it really mean, language models, and what it means that we are treating chemistry as a language? So first and foremost, we are going to focus in this presentation on organic chemistry. This was, of course, the very first part that the very first chemistry that we tried to address with language model. And somehow the decision was dictated by the availability of public data sets of chemical reaction records. So when we say that we treat chemistry as a language, what we are actually saying is that every single chemical reaction records is considered as a sentence where the individual atoms are like letters and the molecules themselves are defining words. So like for a natural language like Italian, English, German, Spanish, you have different words, and the words have to be put together following a specific grammar in order to have semantically meaningful context. The same is for chemistry. You cannot just combine molecules with each other. Quite often the combination may not necessarily lead to any specific type of chemical reaction. And so what we were actually thinking 3-4 years ago when we started this work with the pioneer of the team, Philippe Schwaller and Théophile Godin, we were actually thinking, why don't we use the same architecture that are used for learning the grammar of natural languages like English, Spanish, Italian, German, but we apply them in the context of chemistry with the objective of learning the only grammar that can be defined by chemical reaction records, which are the chemical transformation rules. So to a certain extent, we are giving up the atomistic description, the molecular description, and we are working at the level of the contextual description. So you have a large number of data sets that are describing the reactivity of the molecules, and you are trying to capture the patterns, the correlation that then get summed up in what we study on organic chemistry textbooks. And this is exactly what we have done. Now, the only issue that we had at the beginning is that, of course, you cannot use a graphical representation. That's very tricky and complicated to address with computer technologies. It's possible, but of course, it's on a different level of complexity. So we decided to rely on a linear representation. And among the many available, we decided to stick with the SMILES. So SMILES, it's a very well-known technology, especially in the chemoinformatic communities. And for people that may not be aware of those, it's a way to represent a three-dimensional structure, bidimensional structure, three-dimensional structures with a linear representation. And the overall chemical reaction was cast as a translation problem. Now we have one sentence, which is the sentence representing all the precursors, and another sentence, which is the sentence representing the products. This task, the chemical reaction task, is actually equivalent to translate one natural language, like English, into another natural language, which is Italian. So like you can train a neuronal machine translation architecture for translating between languages, we decided to train an architecture to learn the chemical transformation rules that bring the precursors into the products. As I mentioned at the beginning, one of the greatest challenges is always data sets. And for that, we relied on an amazing work that was done almost 10 years ago in 2012 by Daniel Lowy, University of Cambridge. This was one of the outcomes of his PhD thesis. And that's a data set of chemical reaction records extracted from patents. And we relied exactly on the same data set. Regarding the architecture, we have been evolving during the years. I think the very first experiments that we did with Philip and Theo were more taking advantage of sequence-to-sequence model. We have been experimenting with the attention mechanism on top of the sequence-to-sequence until in 2017, end of 2017, beginning of 2018, it was announced, actually it was disclosed, the concept of this new architecture, which is called the transformer. Compared to the sequence-to-sequence is a more effective, yet more simple architecture compared to the sequence-to-sequence with attention. And it's one of those breakthroughs that is dramatically changing the landscape of in different disciplines, chemistry, biology, languages, of course, on how to reason on data. And one of the key advantages is really the extreme use of the attention mechanism, which basically means whenever you are feeding data sets, these architectures are capable of identifying the portion of the input data that is responsible for specific type of behavior. In the context of the chemical transformation, the attention is actually pretty much focusing on the reaction centers. Now, the beauty of this approach is that compared to the many others, there are really tens of different other approaches that have been developed in the last 6-7 years for predicting organic chemistry reaction. The beauty of this approach is that it's completely agnostic in the data, which basically means we are not codifying chemical reaction rules. There is no need to pre-process the chemical data in order to make them more easily digestible by the architecture. And this is a very key point, especially when you want to systematically improve the performance of the same architecture. Also, one of the very interesting thing is that the type of prediction are incredibly accurate. I mean, when we are refining our attention to specific data sets that are somehow used between different type of architectures for assessing the accuracy, we can reach levels that are of accuracy in prediction that are above 90%. And to date, this is still one of the most accurate architecture for predicting organic chemical reactions. So that's a little bit about the context of the architecture. Now, how does this approach of treating chemistry as a language fits with the initial vision, the one of constructing a platform for supporting the chemist with digital technologies in the synthesis of new molecules? The very first element that we had to design was actually the creation of a retrosynthetic tool. Now, for people that may remember from the organic chemistry classes, talking about retrosynthesis is basically talking about the opposite of predicting the outcome of a chemical reaction. So you, if we look at the previous slides, predicting the outcome of a chemical reaction is nothing more than going from the precursors to the products. When we talk about retrosynthesis, instead, we start from the products and we try to identify all the possible precursors that independently can lead to that specific molecule. And so in the context of language models and translation tasks, this was a very low-hanging fruit, which basically means it was something that it was very easy for us to develop. The only complexity, if we can say so, was in the swapping of the order of the data when training the model. Instead of training a model that was predicting products from precursors, we were actually training an architecture with the order of the data swapped that, given a product, was actually predicting the possible precursors. So the training itself was incredibly easy, not the analysis. I think we spent several months with the team 2 years ago to try to identify proper metrics that were capable of capturing the complexity of the manifold when you are performing a retrosynthetic analysis. And the reason is that there is never one and only one single reaction that may lead to a product, but you may have many of them. And of course, I mean, the retrosynthesis itself is never a single task, because quite rarely you have that the precursors molecules are also commercially available. And so quite often this means that you have to iterate the entire prediction task, and de facto you are constructing a retrosynthetic tree. So we did that by combining traditional hypergraph exploration technologies together with single step transformer architecture. And that's basically what you can easily get. This is an example of the application of these models. The example is actually taken from a free platform that we made available to the entire chemistry community for advocating the the importance of machine learning method, but also for enabling everybody to create their own awareness on the maturity level of this technology for daily life operation. And this is an example of the synthesis of one molecule. That's the target, and this is actually how you get the entire synthesis unrolled. The second part is, of course, a little bit more complex, because the retrosynthesis is nothing more than an architectural design. You have an idea on how to implement a synthesis, but the translation of that idea into a protocol, into a real experimental setup, is a completely different story. It's a little bit, I always make this analogy, is a little bit like constructing a house. You can have an architectural plan, but that plan needs to be executed, and the execution is actually the real construction work. And so in order to support also the chemist in that operation, we decided to use the same language models also for different tasks. And one of these tasks was actually the prediction of the entire action. And we did that. Again, we had to face the major challenge that we did not have available a data set of experimental procedures. So again, we relied on information from patents. And the very first thing that we did, actually driven by Alain, another member of the team, we constructed an architecture that is capable of condensing, processing paragraph text describing experimental procedure into a list of operation. And this was crucial to build a database of experimental procedure, all described by precise steps, in order to build another model that is actually connecting every single chemical reaction, so precursors that go into products, with the corresponding action. Now, what this architecture is actually doing, in short, is trying to capture all the signals related to specific functional groups, specific chemical transformation, and connect these elements that are descriptor elements with the individual action. So what we demonstrated is actually that even in a data set of relatively small, of roughly 700,000 experimental procedure extracted from patents, there is sufficient information that can be learned by these models in order to generate experimental protocols. So the use of the language model doesn't really finish here. There are a couple of other things that I wanted quickly to mention, still in the chemical context. One is actually using the training of the language model for curating data sets. And there is a very, very important analogy. So when you learn a language, you are learning a statistically representative grammar. So when you have sentences that are offset compared to the average grammar compared in your data sets, your architecture will actually be, will have more difficulties in learning and remembering the specific grammar of each individual sentence. And the same is applicable in the chemical context. When you have chemical reaction records that are containing wrong chemistry, a chemistry that doesn't really match with the chemical rules described by a larger data set, your architecture will be really having a hard time in learning and remembering that information. So Alessandra actually had the idea of exploiting this failure, which is considered one of the catastrophic failure in the space of machine learning for actually generating a protocol to clean up the data. And another important aspect of using language models is the one that Philip put together at the beginning of this year. And this is, in my opinion, one of the most elegant outcomes in the space of machine learning, because what Philip actually demonstrated is that you are, after you trained a model, a language model with chemical reaction data in the forward prediction, you can process the numerical weights of your architectures and extract from these weights an information which is macroscopically chemically relevant. It's something that we call atom mapping. So we demonstrated that actually the reason why the language models are learning so well is because without supervision, in a completely unsupervised way, the models are capable of learning the redistribution of the atoms between the precursors and the products. So this is really a very important breakthrough because it's somehow providing an interpretation to the same models and why some of the prediction may be wrong. The third part, I will continue with the platform. The third part is actually the integration of the technology. I will go very quickly, and I see Benoit on. I only need really 2 minutes. So it's the integration of the technology. Of course, we made everything usable through the cloud. I will not spend too much time on that. The only thing that I wanted to say is that from a commercial, from an hardware perspective, even if the community here is a computational community, we had lots of fun actually in interacting also with more the experimental parts. And so we relied on commercial systems that are that have a certain number of batch reactors. We coupled by doing quite a lot of engineering work both liquid chromatography mass spectrometer for monitoring the reactions, as well as we are in the process of completing the coupling a benchtop NMR. And this is really for monitoring the reaction. And this is a short recording, 20 seconds, that are really demonstrating what you can see from the sofa of your apartment while you are running remotely chemical reaction. So once you have all the chemicals loaded in the system, you can enjoy watching the chemistry from kilometers far from the location where the real chemistry is actually happening. I will be very short, really only 30 seconds, to mention something else. The fact that the entire concept is data agnostic, it also means that you can customize the type of chemistry. And this is something that we did by switching from traditional chemical reaction data to enzymatic data. So suddenly what you can do, you can build exactly machine learning models that are capable of supporting the chemist in embedding enzymatic reaction during their chemical reaction planning. And one of the biggest outcome that we have out of this work is that if you represent your enzyme in the chemical reaction as a sequence of amino acids, you can use the same and exact atom mapping technologies to actually do enzymatic design. So that's the reason why in the title I had from chemistry and more. The reality is that language models are really an incredibly powerful technology for rationalizing chemical data, but also for introducing design aspects into fields like enzyme design. I will stop here and leave maybe a couple of minutes. Sorry about the length.
Thank you very much, Teodoro. Wonderful result, beautiful results. We have time for questions, of course, and some of the questions will be asked through the question and response, I would say, panel. Anyway, I take advantage of being the chair to ask you a question. For all these organic chemistry reactions, it is common that you might have different temperature, different concentration, different solvents, and so on and so forth. Could you deal with this? And could your, I would say, your engine choose what would be the best experimental condition in order to have the, I would say, the highest yield, for instance?
Yeah, no, that's a very important question. So for everything which is chemically related, chemical species, yes. If you can represent into the chemical reaction, you can definitely consider that solvent, that catalyst, like an additional elements, like a new, an additional dimension in your multidimensional space somehow. Okay. When we talk about instead the physical properties like temperature or anything else, pressure or things like that, the way we deal with that is actually through the second model, the model that is learning, correlating a chemical reaction with an experimental protocol. So we learn the physical parameters, whether a reaction is exothermic and requires cooling or is endothermic and requires heating. We learn at the level of the experimental protocol. So it took us a little bit of time, but it's the division now is pretty much quite well defined. And regarding the optimization, to a certain extent, when you do a prediction, you are actually predicting the optimal based on your training data set. Now, that's of course far from being the global optimum, because you are in a space where the chemistry that you are in a universe where the chemistry of the universe is described by your data. But of course, you don't know if there are other type of chemistry that were not in your original training data. But at the level of the prediction, of course, you can consider the prediction like optimal ones.
Thank you. Do you see the question from Hans-Peter? Theo, it's a related question. Is it conceivable that you will find new chemical reactions?
Schwaller rearrangement, it's a little bit probably extreme, but this type of...
Can you repeat the question for the audience?
Oh, yeah, sure, absolutely. The question is it conceivable that you'll find new chemical reactions such as X and Y rearrangement? So that's a very interesting one. The technology, this type of machine learning, and I want to make it clear to debunk any fancy idea. At the end is nothing more than an interpolation, a nonlinear interpolation in a space of chemical reaction. So it may happen that by chance you are interpolating through an area where there are no data sets, and you can say, well, I made a discovery. But the reality is that quite often this technology is, in my opinion, the way where it can demonstrate the greatest value is in providing unbiased recommendation for chemical reaction. This is something that we have seen a lot. When you have people that are specializing in specific type of chemistry, they always see those chemistry everywhere. And instead, this type of approaches based on data are pretty much unbiased. So definitely you may be lucky and find a new type of rearrangement, but I would say that most of the value is actually in providing recommendation on a large scale of chemical reactions.
I propose to take a second question from the panel. Any chance of extending to organometallic chemistry?
Yes, that's of course something that we are currently working on. So one of the major, first of all, we are already covering a big part of organometallic catalysis, because if we look at the distribution of the data extracted from patents, I would say that the vast majority, these are all organometallic catalysis, carbon-carbon coupling, and so on. However, there is a problem. I'm not saying that the approach is completely neat and finished. And the reason is that the way we are using for representing molecules, SMILES, is actually relatively ambiguous in the context of metallic center with multi-coordination sites. That's something that the SMILES don't handle at all. So what we are trying to pursue is actually cleaning up the data, having a better representation for the organocatalysis, and improving the model in the direction. And there is a follow-up, if I can, but for synthesizing organometallic, you need a new language. The reality is exactly what I said. The SMILES are not really super effective for representing organometallic. The other thing that we will need is that quite often the synthesis of organometallic is completely ignored in chemical reaction records. And so this means for specifying the synthesis of organometallic, we will need not only a new way and a better way of representing organometallic, and for instance, there are selfies that may be better than SMILES, but also the data set will have to be more broad and more extensive. And the same is applicable for inorganic chemistry without any difference.
Thank you very much, Teodoro. I am much sorry, but I'm sure we could continue asking you questions, but it's time to go to the next speaker. So congratulations again. And on next speaker is Laetitia. And it's difficult for me to pronounce your name, so I would say that you are from Barcelona, and that the title of your presentation is Exploring Molecular Diversity in Drug Discovery. There is plenty of room, not only at the bottom, but also at Marcus. Okay, the floor is yours, Laetitia.
Hi. So thank you very much. Good afternoon. We're going to change a bit the topic. I would like to thank, first of all, the organizing committee of the EuChemS conference that has offered me the opportunity to share our work about chemical space exploration in drug discovery. So to start this short talk, I would like to do a brief review on the well-known chart of the drug discovery process, focusing on the exploratory research. Commonly, once stated the target of interest, the hit-to-lead process takes place, involving virtual screening studies such as ligand or structure drug design. And in pharma, high-throughput screening practices are performed using a sample of all the compounds present in their chemical databases. Still, these first approaches finish in the lead optimization steps with the synthesis of a few candidates that might have involved the use of many resources, time, and high cost, inconvenience that could be reduced by using the so-called rational analysis. In fact, when a final drug or compound is patented, a Marcus structure is stated in the claims part, defending that the combinatorial library derived from it might hide also active compounds. However, when taking a look closer to this chemical space derived from the combinatorial library, such as this grid, we normally find that compounds studied in the lead optimization process are placed near the original hit area. This is the result of the traditional free Wilson approach, which takes in consideration only the structural changes of one derivatization point or two, but not the overall synergistic effect. Hence, as we define that there's still space to be explored in these combinatorial libraries, we do suggest a new methodology based on a rational selection approach, which involves the synthesis of the same number of significant candidates in order to better describe the chemical space of each combinatorial library. This was first evidenced by our group with a combinatorial library derived from 180 HCPT analogs known until that date, which represented only 9% of the space coverage of the overall database of 125,000 compounds. In fact, they synthesized only 24 analogs, and with this short sample, they could represent the 90% of the overall database. But what does space coverage mean? Let's imagine a chemical library. This can be obtained through the compound's features. We can use fingerprints, molecular descriptors, etc. And then we can reduce it, the database dimensionality by principal component analysis, and divide this space by clustering or partitioning methodologies. In this case, the space is described by 16 bins, 14 of them occupied. By the traditional methodology, normally the explored space is the hit surroundings, as we have already said, which might hide new leads, such as this, painted in red. This would represent the exploration of only 4 out of the occupied 14 bins. Hence, the 28.6% of the space is covered. However, through a rational selection, we could optimally represent the 85.7% of the chemical space by using the same number of samples and find even better candidates. To sum up, so the space coverage is a value which is calculated as the percentage of occupied clusters among the overall number of clusters. And moreover, the population coverage represents the population represented by the occupied bins among the size of the database. So once described these values of discussion, to follow up my speech, our actual work departs shaping the drug space or chemical space with drug-like properties known until date. We suggested using Campbell database of bioactive compounds, which already describes 1.9 million of compounds. And we first placed and discussed the sparse distribution on the latest small molecules approved by the FDA regulatory system. Due to the high density in the space, it was first evidenced that although the space coverage was really precarious, there was a good representation of the overall population, but still space to be explored, as even a random sampling would better represent this drug space. If we look closer to the FDA dataset of 359 molecules approved, we can perceive a trend in the latest 12 years that focus the research mainly in neoplasms, infectious or parasitic diseases, and metabolic diseases. We have selected 6 drugs of study attending to a variability of category, disease, year of acceptance, developer, and size of the derived combinatorial library to avoid biased information. The Marcus structures found in their patents are shown in the slide. And when placing them in the already introduced drug space, a highly focused areas of each family can be perceived. However, is this the real space explored until date? The first step of our study consists in assembling the combinatorial libraries with their corresponding database built up, in our case, by 207 1D and 2D molecular descriptors, which were calculated by most software and was further reduced to their principal component to shape the chemical space of each drug's analogs. Later, the square root of the library size is taken as a reference value in clustering to optimally represent the large data sets. So we have applied different clustering methodologies, hierarchical clustering with 6 different linkage methods, also k-means, k-mediates, 2 partitioning methodologies, the well-known binning, and also a new developed tool, which we have called optimum variance binning. After reviewing the population distribution in each cluster, we perceived that there are some clusterings that trend to present a huge number of singletons and hyperpopulated clusters. As we aim to obtain and divide the space in homogeneous clusters, we discarded those presenting these hyperpopulated or singletons, leading to 3 agglomerative methodologies: k-means, k-mediates, and the n-dimensional partitioning methodology developed in the group. Afterward, we searched in PubChem the coincident molecules with the developed databases. This represents the bibliographical data known until date, which from now on will be represented as BIP. And moreover, we developed with this data the bibliographical combinatorial library, or SIG. As you see in this slide, this would represent the real markers known until date, as it is built up by the fragment combination of the bibliographical data. As logical, this database presents a smaller size than the original one, but they do not imply the significant coverage of the overall database. In fact, it can be seen in the case of the EuChemS database that neither the bibliographical data shown in blue nor the combination of its fragments, colored in green, would optimally represent the overall chemical database or the overall chemical space. So when contrasting this data with the square root of the original size, we perceived that in terms of quantification, the number of molecules known until date, having then been tested or not against the same receptor, is not statistically significant for all cases, except for teriflunomide, which has been deeply studied. Moreover, if we do calculate the space and population coverage of this bibliographical data and contrast it with the same number of random molecules, we discover that for all cases, the space known until date is lesser than the one that would be represented by a cherry-picking approach. Here are shown the coverage values obtained from a hierarchical clustering with average linkage, but we obtained the similar results for all the other 5 clustering and partitioning cases. So the first conclusion is that, as expected, for new different libraries of study, a random selection of big compounds would represent more significantly the space described by the drug's patents rather than the molecules already studied. Hence, for all cases, there is still space to be explored. As an alternative, we suggest studying a rational selection of samples which can achieve the optimal coverage of the 100% of the chemical space. How we make it? Let's take a look at the EuChemS case of study. A rational analysis should optimally pick a tractable number of molecules to be synthesized in the laboratory. So in our case, and with our time and resources, we decided to generate 10 clusters through hierarchical agglomerative clustering with an average linkage. However, playing with these data sets computationally does not imply that these molecules are synthetically fusible or drug-like molecules. Hence, curation is needed. We pass from 25,000 molecules to a final amount of 2,500, taking into account the restriction of only one or non-Lipinski rules, filtering the database structures by optimizing the synthetic group from 15 to 9 steps, and checking the commercial availability of the reagents. By these terms, we shape the real accessible chemical space by tafenoquine analogs, which only involved 8 clusters. Among these, we rationally picked the nearest to centroid compound as a representation of each cluster, and we finally were able to synthesize 7 of them. It can be seen on the plot in orange, the molecules found in literature, and in green, the ones that have been synthesized representing the explored and the unexplored regions of the chemical space. Hence, we were able to increase the space and population representation on the chemical space with only 7 compounds. The space coverage was improved by 20% and the population coverage by 32% in contrast with the data known until date. These molecules are being tested by our collaborators in JSK, and we will soon have results of their biological activity. With these results, we can even find hidden active unknown reservoirs, or at least we will have this family of analogs represented for further repurposing studies. So this would be the results of our study. We sustain that the Marcus structure does not imply the proven synthesis of a significant data set of analogs. We suggest a new methodology which may better describe the chemical space of each database to explore new potential hits, or at least represent the library for further repurposing issues. And last but not least, this new methodology, if implemented previously in the exploratory research process, would optimize the process in terms of time, resources, and costs. And at the light of the results, we suggest that implementing these rational selections along with the traditional lead optimization steps, as they can be complementary, so implementing this, both of them in the first steps of any research project would be most advantageous for an optimal space exploration. So thanks everyone for attending to this talk, and a special thanks to my colleagues of the Molecular Design Lab and GSK Global Health Pharma Research Unit.
Thank you very much, Laetitia.
Thank you.
It's time for questions.
Yeah,
Now
go for it.
I look at the panel. Whether there are questions. I apologize, but this is not exactly my field, and I cannot answer you, I would say, a stupid question just to take a few minutes. So I am relying on the 175 people listening to your presentation.
Yeah.
I do not see any question for the moment. So anyway, I am sure that people could ask you a question later on. So
Okay.
I think that it's better to continue, except I see something. No? Yes, I see something coming.
It only says that it was clear,
no,
and thanks.
was very clear.
So no
Thanks.
question at all.
Okay.
Okay.
So thanks again,
I'll be checking the chat
Laetitia.
just in case there's any question, and I will answer. And if anybody has any question, you can write me directly an email, and I can also answer later after the conference. Thank you very much.
In fact, I think people can still write in the Q&A. You can write in the Q&A even after a speaker has finished their talk, because the speaker can respond to your question even after they have finished in writing. So please send along the questions as they come in.
Okay, thank you.
So thanks again. I propose to switch now to the next speaker, coming from the Netherlands. This is Theodorus Gomans. We also switch from life science to material science with your presentation, Fedor. You are going to speak about accelerated materials innovation through machine learning assisted atomistic modeling. So, are you ready?
I think so. Can you hear me clearly?
No, it's a bit low. Okay, can you speak louder?
Yeah, I will try. Is this better?
I think it's better.
Okay, let me
Zoe,
see. Then...
is it also better for you?
Yes.
Okay, so the floor is yours.
Okay. Well, thank you, Benoit, for the introduction. And it's a pleasure to be here virtually. And well, thank you again to the organizers. It's nice that at least there's a virtual platform, and hope to see you all live in 2 years from now in Greece. My name is Fedor Gomans. I'm Chief Customer Officer with Software for Chemistry and Materials. And I would like to talk to you about how we can develop new materials more quickly. Every year we dump 8 million tons of plastics into the ocean. Every year also we need more energy. So in 3 decades, the world's energy consumption will have increased with at least 50%. And oil and gas is going to run out in 4 decades. Obviously, we need new materials and we need new processes to address these societal challenges. We need a more sustainable circular economy. We need better ways to generate energy and to store it. The problem is that the classical materials discovery process is simply too slow. It takes around 15 years to develop a new material solution for a new market. More than 80% of the research development programs for new materials discovery simply will fail. And if they do succeed, usually there's only an incremental improvement. So you may marginally improve, for instance, the efficiency of a solar cell material. The underlying problem for this experimental Edisonian approach is that because the discovery process itself is so slow, only very new materials are being made for testing in the lab, again leading to having not many materials available for testing to begin with. So this is a vicious circle, which to a certain extent you can of course break by using simulations. Now, ultimately, the properties of every material are determined by what's happening at the atomistic scale, at the electronic scale, so we could model each and every one of these materials in the computer and try to find the right candidates to make and finally test in the lab. So this computer-aided virtual discovery works. And here's a couple of examples for organic molecules that have been done in the last couple of years, where you start with a sequentially stricter and stricter set of criteria to finally emerge with the relevant candidates that you're ready for testing in the lab. Now let's have a look at a case study for organic light-emitting diodes. We can perhaps improve upon this computer-aided virtual discovery. In organic light-emitting diode, we have electrons and holes meeting each other in the middle, in the emitter layer, where the excitons can fluoresce or phosphoresce, depending on whether they're in the singlet or the triplet state, emitting a photon and giving rise to the nice screens that we are looking at the moment. In such an OLED device, you'd also need to optimize other properties, not only the luminescence and its efficiency, but also you need to make sure that the transport is quick enough and that there are no processes that destroy your molecules. So to optimize any material in this stack, but also the entire device stack, you need to optimize a lot of different properties simultaneously. So you need a multi-objective optimization, which you can achieve by doing virtual screening, combining that with device level modeling, combining it with machine learning techniques and materials informatics. So first, let's have a look at the properties which we can calculate by using quantum chemistry. So for the second generation of OLED emitters, we're looking at transition metal complexes, which typically have a probability to phosphoresce from the triplet state to the singlet ground state through spin orbit coupling. So if you can calculate spin orbit coupling and in combination with time-dependent density functional theory, you can calculate the radiation point, so the color point of the material, as well as its lifetime. And obviously, for it to be efficient, we want to have it emit as quickly as possible. So we can show that this works. We can effectively screen many different molecules, but still not millions, because it's quite an expensive calculation to run. Also important for these nice screens is that we have a very narrow emission. So it's important also to calculate the vibrational coupling between the two states from which the OLED emitter emits. And again, in red here, you can see the calculated vibronic spectrum comparing very well to the black experimentally measured spectrum, giving some confidence in that you can calculate these properties for many types of materials. Again, it in itself being quite slow for each molecule, so ideally we would speed that up. The latest generation of OLED emitters are using a different principle. They're called thermally activated delayed fluorescent emitters, and they can harvest the triplet excitons, which will not effectively phosphoresce because there's relatively low spin orbit coupling, but they can get back into the singlet excited state because there's a very small energy gap between those two states, and you need also a little bit of spin orbit coupling. And from the singlet state, then the molecule can fluoresce, leading to a theoretical efficiency of 100% for these TADF emitters. Again, we can calculate singlet triplet gap and spin orbit coupling as a proxy for calculating how efficient these molecules would be in OLED materials. Mobility, one can also calculate. Typically, the accuracy for these type of calculations are okay. They're within 30% of measured mobility. So here's an example of showing that for a PAH molecule, where in blue here you see the theoretical mobility, and the dots there represent different experiments. So you get the anisotropicity right of the charge mobility, and also within 30% the magnitude of the conductance. So you can use that again, and this has been used commercially also for patents, for instance. You can screen many different types of materials for the desired mobility properties in OLED stacks. So if we put all of that together and we want to optimize, let's say, a new TADF molecule, we can do that, and this has been proven. Again, this was a study from Samsung with a lot of academic collaborators, where they took a library of 1.6 million molecules. They built a deep learning, simplistic machine learning prediction model by training it on 40,000 time-dependent density functional theory calculations that allow them to, let's say, triage the library down to 400,000 molecules, for which they still calculated the photoluminescence properties using TD-DFT. Eventually, they came up with 20 candidates, which the experimentalists were confident that they could synthesize. They made them in the lab, and 3 were experimentally verified to have the desired quantum efficiency as well as the emission wavelength. Total computational costs, I'm not talking about labor here, because building the model costs a lot of time as well. Just simply the calculation cost, it was $1 million. So let's say 900,000 euros. So how can we improve upon doing these type of virtual screenings? So it's obvious that ultimately we need to make the materials, but this is expensive. It's obvious that we can do quantum chemistry, which is less expensive and a little bit less accuracy. And we can also do machine learning, which once we have a model is really cheap, and we can screen many, many different types of materials. So the idea is that if you combine all of these techniques and you include active learning to also search parts of space that you haven't sufficiently sampled before, you can, with this multi-level screening, you can reach, let's say, millions of compounds that you can screen within a couple of weeks by using decent size compute centers or running it on the cloud with decent accuracy. The more experimental results you have, the more confidence you have in building your machine learning model and actively learning that to improve. So as an example of that, this was a library of 7 million purchasable molecules that were tested for electrochromic behaviors for smart windows materials. By using active learning techniques, only 15,000 molecules were needed to be calculated at the TD-DFT level, resulting finally in 10 verified hits that had the desirable absorption and electrochemical potential to be used in smart windows. So what we want to do is to take that approach further and apply it to different sets of materials. And we are combining here our expertise as a small computational chemistry software company who've been developing different sets of atomistic modeling based in Amsterdam, starting with density functional theory, also approximate electronic structure methods, and more recently, reactive force fields and machine learned potentials, combining that with the expertise of an American-based company called Robotics, who are experts in advanced machine learning techniques as well as robotics, which you can then couple to making new compounds, feeding that back into your multi-level screening approach. The software platform that we have in mind, we will call it Materials Navigator, that allow you to find your way in this complex chemical space by combining all these different techniques. On the software side of things, you can build your own workflow. So depending on the type of properties that you want to optimize, you can input a workflow that will give you the desired properties and put that into the active learning model to most efficiently sample the chemical space for that. Organic electronics is where we have most experience with in both companies. So that is going to be the first set of software products that we will be able to offer to people to test. But on the roadmap, we also have good ideas on the way to help people optimize materials and electrolytes. So both the electrodes as well as the electrolytes for battery applications. That will also include polymers, but for polymers, we also have other ideas in mind related to their optoelectronic properties. Semiconductor materials are something that we want to look into as well, and also classical chemical catalysis. So what we're interested in is learning the kind of materials people are interested in optimizing and seeing if we can help them accelerate the virtual discovery by combining classical atomistic modeling, if you will, with active learning techniques. So let me know if you're interested in learning more and if you want to find out if we can tackle some material challenges together. Thank you for your attention.
Thank you very much, Fedor. Very nice presentation. I'm looking to see whether there are questions in the panel. So if not, I have a question for you. It seems that you go towards, I would say, more and more complex quantum chemistry calculations in, I would say, in your research. And I would like to relate a bit what you presented to one of the points that was mentioned by the first speaker, by Teodoro. He spoke about curating the data set. So when you need to calculate such, I would say, high-level properties, you spoke about spin-orbit coupling, you have the vibronic structures and all these things. So sometimes you might use a method, sometimes this is TDDFT, which is not sufficient in order to catch, I would say, the physics or the physicochemistry of your system. So what is your, I would say, advice when your, I would say, quantum chemistry calculations are touching the limits of its prediction and of its accuracy?
Yeah, that's a very relevant, good question. So yeah, obviously DFT is only as good as it gets, and sometimes is better than in other times, depending on how well you know the deviation of where you want to be. So let's say you can still predict the trends. You can use transfer learning, for instance, to either improve your model or just simply scale whatever you get out of your calculations. But that only works, obviously, if you have an error that predicts itself reasonably well, or something that can be actively corrected on the fly. But it's something we're working on.
Okay, thank you. I have seen two questions in the panel. The first one is by Carlos Bo. Or do you manage to convince experimentalists to provide wrong results? Is it the correct question, Carlos? Okay.
Well, so ultimately, right? So if you want to make a new electrolyte material, you need to make it, right? And so in order for it to test whether it works, we need to provide at least some guidance as to what are the relevant materials to test. And in a couple of cases that I've shown, I think on the fourth slide, by doing like this accelerated virtual screening, you can come up with, let's say, a couple of dozen of candidate materials which you can make, and ideally you would have a robot make that, so you don't need to convince the experimentalist, but you have a robot make it. You could test it and then feed it back into the loop. On some of the applications that Cobotics have been working on, you have a success rate between 10 and 66%. So all in all, that's not bad. It's better than by just doing it with blindly guessing new materials and testing them. That's way too expensive experimentally.
Okay, there is a question from Anna. Were these TDDFT large-scale screenings all performed with ADF or also turbomole? The pictures of molecules you showed also look like you considered maybe already periodic systems, or were these studies you showed focusing only on molecular systems?
So I've shown a couple of samples where we did a few calculations, right? So those were all performed with ADF, and then this 400,000 calculations, I think they were done with EuChemS, but I'm not sure. They were not done with ADF, at least.
There is a question from, okay, there was also a point about the periodic systems or molecular systems.
Yeah, so what was the question again on periodic or molecular?
Also look like you considered maybe already periodic systems, or were the studies you showed focusing only on molecular systems?
So these two examples that I've shown were molecular systems, but we can treat periodic systems as well.
I guess that the question was connected with the batteries, the pictures that you showed at that place. Okay.
Yeah, it's of course a little bit more difficult to generate, let's say, a library of structures that you want to do high throughput screening on or active learning on, but it's definitely possible to do that.
You will have a lot of questions to answer in the panel, but I take the next one from José Manuel. Have you considered to include more sophisticated models than TD-DFT into the workflow, let's say CASPT2?
Yeah, so yes, not CASPT2, but that's definitely something that we could do. It's not something we could do in ADF, but you can hook up any other code as well. In the context of organic electronics, we're including GW and eventually BSc as well.
And a question also from Philippe Baranek. So hello, Philippe. How to find the good artificial intelligence approach to treat a problem to treat a problem for all the speakers because the topics are more or less near?
I'm sorry, but I don't know how to answer that question. So I'll have to relay that question to Alexis or Google. So maybe you can ask them.
Carlos Bo is so. It's difficult for me to read because some of the questions are going away. So what is the next question? I saw from Anna. So does ADF feature excited state optimizations using spin orbit coupling in a relativistic setup? And how are you treating spin orbit coupling for periodic systems?
Okay, so the first part, yes, but these are tremendously expensive calculations. So you can do spin orbit coupling and TD-DFT gradients, but as soon as you run that on a large system, that becomes quite expensive. There have been some studies, for instance, looking at internal conversion processes with Shark, where you take out of ADF just the spin orbit coupling. But in principle, you can run excited state optimizations using spin orbit coupling. In our periodic DFT code band, we do self-consistent spin orbit coupling. So yeah, I hope that answers the question. Again, that is quite expensive. In ADF, you can do both perturbative spin orbit coupling or fully self-consistent spin orbit coupling.
Thank you very much. So I propose you to go and continue to look in the panel.
Will do. I'll answer them via the keyboard, so then you can move on to the next speaker.
Yeah. Thanks again, Fedor.
Well, thank you.
Bye-bye.
Bye.
Okay, so Zoe, I think that we are doing well. We are almost on time.
Perfect. Thank you, Benoit. You're fantastic.
Thank you. The next speaker is Alex. Alex from Athens. And are you there, Alex? Oh, yes, I see.
Hello, hello.
Hello, hello, hello. And the title of your talk is Predicting Protein Membrane Interfaces of Peripheral Membrane Proteins Using Ensemble Machine Learning. The floor is yours. Or the screen.
Thank you very much. Hopefully you can see my screen. My name is Alexios Hatzioulas.
Yes, maybe you should speak a little bit louder.
Okay. My name is Alexios Hatzioulas, and I will present a novel web server that predicts protein membrane interfaces of peripheral membrane proteins using machine learning. So first of all, why is the protein membrane interface important? Well, we know that 50% of pharmacological targets are membrane-associated proteins. Membrane proteins can be divided in peripheral membrane proteins, where a protein sits on the top of the membrane, and in transmembrane proteins. Peripheral membrane proteins are important in many cellular processes, such as transporting substances within or outside of the cell, activate other proteins, and many others. Peripheral membrane protein mutations and abnormal protein membrane attachment is involved in deregulated cellular pathways and in disease. And dragging the membrane binding interfaces has been neglected so far. This gave us the motivation to investigate the membrane binding interactions and to create a tool that predicts the membrane binding regions using machine learning. Dragging the peripheral membrane proteins in the protein-membrane interfaces can enhance drug selectivity and modulatory control of proteins. So because the protein-membrane binding is important in disease, we intend to reconsider the accessibility of membrane-protein interfaces by drug-like molecules, which has been so far unexplored, possibly due to the complexity of the interface and the limited number of structural studies of protein membrane binding. But the membrane binding interfaces are usually unknown, so we devised a machine learning algorithm that predicts them. In order to apply machine learning, first of all, we need a dataset. As a dataset, we use peripheral membrane proteins with known 3D structure and experimentally known membrane-penetrating residues. So now we have a binary classification problem, which is to distinguish the membrane-penetrating residues from the non-penetrating residues. Then, in order for our algorithm to predict accurately the membrane-binding regions, we need features for the amino acids that can separate these two classes. Then we train supervised machine learning algorithms and evaluate them in an independent test set. We retrieve the protein 3D structures from the protein data bank, and then we pre-process them using HTMD. We continued with feature extraction, where we generated residue-specific features, for example, the solvent-accessible solvate area, the conservation score, the hydrophobicity scales, and others. And we also applied the ProtiCal tool, which calculates several thousand thermodynamic, topographic, and property-based features for amino acids. Then we removed the redundant and correlated features, having in the end 560 features. So our dataset consists of 54 peripheral membrane proteins with experimentally known membrane-penetrating residues retrieved from extensive literature search, where we assign class labels and split in training and test sets. Because the penetrating residues are way less than the non-penetrating, we face the imbalanced classes problem. When this problem occurs, the machine learning algorithms tend to underpredict the minority class, so we have to create balanced datasets. To solve this issue, we utilized 3 techniques. The first one is to use weights on the samples where more emphasis is given by the classifiers in the minority class. The second is to oversample the minority class using algorithms that generate synthetic samples. And finally, the third technique is to undersample the majority class with sample selection methods. In the end, we got 6 datasets, the initial dataset using weights, 2 different datasets generated by 2 different oversampling techniques, 2 datasets generated by 2 different undersampling techniques, and 1 dataset generated from a combination of an over and undersampling technique. Except from the features and the dataset, the success of machine learning depends also on the machine learning algorithm. We tried many different algorithms because every classifier works in a different manner, having the potential to predict correctly samples that others cannot. But the problem is that you cannot know a priori which classifier is the best for your problem. Also, every classifier has parameters that control the behavior of the training algorithm and have a significant impact on the performance of the model. Depending on the parameters of the model may underfit the data, overfit the data, or be good and robust, which is what we want. So in order to tune the classifier parameters, we have to train thousands of models with different parameter combinations, where in the end, we will keep the parameters of the model with the best performance. In total, we trained 21 classifiers, 19 from the Python library scikit-learn, the XGBoost and the LightGBM, using the 5-fold cross-validation. So for a specific classifier and parameter combination, we train 5 times, each time with a different fold as a validation set, and in the end, we take the average of the 5 prediction scores. This way, we avoid overtraining. So for each classifier, we trained thousands of models with different parameter combinations. Then we kept the best model for each classifier that has the best predictive score with respect to predicting penetrating or non-penetrating amino acids according to the 5-fold cross-validation. Subsequently, the resulting predictions of the aforementioned classifiers were imputed as input to meta-classifiers. We facilitated the voting classifier and the stacking classifier, and this was done for all 6 datasets. In both meta-classifiers, we tried all possible combinations of the first-level classifier predictions in order to find the best classifier combination. That is, we took every 2 classifier combinations, every 3 classifier, and so on. The meta-classifiers were tested using an independent test set in order to avoid overtraining. The best model was a voting classifier of 5 out of the 21 first-level classifiers with the initial dataset using weights, achieving a macro F1 score of 0.93 and a Matthews correlation coefficient score of 0.87 in classifying penetrating from non-penetrating amino acids. Here, we can see the predictions of the best voting meta-classifier in an independent dataset with known membrane-penetrating regions shown with red circles. We can see that the predictions are in these regions or adjacent and in line with them, except for a few false positives predictions that in most of the cases are important for protein-protein interactions. This work is expected to be published in briefings in bioinformatics journals soon. Furthermore, to assist in tracking the protein-membrane interactions, we automatically search for binding sites near the predicted membrane-penetrating residues. We do that in protein conformational ensembles to take into account the dynamic nature of proteins. In case a conformational ensemble is not available by the user, either from molecular dynamics or NMR, we also incorporated the distance geometry-based method XPROS that generates conformational ensembles. In each conformer, we utilized the novel machine learning-based pocket detection method P2Rank. Moreover, the PyMol scripts generated by P2Rank are automatically modified to only display the predicted membrane-penetrating residues and the nearby binding sites. For example, in the figure, we can see a prothrombin conformer with the predicted membrane-penetrating residues colored with purple, along with the nearby predicted binding sites. All of them are designed as a free and without login requirement web server called Dream, which can be accessed by dream.nifos.eu. Here we can see the workflow of Dream and what it can achieve. Now we will see a video tutorial for using the Dream web server. The user first chooses to use the option of searching for binding sites near the predicted membrane-penetrating residues. In case that the user does not want to search for binding sites, the user may input the BDB ID at the chains and hit the upload button. If the chain field is empty, the whole structure will be used to predict the membrane-penetrating residues. The user may also choose as an alternative to upload his or her own structure by hitting the Upload BDB file. In case that the user wants to search for binding sites near the predicted membrane-penetrating residues, he or she has to check the appropriate box, and once checked, new options will appear. The first option is to use the BDB ID of an NMR structure, choose the chains, and hit the Upload button. The user may also choose as an alternative to upload his or her own protein conformational ensemble by hitting the Upload PDB file button. In case that an NMR structure and the protein conformational ensemble are not available, the user may choose to create a protein conformational ensemble using XPROS. The user has to input the PDB ID, the change, the number of additional conformations to generate, and hit the Upload button. Here, as an example, we will use the P10 protein without searching for binding sites. We add the PDB ID and the chain, and we hit Upload. Hitting Upload will start the feature extraction and then the prediction. In approximately 3 minutes, the job will finish for the size of this protein. The page automatically reloads every 10 seconds. In case that the user does not want to wait, or if the job is queued, you can copy the URL and bookmark it for later use. 2 jobs are allowed to run simultaneously, and if 2 jobs are already running, the next jobs will be queued. So let's wait a few seconds for the results. The results are displayed in the top, showing if any residues and which are predicted to penetrate the membrane. The membrane penetrating residues are also displayed with JS-mol. The protein is represented in a secondary structure and the membrane penetrating residues in CPK. The user can also download the results in a CSV file, or in a case the user chose to predict binding sites in conformational ensembles, in a zip file containing various results, such as the Biomolecular visualization. There is also a return button if the user wants to run another prediction. The URL with the results stays active for approximately 2 days, and afterwards the results are automatically deleted from the server. To conclude, a dataset with experimentally known membrane-penetrating residues was assembled from extensive literature research. A set of features describing the amino acid properties has been produced, and machine learning classifiers have been trained and tested. Our predictions are accurate and confirm experimental results. Additionally, cavities are found near the predicted membrane-binding interfaces in conformational ensembles, and the web server was designed providing users a way to use the tool without installation or accounts. In the future, we plan to design a new method that detects allosteric connection between these predicted binding cavities and the orthosteric site. In the end, I would like to thank my supervisor, Dr. Zoe Kournia, for all her support, all the lab members, the organization committee for giving me the opportunity to present this project. I would also like to thank the State Scholarship Foundation for the financial support, and of course, all of you for the attention. Thank you very much.
Thank you very much, Alex. Very nice talk. I see that there is already one question in the panel. So did you try your system on the output of AlphaFold 2, including multimer version? By the way, do you see the questions? Yes? Okay, I will read the questions. Okay,
okay.
No problem.
I see the chat and the Q&A. So to answer the question about AlphaFold 2, I tried not in the multimer version, in the initial version of AlphaFold 2. The problem with AlphaFold is that in many cases, the N or C terminal is not folded and is not accurately predicted by AlphaFold. And these parts, the N terminal, the C terminal, or parts that connect to different monomers are not folded, and they have a very high solvent accessible solvate area. And this is probably the DREAM tool, our predictions, are going to have false positives in these areas. Predictions from AlphaFold 2 are not the best for inputting in our web server unless the user cuts by its own the areas that are not folded.
Thank you, Alex. There is another question. Could you comment on the pros and cons with respect to orientations of proteins in membranes?
Well, the OPM, I guess, database. OPM database contains the results of the PPM tool, actually. The pros is that our tool, in many cases, have better results. Also, OPM tries to put the protein in the membrane, and in many cases, it does that with mistakes, by doing mistakes, which is not the case in our tool. In my opinion, one has to try all tools and make his own choice of what he thinks is the correct or not. But I think that both tools have very comparable results. If you try both tools, you will see that they have very, very similar results in most of the cases. But in many cases, our machine learning algorithm is better.
Okay. In the meantime, Antoine, who was asking you the first question, has written, thank you. Are there any other questions? I try to see also in the chat. No. So if not, thanks again, Alex.
Hi, thank you very much for watching me.
You're welcome. And I would like now at the end of this session to congratulate all the speakers for their very nice presentations and their fantastic research. I don't know whether, Zoe, you have something to say before the coffee break?
First of all, thank you very much, Benoit, for a wonderful sharing. Everybody was on time, but still we had time to discuss, and that's really great. And before we go on the coffee break, I think it's time to have our first poll for the award that the audience is going to give to their preferred presentation among our 3 short talks for the session in artificial intelligence and chemical research. So perhaps we can run the poll, Anna. We will leave maybe how many, 1 minute or 30 seconds? What is the time limit that we have here? Let's leave 1 minute, because I see it's 170 people, so I'm sure everybody needs their time. And we already have lots of responses. They're coming in. So close to 90 responses, which is really, really great. Thanks everybody for participating. Okay, the answers are still coming in, so we're gonna let this go on a little bit longer. Okay, another 20 seconds to go. If you haven't voted for your favorite presentation, now it's the time to do so. Okay. I think we have a winner, so we can close it. Thank you. Thanks to everybody who voted, 130 responses. That's really, really great. 70% of participants voted. Fantastic. So let's all go to a short coffee break. We have 10 minutes for the next session, which will be on materials. And well, while we're on the coffee break, I could present an interesting initiative that we have with the Journal of Chemical Information and Modeling. I can share my screen here. Right. So JCIM is one of our sponsors for the European Conference on Computational and Theoretical Chemistry. And the JCIM is a journal that aims at scientists engaged in developing new methodologies in the fields of chemical informatics and molecular modeling. And all of the topics that were presented today and that are in the conference material, in the conference program, are relevant for JCIM. I'm an associate editor for JCIM, and we welcome articles and contributions as viewpoints, as full-length research articles, perspectives on hot topics, reviews, letters, and we also welcome application notes, which are novel software package reports, databases, web servers, so new tools. And we have also now a new initiative, which is a special issue, Advancing Women in Chemistry. We are launching the call for papers. The platform is already open with a deadline in February. So if you have an interesting paper that you would like to share in this special issue, what we're trying to do is to encourage women to submit manuscripts, but not only women can submit manuscripts in this special issue, of course. Everybody can submit a manuscript as long as they are supporting women in chemistry and they can state that. So yes, please submit your papers. It's for a good cause. We're trying to boost the participation of women in computational chemistry, but in general, to advance women in chemistry. So if you have an interesting article that you would like to share, please consider this special issue. And with this, I will leave you to enjoy your coffee before we go into the next session of materials. Okay, we still have 1 minute before we start the material session. And after the materials, we will have the flash presentations. The flash presenters are going to speak for 3 minutes each. In order to promote the flash presenters to panelists, we now ask all flash presenters to place their names, their actual names in the Zoom as they are coming in, so that we can know who are the flash presenters and promote them to panelists. So if you're a flash presenter and you can hear this, please write your name, follow the 3 dots and rename your name to your actual name so that we know whom to promote as a flash presenter. And with that, I would like to welcome Tanya van Moorik as the chair of the next session in materials. Tanya, we cannot hear you.
Hello, I'm Tanya van Moorik. I will be chairing this session. So the keynote speaker in this session is Nong Atrit from Utrecht University in the Netherlands. And her talk will be on modeling of complex energy materials with machine learning. So Nong, please go ahead.
Thank you very much, Tanya, for the nice introduction. So you see my full screen, right?
Yes.
Okay, that's nice. Yeah, thank you very much again for the kind invitations to this conference. It's really nice to see many people here in these rooms, almost 160 people here. So I am Nong Atrit. So I just joined Utrecht University a few months ago. The work today that I will discuss is based on my previous work from different places. So in this lecture today, I will discuss and show you how to do simulations, or how we modeling of complex energy materials with machine learning. So using our machine learning models or machine learning framework, the atomic energy network. And then after we develop machine learning models, we apply to complex energy materials. And when we get the machine learning model and also database, we share with the scientific communities. So as you know that many energy conversion processes are based on reactions at interface that can be very complex and very complicated for the simulations. For example, here in this cartoon of electrocatalytic CO2 reductions, so to model such a complex processes, so we have to find the energy model that can describe complicated phases such as liquid solids and interface, and sometimes also non-ideal surface with various type of defects, or sometimes also include the solvent effect. So as you know that first principles or DFT to simulate such a large system size like this, it will be very difficult. And another examples, this is batteries materials that I show in these 2 examples of the, for example, on the left is interface in the solid state batteries, and on the right hand side amorphous silicon anode. So many aspects of batteries are complex for the DFT calculations. So consider these 2 examples as you can see, right? So this is the cathode, lithium cobalt oxides, and the interface is this order of the lithium cobalt oxides, and the electrolytes here, a lipon. You can see that this is some kind of like a non-ideal structures and nanoparticles. And also the same for the silicon anode here, there are so many different phases occur. So both systems that I show here, they are nanostructures, and also look at solid-solid interface and amorphous phases. And these structures really are very complicated, and the importance properties really of batteries that we really need to capture, and to model such a system like this, it is really very complicated. So what we did is that we combined atomistic simulations and machine learning to looking at such a complicated systems, especially for the interface here, like I show in this cartoon in the orange regions. So what we did, so we use machine learning potentials, for example, to describe or to describe the representations of potential energy surface, or PES, from really accurate energy methods. For example, in the quantum mechanics database of first principles or density functional theories or DFT. And then we use the accurate energies or forces or charges that collected, and in this quantum mechanics database interpolate use a machine learning model to interpolate and construct efficient and accurate machine learning potentials, and then use it in applications for large range and long time scale simulation, for example, in MD simulations or in Monte Carlo simulation. So the approach that we use is artificial neural networks for the interpolations, because they can be very accurate and can be really trained on really large data sets with, for example, millions of data points. And the models that we need as an input to describe based on just only atomic positions. And when we construct, we can really get the potential energy surface with reactive and full dimension. But of course, this is not that easy. It takes also a bit of effort to construct and so also validate them before we can use in our intended applications. The idea to use neural network to represent potential energy surface actually is not new. Like you can see here in 1995, Dorrand and group already show and published in JCP that this is the first PES to construct neural potentials to describe the complex system like a nickel 111 surface in the environment of the CO molecules. And then 2004, Machette chapter groups show that the symmetry adapted coordinates for neural network to represent potential energy surface. So describe palladium 100 and potassium and hydrogen molecules. But for the first time that Baylor and Pilinero show in 2007, published in PRL, to describe like a very high dimensional neural potentials that can be used in any number of atoms, but they describe in only chemical species, only just for one is a silicon, but many different phases of silicons. When I joined the Baylor group as a PhD student, so I extended together the methods together with Professor Baylor to multi-component systems by also including electrostatic interactions, and we demonstrate the results and the capabilities of the potentials with zinc oxides. And then later when I moved to work as a postdoc with Professor Seda, we are looking for very complicated battery materials, which is many different compositions. So we also develop further. I will also discuss this method in the next few slides, but just to briefly to show that in 2017, even from Rorschach groups also show really large data sets, the FT data set with any force field with really general organic molecular systems that contain many different chemical species, hydrogen, carbon, nitrogen, and oxygens. So you can see that since 2011, neural potentials have become more and more popular, and number of publications per year is now really growing really very fast. So I just did type in Google Scholars and search neural potentials. You can see that the paper really growing really fast. And during the last few years, that the term of neural potentials also really changing. For example, machine learning force fields and also machine learning potentials. So I just sum up all of the paper here. You can see that number of publications really many. But as you can see that there are so many different databases and also many different number of publications, but still many potential energy surface based on neural network not really can reuse for different type of applications. So this means the field still growing and also still active and needs many different improvement, especially in the method development. So before I really show my applications, I would like to point out that the input or how a high-dimensional neural network make it really works for complex and to describe complex energy materials. This is one important or one feature is that we usually have the input and also machine learning models, and also the output is the energies or the forces that we can use in MD and MC simulation. But our focus in this talk we really would like to demonstrate that the descriptors or the input part is very important, because the descriptor has to follow the invariance of the energies. Look at these equations, right? The properties of the atomic energies. So total energies of a structures, or here sigma, is the sum of atomic energies. And the atomic energies have to follow the physical invariance of the total energies. The atomic energy have to be, for example, also invariant with respect also to exchange of equivalent atoms, and also with respect to translation and also rotation of the structure, like I show here in the cartoon that you see here from the cartoon. I don't know if you can see my cursor. That, for example, if you have water molecule like H2O, so you have H1 and H2, even it's exchange or separate or stay in different position, so the energy should be the same. So this is as the input of our descriptor that we have. So additionally, the descriptor needs also have to be constant length, and neural network has to, neural network has one specific number of input nodes. Therefore, the length of the atomic structure descriptor has to be constant. Not only that, the size of the descriptor also has to be independent of number of atoms and also chemical species in the structures. So we made a wish list of the descriptor of the local atomic environment. So this is what we believe, that the descriptor should be automatically and should not require too many tunable parameters. Its accuracy should be systematically improvable. It should also be as efficient as possible. And its computational cost should not depending on number of chemical species, right? If you want to describe really realistic and complex system. So this is the descriptor that we use. This is based on the Chebyshev expansion. So the descriptor for the local atomic environment, or the fingerprint, or the descriptor that we use based on an expansion of the local radial distribution functions, or RDF here. Not only that, we also use angular distribution functions, or ADF, like you can see here, which is in the basis set of Chebyshev polynomials. Here, phi, like you can see here, or phi alpha, and it's a Chebyshev polynomials in order of alpha. And the C alpha is the corresponding expansion coefficient. So as you can see here, and the local atomic structures in the top figure here, A and C, like you can see here, with the coordinations of all atoms within a R-cut like RC, which is described by two sets of coefficients. So one for bond length distribution, or RDF, and then one for ADF. So this is our local atomic environment descriptors. And now how to do with many different chemical species. So we introduce a second set of weight coefficients, which is used to capture the local atomic compositions or atomic types, or T, or many different chemical species. Here I use the notations W or WT or WTJs, which is to describe all different type of elements specifics. So how to deal with this different type of chemical species? If you have one chemical species, so our weight type will be 0. So this means you only have the local atomic environment descriptor only for structures. But if you have two chemical species, we have -1 and +1. Or if you have 5 chemical species, you have -2, -1, 0, +1 and +2, for example. So this is the notation or the way that we use to describe our structures. Maybe sometime it's easier to look at equations than just the cartoon that I just draw. So here are the equations of the Chebyshev descriptors for the local chemical species or atom type T that I just described in the previous slides. So the descriptor components are really the expansion coefficients of the RDF and ADF. The weights WTJ are specific for atomic species, and the descriptor for the local structures actually is equivalent, but all of the weights are just equal to 1, for example. So we did benchmark for different types of systems. For example, in this case, in the middle figure here, we take a look at the lithium titanium metal oxides. This is rock salt structures, which is contained from many different chemical species. The database that we take from the open data from material projects. On the x-axis, this is the descriptor dimension that we use from our Chebyshev polynomials expansion. And the y-axis, this is the accuracy that our neural potentials predicted that we are looking at in terms of RMSE. You can see that many different databases and many different compositions give really very good agreements with the reference, the FT data. The error is around 3 millieV per atom. And the same is also for molecular system. This is the amino acids complex with even up to 11 chemical species, also very good agreement with the DFT. So this is how our models can describe really complex systems. And not only that, we also think that so far we only discussed neural potentials trained only on energy only, but actually if we want to use in MD simulations, atomic forces also are important, right? So in this work together with April and Professor Keisner and also Professor Urban, so we propose an efficient approach for training neural potential, including atomic forces via Taylor expansion. So usually if we have a large data set, for example, if we have like in this case, this is just a sample that we test. We have like 2,000 structures. This is the errors in absolute forces. You can see that the forces in absolute forces give quite good accuracies. But if we have only 500 structures, use only energy training already, I think it is quite a high errors. You can look at the tails. It's really spread very much. So this means more data points, it is better to predict the forces. And also here, looking at the directs of the forces, if we have many data points, the mean absolute error of the forces are getting better. So, but in realistics, we cannot generate reference data that too many in the short time. How can we help? That's why we propose and we try to implement or find alternative ways. So we are looking at the Taylor expansion to estimate, for example, energies of the structure with small displacements of atoms. For example, in this equation, in this now the energies that we have. So we introduce small atomic displacements to include force information in the training set. So look at the example of carbon or the C dimer here. If we use only energies only to train in the neural network, this is the x-axis, this is the bond length, and this is the neural network or energies or forces. And we have only 7 data points or sample or DFT data point, for example. And then we train neural potentials. You can see that it is slightly predict wrong distances and also wrong the energies. But now we use our approximations information with Taylor expansion and we train neural network potentials. And you can see that our neural network improved the accuracy, that we have also accurate atomic structures and also energy correctly. So why we only use why don't we just use direct force training? Because it looks so good here. So this example with April dataset with water 6 molecules, direct forces give really very good agreement. But using our models, random displacements with Taylor expansion, give also not too bad, right? But then when we're looking at the CPU time or even the computational courses, direct force training have like 8 times take much longer than our methods, training with just use Taylor expansion methods. So basically, if you work on the cluster or isolate molecular system, it is okay to use directly force training in your training set. Is excellent, it's good. But most of my work and complex system, I mainly work on condensed periodic structures, and it's not easy to include all of the force information in my models. For example, in this case, we have very complicated, for example, the disordered cathode materials for lithium-ion batteries. So this is 5 chemical species, and there are so many different directions and many different types of chemical species. So it's not really feasible using direct force information. So we use the Taylor expansion, expansion method, include force information. And we see that the errors of false information is also not too bad, like you can see here. So how to check and validate our test? So we use the model to train and run MD simulations. For example, here, we only use these 800 DFT data points to run MDs, to train only energy training only, and then run many times many different MD trajectories. You can see that only energy training and run MD simulations only. So both only energy training not really have a very stable or good MD simulations. But one of our neural potential use for information, you can see that it's really have to stable MD simulation, make our simulations really stable. But note that this one is it just as a benchmark. It's only 800 reference DFT data points. It cannot use it for real applications. If you want to use this for real application, we need to include many more data points and many different configuration. It really depending on your application. So in brief, how neural network fitting really work, this is show example of water dimer. The black diamond, this is show the DFT reference, and the solid line show neural network fitting, but this is it before fitting. And in the same time, for high dimensional structures like complex copper gold, you can also see here the crystal structure that we have, like a gold 1 copper 3, gold 2 copper 2, or gold 3 copper 1. And this is the symbol show the reference data. And after a few iterations of optimized neural network parameters, you can see that our neural potentials can really predict energies of the DFT reference data accurately. So this means neural network can really establish a functional relationship between the structures and its energies. This is the workflow that we have, how to really construct neural potentials in practice. So basically, just in summary, we have the sets of the database, and then we have data selections, and then we select the machine learning models and how to validate and optimize hyperparameters, and then validate them. If they are already good, then we can test with the real application. In our test application that we would like to really do simulation, if this is not working, or we have to really maybe use another tool, it's called active learning, to find and add more structures that can really help to cover potential energy surface. And then again, do is as iterative refinements. And if really our potential really good, then we can use this in real applications as you for your own research. The implementations of the methods or approach that, as I mentioned before, is already implemented in our free and open source, the Atomic Energy Network. We have it, you can follow this from this website. We don't only just do predict only energy and forces in our ENIT code, we also provide libraries that ENIT can really interface with many different professional MD and MC codes, for example, ASE, LAM, Tinker, DL Poly, or even the genetic algorithms. So we already discussed and implement and show also how to use it in this JCP just published in 2021 here. So our ENIT also compatible with many different high performance computing architectures and systems. So we already test with many different computer clusters also in the US. But right now we also just have allocations at the Dutch government NWO South Netherlands here, scenarios, which is really very highly parallel together with Professor Urban in Columbia. So we also test and benchmark and continue the development at Columbia universities. And not only this, there are so many different features that we have been worked on ENIT and also developed together. For example, the ENIT lamps that we just have it together with Tobias Molowitz and Michael Shen and also Professor Markland and Dr. Mori for the Taylor expansion methods together with Aprils and Professor Kaiser from Stuttgart universities. This is just briefly show and benchmark how highly parallel of the neural network potential together with the LAMS code here. So in realistics, we don't really do simulation with million of atoms, but in this case, we just do as a benchmark. with 1 million of atoms, it takes like a 15 seconds on the CPU, like a 96 CPU on supercomputers, like you can see here. So it's really very highly parallel. So let's take a look a few examples of our applications. So we really, over the years, we investigate many different research questions in energy conversion and also energy storage. For example, for catalysts, we investigate the metal support interactions, solvent effects, and also active sites in oxides. So in batteries, we simulated the structures and lithium transports in amorphous and also nanostructural phases. This is such a system site that we could really use our efficient and accurate neural potentials to looking at copper zinc oxides, which is a good catalyst for methanol synthesis. So this is just to show you like how efficient that we can use it to simulate such a system, like around 8,000 of atoms that we do simulations. So after like 300 picoseconds, you can see that the copper zinc on the zinc oxide is supported and show very similar structures that can provide and also show from our collaborator. This is the STM images. Yeah, this is really very nice. So without the neural potentials, we cannot really do a simulation with such 1,000 of atoms like this. And not only this, this is just I think I can only show one example, like a copper gold nanoalloys. This is a catalyst for CO2 reductions. So we work together with our experimental collaborators, Professor Yang Chaohong. So they found that copper, this is in the light blue here, is this good catalyst, but it's oxidized too fast and stay in the reactors really short time. But once they start to mix with a gold, it really makes the composition and the very long and stable in the reactors. So, but the cluster size is really large, like a 5 to 10 nanometer cluster size. So how can we really use or apply efficient and accurate neural potentials to help to find the compositions and also the surface structures? So first, we help to take a look at the copper gold nanoparticles in vacuums, and then we do simulation of Monte Carlo's annealings together or use our neural potentials. You can see that really rearrange the gold is in yellows and the copper is in orange. In vacuum with many different cluster size, you can see that the nanoparticles is really stay and mix like you can see here. And look, if you take a look at the CPU time, for example, in one structure with 147 atoms, if you use a CPU with like a 16 cores to do the FT calculation, it takes around 3 hours. But with our efficient and accurate neural potentials, it takes just 1 second. Like you can see here. If we have like a 4,000 of atoms with DFT, it will be really very difficult. And not only that, we can also extend our database and include this more realistic by including like a more chemical species. In this case, we use water to demonstrate and how this copper gold nanoalloys really react in solutions. So you can see that with efficient and accurate neural potentials, we can really find many different compositions of the more realistic atomic structures. Not only nanoparticles, it's also like a for larger interface like this. So final quick example, this is we also looking at lithium transport in amorphous silicons for high energy density battery, because during the battery cyclings, many different compositions occur, and this is not easy to capture all of the compositions, right? Okay, I have no time, right? Yeah, but okay, just wanted to let you know that briefly to show that we also apply neural potentials to looking at many different phases, like a map this complete the phase diagram of many different crystal structures and also amorphous structure here. And we can also use it to looking at many different parts of how lithium really transports in the structures in different states of the batteries. And also can use it really run long-term MD simulations, and we can really simulate many different type of structures, nanoparticles, and also complex complicated structure in different compositions. And we can also predict lithium diffusities in the structures. And not only that, our neural predictions is also give good agreement with the experimental measurements like you can see here. So this is the my conclusions. So there are so many different work you can also take a look and also check, or if you are interested in using ENIT, you can also contact us. We are happy to really help. So I hope that I could show that using more information like force information based on Taylor expansion help to improve and make MD more stable in the simulation. And also, yeah, all the time when we do simulation with machine learning models, we really need to validate the predictions with, for example, compare with the more accurate methods and also from the more realistic, like experimental measurement. So, and finally, I would like to thank my collaborators and also facilities, the students at Columbia, and also April Coopers who helped to develop the Taylor expansion, and also the discussion with Professor Urban, Dr. Hyberson, and also Dr. Shen, and also Annika Stuckert to develop the batteries model that I just discussed. And thank you very much for your attention.
Thank you, Lauren. Are there any questions? I think there's one question coming in. It's a question from Mihai Krimpai. Thank you for your brilliant presentation. I wonder if you are prospecting the use of Monte Carlo EuCos in adiabatic quantum computers such as Drive 2 or the new e-EuCo-quantum supercomputer.
Which computer? Oh, so sorry.
It says Drive 2 or the new e-EuCo-quantum supercomputer. Sorry, I don't know either.
Ah, so sorry. Maybe this is the question.
You can also see the question in the chat if you want to see the names of the computer. I think they're asking if you can use quantum computing.
Ah, oh, okay. We don't do quantum computing yet. We only do, yeah. This is the model that we have only evaluate like accurate energies and forces that as close to like the first principles accuracies. For example. So
we have another question. Could you comment on the surface reconstruction of surface from your machine learning potential model?
So you are saying like how to construct this, right?
Yeah, I think it's just a comment on the reconstruction of the surface.
Ah, okay. So from the couple, I guess this one, right? So okay, the surface reconstructions of the surface from your ML model. Actually, this is what we have. This is the model that we get. Is from the Monte Carlo simulation. Is it rearranged? It is when you have once you have like first we have like a 2-1-1 surface, but after and first we have like a mixed terminate like copper gold, like you can see here is like a perfect mix. But once a Monte Carlo simulation and also with water, you can see that sometimes copper also like to go to the surface and also more go on the surface here. So when you have different compositions and also make your surface is slightly changing from the original. But actually, we also did experiments also with like the surface like a 1-1-1 or 1-0-0. So sometimes we also see the slightly different surface when we start to run Monte Carlo, and we also see different type of rearrange.
Okay. I see no more questions at the moment. If there are questions later on, then...
There's one more question in the chat from Anna Hen. If you can sit before Mihai's and after one, there's two.
Okay, the question regarding the applications on mixed cold copper clusters, would it be possible to train only on small clusters and then go towards large clusters? Morphologies often differ significantly for smaller, larger nanoparticles. Do you think that neural networks could predict a change in morphology?
Yeah.
And this is the last question.
Yeah. So actually, we include also small cluster and a bit large cluster, and we also include the surface slab models with different the surface like a 100, 111, or 211, so that it can really capture also when you have large nanoparticles, that we draw the woof constructions from the surface energies that we have. So, but I don't show it here in my slides. So the model that we have, we include many different, for example here. So we also include the slab model that contain many different small phases, like you can see here. But when we have slab model, we don't have many atoms, right? Like less than 200 of atoms. That's also included in the training set. So when we have those type of surface structures in the training set, we can also predict larger nanoparticle, like you can see in my like 4,000 of atoms. Yeah.
Well, thank you. In the interest of time, I think we should move on. So thank you very much for a very, very nice presentation. So the next talk is by Adriana Pietropaulo from Università di Catanzaro in Italy. And her talk is on multi-replica bias sampling for photoswitchable conjugated frameworks. So Adriana, please go ahead.
Yes, good afternoon. I hope you are sharing my screen. You are seeing my screen?
Yes, we can see it.
Okay, that's perfect. So good afternoon to everyone. And first of all, I would like to thank very much the organizer to give me this chance to present some of our recent research. Why we are interested in photoswitchable frameworks? Because this kind of conjugated frameworks can be used, for example, for photovoltaic inks. For example, in a near future, we can have our walls in our home with these solar panels inks. Or these can be used also in photopharmacology. For example, bilirubin can undergo to trans-cis transition and can become from insoluble in a soluble form. This can be used to treat neonatal jaundice in baby boys in a mechanism very similar to what is happening in our eyes in this moment when our eyes are irradiated by light. So the cis-trans transition that undergoes in the retinal. Against conjugated frameworks, photoswitchable conjugated frameworks can become chiral in excited states and can emit circularly polarized light that can be used in a next Zoom meeting, like sitting in a Jedi conference in a Star Wars meeting, or also very important to have an accurate resolution or materials is activated by light, can undergo to excited states and can come back to another free energy minimum, for example, in this case, the second one, and can be populated with different property from the first free energy minima of the ground state. So motivated by these aspects, we are studying switchable rotation that can be coupled with temperature and light irradiations. So we test as a molecule oligofluorine, substituted in the 9th position. So polydioxyl oligofluorine of 5 mer. And we first need to get a force field for both ground state and the steady states. So we scan a dihedral scan, finding the ab initio total energy. Then we did a linear least square interpolation, minimize the differences between ab initio and force field molecular mechanic energy. And then we obtain the coefficients of the torsional potential energy. So like in this way, we calculated also the free energy at 200 Kelvin to have a good indication that the nonlinear least state interpolation got good coefficients in the force field where we derived. So if we write down the free energy, we can see that the electronic state's free energy differs only for the torsional potential energy terms. So basically we can derive free energy in the ground state, first excited state, second excited state, that differ only for the torsional energy, potential energy, because basically the molecule can rotate under light irradiation. So the torsional potential is basically what differentiates ground state from excited state. In order to have a sampling in ground state and all the excited states, we use the replica exchange methods in order to have many replicas of the systems that represent a given electronic state. So one replica for ground states, another replica for the first excited states, and so on. In order to get an overlap with the torsional potential energy that represent each replica, we use a control parameter lambda that differentiates each replica. So basically, this parameter represents the final formulation of the torsional potential, in which we can start for all the lambda equal to 0, so we are in the ground state, and then moving to lambda 1 equal to 1, and the other lambda equal to 0, so we are in the first steady states, and then moving lambda 1, lambda 2, 1, moving the second steady state until all the lambda are 1, so we are in the final steady states. In order to run free energy simulation and to sample every free energy landscape, we resort to parallel bias metadynamics using as collective variable the hydrals. We use parallel bias metadynamics because in each collective variables we had one monodimensional metadynamics bias potential. And finally, to estimate the free energy differences between the ground state and excited states, we use free energy perturbation theory, in which we simply calculate the free energy differences between neighbor free energy minima. So the summation of these variation in the free energy differences give exactly the absolute free energy differences between each electronic state. So what we observe is that using the 9,9-dioctylfluorane, 5-mer of this oligofluorane, substituted oligofluorane, we observe that the free energy minima were not degenerate. So we have different free energy basins, and these were in accord with experimental observation that the 5-2 helix of this polymer that have the hydrals of 144 degrees are more stable than the other the hydrals at 40 degrees. This is in contrast to the unsubstituted oligofluorane. So without the substitution, the free energy basins had the same stability. So the dioctyl side chains remove the degeneration of free energy differences as a function of the hydrals. Also, this kind of polymer can undergo positive to minus twisting dihedrals. This is quite important to study chirality in this kind of polymer and also chirality emissions. And the switching, the dihedral switching undergo through the periodicity of 180 degrees. Also, the coplanar states are stabilized in the, especially in the first singlet excited states. Coplanar states are stabilized during irradiation, and owing to the coplanar stabilization, to the lowering of the free energy barrier, there is the switching between positive and negative dihedrals. We also test these free energy methods by calculating the electronic emission spectra, sampling the conformation in the free energy basins of the first singlet steady states, and calculating the oscillation trends and using the free energy differences we obtain in the free energy profiles. So we basically use all the conformation we sampled in the first excited states to calculate the emission spectra. All these data can be found in the Plumed NAST repository, so under this ID, in which you can find the topology, force field, Plumed input files, every information related to this kind of simulations and many more. If you want to visit the Plumed NAST repository, you can find a lot of Plumed input files if you want to run metadynamic simulation with a lot of methods and collective variables. So, concluding, a simulation framework coupling radial exchange, parallel bias metadynamics, free energy perturbation have been proposed to reconstruct the free energy profiles and estimated free energy differences under light irradiation. Also, the calculation of free energy differences between each electronic state is an absolute value because there is an average term in the free energy perturbation formulation. This method is quite important if you want to consider thermal effects coupled with electronic transition. So that's why we're calculating free energy, because these kind of frameworks are very sensitive to temperature. So not just a static calculation with potential energy surface, but free energy is quite important if you want to take account of thermal effects. Next direction will be to screen excited state twisted frameworks, because we want to test how the twisted conformation and distortions can cause and increase the circular polarite emission in chiral materials. So I would like to thank very much Dr. Max Bonomi that worked with us to realize these simulation frameworks, and Professor Tamaki Nakano that works with us in the experimental synthesis of polymers, my research group, Dr. Maria Grazia Fortino and Gioacchino Schifino, and thank you very much for your kind attention.
Thank you very much for your talk. Are there any questions? So we have one in the chat. So thanks for a wonderful presentation. Considering the predicted emission, did you shift your spectrum or was it directly issuing from your computations?
Yes, with slight shift of 10 nanometers in the blue part, yes, there is a shift factor. Thank you very much. This depends on the time-dependent DFT potential energy scans that we used. Yeah, thanks. Excellent question. Thank you.
Are there any further questions? I don't see any at the moment, but I'll wait for a minute, see if anybody types. Okay, so there's another question. Yeah, so please, Camilla, go ahead with asking another question. What is the computational cost for this kind of study?
Yes, actually is not quite high because we use, you can use also 16 core for each replica, but it depends, okay, it depends on the energy gap between ground state and excited state, because if the energy gap is very high, of course, you need to use a lot of lambda window. But if the free energy gap is not so high, for example, also 2 electron volt, 3 electron volt is not so that high. So you can go to normal supercomputers, also with 256 cores. So it depends on the free energy gaps, but actually not that high. It's also because free energy converts very, very soon with parallel bias metadynamics and replica exchange. So I can say that is straightforward.
Any further questions? I don't see any further questions coming in. So thank you very much for your nice talk, Adriana.
Thanks, goodbye.
So the next presentation will be by Daniel Reiter from the University of the Basque Country and Donostia International Physics Center in Spain. And the title of the talk is Ab initio spin dynamics of high-performing single molecule magnets. So Daniel, please go ahead.
Yes, thank you. Let me just turn on the pointer. There you go. Thank you very much, Tanya, for that kind introduction, and thank you all for having me. So today I'll be presenting our theoretical work on spin dynamics of single molecule magnets, and I'd like to start by addressing what makes single molecule magnets so interesting and worth studying. So in a very simplifying way, one can think of a single molecule magnet as a set of pure magnetic states, and each magnetic state has a very defined magnetic moment, and those states are very well separated by energy. And in such a case, if you are to apply an external magnetic field, for instance, low temperatures, what you cause a population bias, which is represented here by this all the population being in the most magnetic state. And then if you let the system evolve, because of these characteristics, it will take a certain time for the system to transfer all its population from the most magnetic state to all of the different states and reach net magnetization of zero, so equilibrium basically. And it is precisely this microscopic mechanism which is behind the macroscopic properties that we observe in single molecule magnets and that make them so interesting, namely the magnetic hysteresis and slow relaxation of magnetization. And having a magnetic hysteresis is interesting because one, depending on the history of the sample, one can access two very different values of magnetization at a given applied field. And that's precisely the definition of a bistable material, of a bistable molecule. But interestingly, this is due to the molecular origin. So it's just down to the very molecule of your system. And that's precisely why, or that's the reason why these systems have been always, from the very beginning, proposed as the paradigm of miniaturization of data storage devices. So that's what makes them interesting. And then also the question of why spin dynamics. And to answer that, one has to realize that what drives spin dynamics is nothing but the interaction of vibrations and electronic states. And that happens in all kinds of matter as long as you have a temperature, so a thermal reservoir, basically. So basically, counting with a tool that allows you to describe spin dynamics, or more broadly speaking, vibronic coupling, offers the possibility to study a broad range of very interesting problems, and that's the reason why we're very interested in this. But now coming back to the specific example of, or specific case of single molecule magnets, I'll now introduce the concept of the relaxation profile. The reason why and this is an experimental signature of the single molecule magnets, and the reason why I'm doing this from the onset is because all my calculations will be compared to these experimental results. So the relaxation profile is nothing but the temperature dependence of the relaxation times of your system, basically. So if you were to measure how long it takes for your system to relax at a given temperature and then record the different at different temperatures, you would end up with a profile, a relaxation profile, which normally in high-performing single molecule magnets is composed of three regimes. The first one at the highest temperatures shows a very pronounced dependence with temperature, which is exponential, and is due to the direct coupling between pairs of electronic states through single phonons. Then you enter a regime in which the dependence is not so pronounced. It's a power law dependence now, which is due to what is normally referred to as Raman, and is due to pairs of phonons. And then you enter the coldest temperature, and you would think that, okay, my states are so well separated that there is no thermal energy to couple anything, and the system is not going to relax, but the system will, of course, outsmarts you and finds ways of transferring population from one side of the barrier to the other, in this case with quantum tunneling of the magnetization. So today I'll be focusing on the Orbach part, mostly because it's the mechanism that contributes to losing the magnetic memory effects quickest in your samples. So the way we go about trying to simulate these relaxation profiles is, first we optimize the geometry and calculate the vibrational modes gas phase, not using DFT. And then we calculate the vibronic coupling, and this entails three steps basically. So taking the optimized geometry and calculating its electronic structure, taking the vibrational modes and distorting the equilibrium geometry, and at those distorted geometries, calculate again the electronic structure. The way we do this is with open molcas, with CAS-CF approximations. In the case of dysprosium centers, which is the case for all the results I'm going to be presenting later on, we have a problem of 9 electrons in 7,4 and 7f orbitals, but our method also works for other lanthanides, and is sort of been tested. So basically what we do later on is we model, or we decompose, or yeah, I think we can say that we decompose the CAS-CF results into a phenomenological crystal field Hamiltonian, which is basically a set of 27 parameters that allows you to fit and model the electronic structure of your problem in a very convenient way. Then we calculate the transition rates. So basically the rates between the transfer population between each pair of states using the standard Fermi's golden rule depicted here, which is composed of 3 elements. The first one informs us on whether the vibrational motion is actually affecting the paramagnetic center. And the way we go about doing this is we define a spin-phonon coupling Hamiltonian, which is made up of first derivatives of the crystal field parameters with respect to the displacement. We obviously do this for each of the vibrational modes. And then we evaluate it on the equilibrium basis. So it's an adiabatic approximation there. Then we have the vibrational occupation number, which is, it's basically asks the question, is the vibrational mode occupied at the transition energy? This is just both Einstein statistics. And then we have the vibrational density of states, which we model here with a simple Gaussian function. It's important to note here that this is where the only free parameter in our model enters, which is sigma, or full width half maximum of the Gaussian that we apply to the vibrational mode to broaden it. And then once we have all these transition rates for all pairs of states, we simulate the dynamics as making use of the master matrix formalism, which in a nutshell is telling you the change in population of a given state with time is everything that goes into this state minus everything that leaves that state. Basically, you can build a matrix, which is a set of differential equations that you can diagonalize and directly obtain tau, or the relaxation time, that you can compare with your experiment. So now I'll just jump in to present the results. These are the molecules that we have studied. These are the best performing single molecule magnets to date in the literature. And as you can see, they all are fairly similar. They all are based on a dispersion center, which is sandwiched between these cyclopentadienyl ligands. And the differences between them are just down to the substituents that we have in the cyclopentadienyl. But interestingly, despite this structural similarity, their magnetic properties are very different. And I don't know if I mentioned this in the beginning, but these are the blocking temperatures, which are customarily defined as the temperature at which your relaxation time is 100 seconds. So you have a single value that you can compare across series. So as you can see, they are very, very different. So we thought that was a perfect test case to test our approaches and try and say something meaningful as to why these systems, despite being structurally similar, behave so differently in terms of their dynamics. And I just jumping into the results here. I'm presenting again the experimental data compared to the simulations in the solid lines. And what we observe here can be summarized as the results for a given molecule are full width half maximum independent, and this is important because that's the only free parameter that enters in our model. That we consistently overestimate the relaxation times around an order of magnitude, but despite this, we get the order right, meaning that we predict that molecule 1 relaxes the fastest and molecule 6 relaxes the slowest. And as such, we can tentatively conclude that our method is a predictive tool, which is very good, but you not only want a method that is predictive, you want a method that allows you to understand the problem that you are studying. And for that, we looked at the differences between molecule 1 and 6, because these are the most distinct ones, and looked at the problem from a slightly different perspective. So now, instead of building the dynamical matrix and diagonalizing and getting the rates, we realized that for each transition rates, only a certain number of modes were contributing. So what we can do is recast or express the relaxation, the gamma matrix differently as a product, Hadamard matrix product of the different components, so we can pick and mix the elements of different compounds and see which one brings about the largest differences. And that's what we did. And here I'm showing you all the different combinations, but only highlighting the one that brings the largest changes, which is consistently the vibrational density. Sorry, the vibrational occupation number here highlighted in green. So when you put that of 6 in the elements of 1, makes the rate in 1 slower, and conversely, when you do the same for 6, it gets faster, which is consistent with what we observe here. And what this is telling us is because the vibrational occupation number is proportional to the energy difference between the states, the reason why this is a better single molecule magnet to this is simply because the energy gaps are larger in 6. So that allowed us to ask the following question is, okay, so can we try and come up with molecules that enlarge this crystal field splitting and behave, present improved single molecule magnets. So, and to do that, we looked at a range of molecules, hoping to precisely modify or address the factors that affect the crystal field splitting in your system, namely the distances between the acyl ligands, the angle between them, and the charge of the ligands. So now I'm going to guide you through the results. This slide is going to get messy quickly, so let me try and break it down for you to make things easier. So here I'm showing the predicted relaxation rates for 6, the best performing experimentally determined molecule. And now on the right, I'm going to be showing you 2 other numbers. First, the first energy gap, and then the total, the overall crystal field splitting of your molecule. And when we apply this, for instance, to this molecule, we get what we expected. So namely, smaller crystal field splittings result in worse performing single molecule magnets. So far, so good. But then when we looked at the 4-member rings, we saw the first surprise in this, exemplified in this trace here, because we have something that has an energy gap of the first excited state that's smaller than 6 and relatively similar to the overall crystal field splitting, but still it has an improvement of around 2 orders of magnitude in the relaxation time. Then when we looked at the 5-member rings, we observed something similar, but even more pronounced, more exaggerated in the sense that now the improvement is, it gets to be around 4 orders of magnitude, and the crystal field splitting is smaller than that of 6. So we applied our methodology again to understand why this was happening. And what we observed is that in this case, it's no longer the vibrational occupation number, it's the vibrational density of the state. And that means that if we want to improve, we need to bring off resonance the vibrational modes that make the dysprosium the most from the available electronic transitions. And very briefly, this is exemplified further by calculating the crystal field strength, which is a single value parameter that basically tells you how much the vibrational motion affects the center, plotted against the electronic states for each of the compounds. And hopefully what you can see here is that as you go down towards the better performing single molecule magnet, the vibrational density of the states are around the electronic transitions are more sparse. And with this, I just like to conclude, and since I'm running out of time, I'll just jump to the acknowledgements. So this work has been done during my postdoc period at the Chiltern Group at the University of Manchester, but since 3 weeks ago, I started my new position as an independent researcher at the University of the Basque Country as an Ikerbasque. So, of course, I would like to thank you for your attention and happy to take any questions.
Danielle, for your nice talk. Are there any questions? So there is a question from Carlos Bo. There's a high expectation
Yeah, there are expectations to use single molecule magnets as qubits. So to bring molecular magnetism to a further application. Do you see such applications? Yes, but the thing is, in the field of qubits, you actually don't want a single molecule magnet because you want a molecular magnet, but you don't want a single molecule magnet because that means that you would have large splittings between your states, and you actually want, for instance, the works by Wolfgang, they make use of hyperfine coupling to open up states that are close in energy, so you can operate them with radio frequencies, for instance, they're available in EPR. And if you have a single molecule magnet that have states completely isolated, you wouldn't be able to manipulate them for qubits. So yes, the qubits, it's a whole different field and it has a lot to offer, yes.
Okay.
You need more metals. I guess, not sure what you mean by that, but
Any further questions or comments?
There's one from Adrian. Is it possible to evaluate the quantum tunneling contribution in your room temperature regime? So the quantum tunneling contribution will only become important at temperatures that make any thermal contribution not important, meaning very low temperatures. So it's basically like the last resource of your system to transfer population. If your system has energy at room temperature, as your question asks, it will take a different route, a much more effective route and by effective I mean faster, to relax. So the quantum tunneling at room temperature is going to be tiny compared to the Orbach contribution. So,
any further questions? I don't see any at the moment. Okay, if not, then thanks again for a nice presentation, and we'll move on to the next talk.
Thank you very much. Thank you very much, Tanya, for very nice sharing and on time, and also allowing for discussion. Thank you very much to our speakers for wonderful talks. And I think it is time for our second poll now. So the audience would vote for an award from the 3 short talks that were presented in the session of materials. So we would like to pull up the new poll. And now you can vote your favorite talk among the 3. We will leave the poll open for 2 minutes. I see people are already responding very fast, which is great. And also would like to ask the scientific committee to cast their own votes for the Scientific Committee Award for the short talk. I see the votes are still coming in. So if you haven't voted, vote now for your favorite talk. We'll leave this open for another 30 seconds. Another 10 seconds for people who have not voted yet. And I think we have a winner. So we will announce the winners at the end of the first day. So thank you very much all for voting. Now we will go into a break, a very short break, to come back in, let's say, 5 minutes for the flash presentations in artificial intelligence in chemical research, where Hans-Peter Lüthi will be the chair. So I will let you enjoy a coffee, and we come back at 17:40 for the flash presentations in artificial intelligence in chemical research. Thank you. Okay. So I think we can start again. Maybe Hans-Peter, who is chairing the session, will start with the flash presentations. Hans-Peter?
Yeah, hello everybody. I hope you enjoyed your coffee or still enjoying your coffee. We have 4 flash presentations. It's actually a trip around the world. We start off in Tarragona, go to India, go to Florida, and then come back to Barcelona. So it's just like 30 kilometers missing to close the trip around the planet. Don't want to waste any time here. Our first flash presenter is Raúl Pérez Soto from the Institute of Chemical Research of Catalonia in Tarragona, Spain. Are you ready?
Raúl?
Raúl?
Are you here?
Hello.
Raúl, can you hear us?
Can you hear it?
I can hear you, but it seems like my microphone is not working.
No, we can hear you very well. So go ahead with your presentation.
Okay, thanks. So within machine learning, clustering falls into the unsupervised type of machine learning techniques, and it aims to group data together. Although we may not know how many groups we have in data, nor how they should be grouped properly. Nevertheless, we want our data to start looking from the chart that we have on the left side to look like the one on the right side. When we're speaking about conformational results or conformational data, each one of our data points corresponds to a specific geometry or a representation of a specific geometry of our molecule. We may want to apply this type of technique for different approaches or for different reasons, but we will always find the same questions. Which algorithm should we use? How do we choose the parameters for that algorithm? And which features should we use? Like, how do we represent the data, the conformational data that we have? And I'm sorry. So if we look a little bit into the literature, the general answer for that is, well, it depends on the data and it depends on the shape of the data that we expect. So can you please change the slide? Thanks. So we started by constructing our own validation data sets, and we selected these 2 molecules for that. And we manually label each one of the different geometries that we had for those different compounds. With that, we had our top validation data set for top molecule that corresponds to a fairly flexible macrocyclic geometry. And as you can see on the chart on the left side, it was a really difficult to cluster data set. And on the bottom side, we have a really easy to cluster data set, as you can see, which corresponds to a fairly rigid cage molecule. Then we proceeded with our data sets ready. We were able to design the study, including as many algorithms as we could, different strategies for optimizing the different parameters of those algorithms, and different ways of representing our input data and different combinations out of them. Would you please change the slide? So we ended up with this really nice looking plot, although it summarizes a lot of information here. On the top side, we got the results from the difficult to cluster data set, and in the bottom side, the easy to cluster data set. Each data point, or each point that we have here, corresponds to the best optimization criteria for each algorithm and for each set of input features. We can use this overall picture to get some useful advice for doing some clusterings, such as, for example, if we go for XYZ that we got on the rightmost part of all the charts, we can see that pure XYZ coordinates as an input feature are not necessarily good for the easy to cluster algorithm, but we can just fix that by adding the potential energy as another feature, although we can just simply change to set matrices. I would like to thank you all, and thank you for your attention, thank all the funding, and thank my group.
Yeah. Hello, can you hear me? I'm Siddharth.
Yes.
Yeah, great. Yeah, hello. My name is Siddharth Hille, and hi from India. I'll be presenting on predicting redox potential of finazine derivatives using DFT-assisted machine learning. You can go to next slide. Yeah, so I will briefly introduce the motivation behind this work. So lithium-ion batteries are quite popular these days, and they are being used everywhere. But there are certain issues associated with these batteries. So particularly environment impact, safety issues, and high cost for large-scale storage. So these are the issues. There is alternative technology that is gaining momentum these days. So that is redox flow batteries. And you can see on the right-hand side, there is a diagram. Let me quickly explain what that diagram is. So in redox flow batteries, you have catholyte tank and anolyte tank. So those are electrolytes. You don't have electrodes as in lithium-ion battery. And then these electrolytes, they circulate in these pipes, as you can see, the blue and green pipe. And there is a membrane in between, which is and electrodes are attached to those membrane. And redox reaction takes place when they come in contact together, and that is how you get power. So this particular technology is quite useful for large-scale energy storage. Unfortunately, it's not as popular. Basically because there is high cost. As you can see, you need to have tanks and all, so you can't fit them into our cell phones and all. Also, these flow batteries, they contain transition metals, so there is toxicity associated with them. Also, there is issue of corrosion. The good thing about these flow batteries are they are very good for large scale energy storage. So they are being actually used, particularly vanadium batteries are being used in renewable energy sources. And there are lots of parameters that you can tune. Particularly, they have independent control over storage and energy. So if you want to increase the capacity, you can increase the size of your tank. So that is really good property of these kinds of batteries. The thing is, if you want to make it more popular, we need low-cost material and green and efficient material. So particularly quinones, vialogens, and flavins, these organic compounds are easy to synthesize. So cost will get reduced. Also, some of them can be made green. Particularly finazine derivatives. We are investigating finazine derivatives because you can tune their properties so that you can obtain high redox potential, as well as you can make them green. So it will be environmentally friendly. So in this work, what we are trying to do, we are trying to create a model from very small data sets. As you can see, we have used 189 finazine derivatives. They were obtained from reports and DFT potential, and we have used supervised learning to make a model out of them. And you can see some of them are at the bottom. You can see 3 molecules. So these are all training sets, and in training sets, we have only one type of functional group per molecule. So you can't have like fluorine and NH2 on single molecule. So these are very simple and easy to produce data sets. You can go to next slide. Yeah. So with that simple 189 molecule data set, what we have made, we have used actually 4 different machine learning models. I have shown results for particularly 2 because these are best performing models, and we have synthesized. We have generated 3 data sets using DFT. So the left side data set is the external data set that has been compiled from reports, and you can see there are a lot of different structures, and still we are able to achieve R square of 0.77 from simple only less than 200 data points. Very simple structure. We are still able to achieve good accuracy. If you see in the middle, those are the compounds which contain different functional groups. So you can see CF3 and OH attached to a single molecule, NH2 and Cl attached to a single molecule. So these are you are attaching different functional groups to the same molecule, which is not present in the training set. And we are still able to achieve reasonable accuracy of R square 0.69 with ARDR model, which is linear model. On the right hand side, we have extended the derivatives. We have attached 3 functional groups to the finazine backbone, and we are able to achieve accuracy of 7.1 in this case. If you are wondering what is the X and Y axis scale, it is from -1 to -2.5. So with this simple data set, we are able to achieve very good accuracy. So that was the essence of this work, and it can be used for high throughput screening of molecules. Thank you.
Okay, thank you, Siddharth, and good night. I think it's midnight in India now.
Yeah, it's almost close to midnight.
Okay,
yeah,
time to go to bed.
Yeah, sure. Yeah,
our next speaker just had breakfast, Ramon.
Yeah, thank you so much. Could it be possible for me to share the slides from my laptop? I think it might be easier just for the transition.
Sorry, can you go ahead with your presentation?
Yeah, no, I was saying like if it would be possible for me to share the slide from my laptop.
We don't have time for that, so please go ahead.
Yeah, no problem. So thank you for the invitation. I'm going to be talking about the work that we are doing on extended similarity indices. So the notion of similarity is key in chemistry, since we know that similar molecules have similar properties, so it makes a lot of sense to try to understand chemical space or navigate through chemical space using similarity indices. So usually we encode the information, the structural information of a molecule as vectors of ones and zeros, which are called molecular fingerprints. And from this, we can define several similarity indices, like for instance, the Jakarta-Tanimoto index, which are really popular in cheminformatics. Next. The problem with these indices is that if we want to calculate the similarity of multiple molecules, we need to take into account all possible ways of dividing this set into pairs of molecules, which is going to scale as ON squared. So this is something that is really unfeasible because this cannot be applied to really large data sets as the one that people have been using high throughput screening and the search. Next. So hence why we propose, along with some collaborators in Hungary, to these like new extended similarity indices that allow us to compare n number of molecules in arbitrary in a single step, which essentially scales as ON. And you can see right here that the efficiency of the method allows us essentially to study chemical libraries with hundreds of billions of molecules in a really, really short amount of time. So we have applied this to the problem of chemical diversity, selecting a diverse number of molecules from a given library. And notice how our algorithm here in green allow us to recover much more diverse sets than what can be possible done with other standard algorithms. In this diversity picking problem, we have also applied our methodology to the problem of representing chemical space. That is, here you see 18 different libraries comprising over 18 million molecules, and we can easily establish the relation between all of them and see how they essentially have to study the topology of the chemical space. Also, we can extend this to the study of DNA and protein sequences. And as shown right here, we can provide further insight into the phylogenetic more conserved motifs in different families of enzymes, both comparing using the amino acid or the DNA sequence. Next. And finally, in collaboration with the Paris lab here also UF, we are applying these methods to the study of biological ensembles. So for instance, we can determine the most important structure in a molecular dynamic simulation and correlate that to the native structure of a protein. Also clustering, in which we can see that our methods essentially provide clustering that is way more robust than traditional alternatives, or we can combine all of this to study the problem of protein folding. And as you can see from a molecular dynamic simulation, we can not only distinguish the folded state and the random coil state, but also all the intermediate states contributing to the protein folding process of this system from different protein pathways. So I want to thank my group, and once again to all of you for attending and for the invitation.
Okay, thank you, Ramon. And it's not breakfast time, it's lunchtime, I guess, for you. Okay. Now we go back to Spain or Catalonia. And Ndika, are you ready?
Yes, I am.
Wonderful. Go ahead.
Okay, so yeah, good afternoon. My name is Ndika, as he said, and I will present the research that I'm currently on. Can you pass the slide, please? Yeah. So the main aim of this research is to find a potential drug candidate against pancreatic cancer by developing a tyrosine kinase inhibitor, as these tend to malfunction when this disease is present. The main challenge here is that these proteins, due to the common pathway signalings among them, they tend to develop drug resistance pretty easily. For this, we propose to develop multi-target inhibitors so we could inhibit more than one protein at the same time and reduce that drug resistant development. Exactly, we will be trying to inhibit IGF-1R and FGFR2, the ones that are in bold here in this list. Next slide, please. For this, we approached this issue by doing a structure-based drug design, which is basically using the information regarding molecular structure of compounds with known activity values against these targets, and and using these properties as features for creation of a prediction model. Yeah, in this case, in order to filter the features that we would use to make these models, we used an in-house feature selection method, which involved different typical feature selections algorithms, such as recursive feature elimination or addition, as we can see in the center of this pipeline right here. A total of 4 different models were studied: k-nearest neighbor, support vector machines, gradient boosting, and histogram-based gradient boosting, which is hyperparameters were tuned twice using a typical grid search type approach. These models were able to perform outstandingly, as we can see in this small table on the right, obtaining values of around 0.7 in the Q-square value. But is the support vector machine the one that was interesting for us? Yeah, the next, please. Using this model, we filtered an in-house combinatorial database of around 250,000 compounds in order to predict activity for against both FGFR2 and IGF-1R. Allowing us to easily see which is the structures that could be more interesting in order to study them further. Exactly, we did different studies such as molecular dynamics and MMPDSA methods, which supported our theory that these structures could be interesting, as both could or the structures that we've chosen as potential candidates were able to replicate ATP-like interaction through the time in all the molecular simulations, and also when we measured the predicted binding delta G value, we obtained very interesting values compared to reference active compounds in the market. Yeah, and right now these structures are being synthesized in the lab, so we can test them in isolated proteins. Thanks a lot for this opportunity.
Okay, thank you, Andika. We have a short break now, and then we'll go on with the short presentations in material, the flash presentations in materials.
Right. Yes, we can have a 2-minute break. Let me say that you can still ask questions in the flash presentations. You can type them in the Q&A, and then the speakers will type in their questions to your answer. Sorry, they will type in their answers to your questions. So there's still an opportunity to have some discussion. Just type in your questions in the Q&A panel, and then the speakers will answer in writing. I think we can already share the next presentation. I can introduce the next chair, Mercé Dumal. Mercé, are you here?
Yeah, I'm here.
Great. And maybe we can already have on screen the presentation for the flash presentations for materials. So Aspa, can you share your screen? And please, I will ask all of the flash presenters to have their names appropriately placed in Zoom so that we can promote you as panelists.
No. These are not the plus presentations for materials. These are the bio. This is next. This is the next one.
Yeah, this is the next one. This is biomolecular. So we want the materials.
Yeah.
Mm-hmm.
So in the meantime, just please let me remind you to not exceed your allowed time to give your flash presentations, please. Just try to keep as much as possible to the allowed time. Yeah. So shall I go ahead?
Yes, I think we can start. It's
okay. So then our first flash presenter is Yannick Schutze from the Helmholtz-Zentrum Berlin, and he will be talking. He's changed a little bit the title, so he will be talking about polymer-based lithium-sulfur batteries. Whenever you're ready, Yannick.
Yeah, I'm ready. Thanks for the introduction. So today I want to present you the latest results of our research project as a part of the priority program Polymer-Based Batteries, in which we study a new polymeric cathode material for future lithium-sulfur batteries. And in my work, I developed a multi-scale approach in order to investigate the structure of this polymer. Next slide, please. So lithium-sulfur batteries are considered one of the most promising candidates for next-generation rechargeable batteries, and this is due to their high theoretical energy density of 2,600 watt-hour per kilogram, which is more than 6 times higher than the limit of nowadays lithium-ion batteries. And furthermore, sulfur is environmental friendly and it's naturally abundant. But however, so despite the potential of lithium-sulfur batteries, there are several challenges which hinder practical application so far. And the 3 biggest obstacles are the installation of elemental sulfur, the so-called shuttle effect of dissolvable lithium polysulfide, which causes a loss of active material, and the volumetric change of sulfur during the charge and discharge process. And in order to tackle these problems, we recently proposed a strategy to construct a freestanding cathode with a conductive and flexible polymer as a sulfur host material. And here, organic monomers are first electropolymerized onto the surface of a nickel foam to form a porous polymer network. And in the second vulcanization step, elemental sulfur gets embedded into this framework by ring opening polymerization of sulfur rings and the binding sites of the polymer. And the benefits of this cathode are its high conductivity, the ability to confine polysulfides via chemical bonding, and the mechanical flexibility to cope with the volume change of sulfur. Next slide, please. So from a theoretical point of view, we were interested in the structural characterization of the charged cathode. So the sulfurized polymer as it is prepared after vulcanization. And for this, I developed a combined first principles statistical mechanics approach, where I started with a conformational space sampling and a DFT and stability analysis of differently sulfurized molecular dimers as the basic polymer unit. And I combined this with a statistical binding model to derive probability distributions. And here I looked at 2 different binding types. So the cross-linking of different polymer backbones versus the intra-chain binding, and also the distributions of sulfur chain lengths or ranks. And these results are then compared with experimental Raman spectroscopy. And to conclude, our results show that pentasulfide interchain crosslinks are the most dominant after vulcanization. And with this, I would like to end, and thank you for your attention.
Thank you very much. Thank you very much, Yannick.
Welcome.
And our next presenter will be Estefania Díaz López from Universitat Autònoma de Barcelona, and she will be talking about CO2 hydrogenation to methanol led by copper molybdenum carbene interface. So whenever you're ready, Estefania.
Thank you. Good afternoon, everyone. I'm Estefania from Autonomous University of Barcelona. And here I present the study of the production of methanol via CO2 direct hydrogenation. In the industry, the copper-based catalyst faces several challenges, such as lack of selectivity due to the occurrence of the reverse water-gas shift reaction. For that reason, we report here in collaboration with an experimental group from ETH Zurich, silica-supported copper molybdenum carbide catalyst. In fact, this catalyst showed a higher activity than the industrial catalyst, and we propose that the interface with copper delta plus sites is the site responsible of this higher activity and selectivity, where we perform DFT calculations to understand the nature of catalytic sites. And first, we focus on finding a suitable model to represent the catalyst, and then we validated the model, testing the theoretical results against the experiment. And we found, according to the vector charge analysis, as we can see in the left of the slide, the copper atom showed the most significant delta plus character after the CO absorption, with oxygen atoms surrounding it. And it also correlates to a stronger blue shift of the CO station frequency, and in agreement with the experimental results. And we also found that the hydrogen absorbs stronger in the interface, consistent with the experiments. Next, please. Once we selected the model, we studied the mechanisms, which was mostly carried out by my colleague Ana Vidal, and we found that the production of methanol occurs via the formation of the deoxymethylene from formate intermediate. And this step has the rate-limiting transition steps. It involves heterolytic cleavage in the same way that the first transition state, as we can see in the vector charge analysis, with the separation of charges. Here, the interface played a key role because the copper and the support both participate in the heterolytic cleavages of hydrogen, which are responsible of the lower energy barriers. Next slide, please. And finally, according to the competitive reaction pathway, we can see the CO is also easily obtained. So it explains the formation of both products in the experiment. And we can conclude the active site is the interface with a copper single atom with delta plus character. And thank you for your attention, and thanks to Anna and Aleix for the support and the experimental group.
Thank you very much, Estefania.
You're welcome.
Our next presenter is Kalin Shankar Bhattacharya from the Max Planck Institute for Kolem-Forschung. And the title is Structure and Reactivity of Iridium Oxide Nanoparticles for the Oxygen Evolution Reaction in Electrocatalysis and Electronic Structures Theory Study. Whenever you want.
Thank you. Good afternoon, everyone. Today, I'm going to talk about electrochemical reaction from first principle modeling, and this research was funded by Humboldt Foundation. So please, yeah. So what's our motivation to do research in electrochemistry? Because the electrochemical interface for understanding the reaction like water oxidation or CO2 reduction reaction is very important in nowadays for energy research. But from the theoretical point of view, it's very important to understand the mechanism in the atomistic level. Because in electrochemistry, the two important points, that is the role of potential and role of solution pH is important to monitor the reaction. In principle, from the theoretical calculation, most of the cases we have seen that the reaction happen I mean, the study happened in the constant number of electrons, because in DFT, the number of electrons is always fixed. But in electrochemistry, the number of electrons is changed depending on the potential. So how one can do that? So that's why we are currently interested to model, to make a new methodology to understand the electrochemical reaction. So here I just briefly mentioned that the two potential factor, that is the electrochemical potential, comes from the electron transfer, and the solution potential, that is controlled by the pH of the solution, is important to model. So can you please go to the next slide? Yeah. So based on our very fundamental knowledge on the acid-base reaction and redox reaction, we are trying to model these two important points, that is number of electron transfer and number of protonation, deprotonation during the reaction. So in the left-hand side, it's a model structure of our catalyst that is mostly amorphous. And in amorphous structure, the defect site and the local environment is very, very important. So considering the electron transfer and considering the protonation and deprotonation, we merged two important computation parameter into a computational potential pH diagram that's mostly known as a Podbe diagram. From this Podbe diagram, we can identify the stable structure at a particular potential and pH condition. So in this way, we developed our model to understand the phase structure, phase changes depending on the potential and pH. Please go to the next slide. Yeah, so this is our results that we published recently, and here we modeled two different clusters, that is the smaller iridium oxide cluster and the larger iridium oxide cluster. Depending on our potential and pH, we made the Podbe diagram, and from this Podbe diagram, we understand that at the low pH, low potential, the iridium oxide is mostly protonated. That is also observed from the experiment. And from the high potential, high pH, the structure becomes dissociated and produce a very exotic structure that's mostly dissolved in our solution. And the other point is that if we change potential and pH, the important thing that the oxidation state of the metal center also changes. That's also control the electrochemical reaction. From the reactivity part, we also observe that if we change, if we increase the potential from the low to higher potential, the most important reaction during the oxygen evolution reaction is that oxygen-oxygen coupling reaction also changes depending on potential. If we increase the potential, the barrier for forming the bond formation decreases. So from our modeling and also our methodology, we recently developed a new model for understanding the electrochemical reaction, particularly for oxygen evolution reaction. And currently we are going on other electrochemical reaction. And I'll be very happy if anyone have any questions and can send an email in my email address. Thank you, all of you.
Thank you very much, Kalin Shankar. So now we move on, and our next speaker is Manuel Kolb from Universitat de Barcelona and EuChemS, and he will be talking about the structure-sensitive scaling relations among carbon-containing species. Manuel, whenever you're ready.
Yep, thank you. So yeah, today I'm going to be talking about a combination of the last two talks. Namely, we're going to be talking about the electrochemical reduction of CO2. And in this case, we're going to be focusing on something called scaling relations, which will define the ability to optimize our catalyst. If we go to the next slide. Here you see the scaling relations, how they are defined. They describe a link between the adsorption energies of a specific molecule or a specific adsorbate. In this case, on the left panel, it's carbon, and we scale it with the adsorption energy of CHX, so CH1, CH2, CH3, which are important intermediates for the CO2 reduction towards methane. And as you can see, the adsorption, oh, sorry, this was too early. As you can see, they scale with each other. Now you can extend those those scaling relations to include different coordination numbers, and what you end up with is different parallel lines. And if you measure the offset, you see that the offset is linearly dependent on the coordination number. Now, if we go to the next slide, in our study, what we looked at was at the adsorption energy scaling for the CHX, so CH1, CH2, CH3 on 5 different coordination numbers for a range of different metal adsorbates, the results of which you can see here. And then we went on and we measured the offsets. If you go to the next slide. So the offset is quite simply, you extend the scaling line up until you meet the y-axis and just look at the cutoff. If we go to the next slide, we see our results here. What we see is that for CH2 and CH3, so for CH3 and CH2, the offset is linearly dependent on the coordination number as is expected. However, for CH versus carbon, we actually see that the offset is constant. And that means that the adsorption energy of carbon and CH is not independent of each other. We are fixed in the optimizability of the catalyst. And quite simply because we cannot improve the CH energy difference by changing the coordination number, which will limit the possibility for optimizing the catalyst going forward. Yeah, and with that, thank you for your attention. And if you have any questions, please feel free to reach out.
Thank you very much, Manuel. And our next presenter is Said Amir Jalayer from the University of Münster. And he will be talking on the cooperative interplay of molecular machines embedded in functional materials. So, Said.
Thank you. Good afternoon, everybody. Yes, we will talk about molecular machines, and because of time limitations, I will focus a little bit more on the methodology. So the general motivation in our work is to have molecular machines integrated in functional materials. And on the left, you see some kind of open structure where these kind of molecular machines are embedded. But we will focus here on the methodology to describe these mechanically interlocked molecules. As you can see in the middle, it's a ring around axis, and we want to develop methods which can be efficiently describe these kind of systems and then go to larger systems. And the approach we developed is on-the-fly training, and is a part of the PhD thesis of one of the PhD students, Elena Kolostajski. And then in the next slides, I will show you in a nutshell what we did. So we have our molecule, and if you, next please, you see that we will now focus just on the core part, which is assembled here. You see the chemical structure, and what we do, you see we separate it in 2 individual units and develop a force field for each of these, first of all. In the next slide, you will then, next please. Yes, so what we have, first of all, if you have this ring structure, which we will see, next please. Maybe you can just open the full slide, then it's easier. This ring structure has numerous conformations, so it would be very difficult to really have a initial guess for each of all the conformers which are possible. So what we do, we start with the local information, develop a force field for it, and based on this initial force field, we performed MD simulations, which then can at each the step, you can extract information, generate new reference structure, and by this you can continuously on the fly improve the force field. And we have a specific way to also use in population swapping genetic algorithms, so that each of these different points are communicating with each other. And next please. So at the end you get this non-guided on the trained force field. And next, yes, here you see the validation. So yes, here you see the validation. So you see a significant improvement comparing the on-the-fly trained, which is the gray one, compared to the red one for this highly flexible system, which has multiple minima. And in the next slide, if maybe you can also again just show the full slide. We focus now on the shuttling, and there, of course, you have now, in addition to this larger conformational states, you have a reaction coordinate, which is important for it, which is the functionality, this translational motion of the ring. And here we go towards a guided on the flight trained force field, where we really go stepwise along this reaction coordinate and train subsequently our force field. And by this, putting everything together, you can really analyze. Here is the free energy topology shown now, calculated. We can go now to extended length scales and time scales, and have in addition this atomistic picture, which is experimentally not possible to observe. And of course, you can now go to more complex systems, more complex architectures, which I could unfortunately not describe here, but I would be happy to answer any questions. And of course, anybody who is interested in the methodology, which is not just for molecular machines, but you can also use it for other highly dynamic systems. Thank you.
Okay, thank you very much, Said. And we will have our last speaker for these flash presentations on materials, Jordi Poitet from Universitat de Barcelona, and he will be talking on non-covalent interactions between boron clusters and aromatic rings and its applications. Jordi, when you're ready.
Yes. Thanks a lot, Marcel. So having in mind that non-covalent interactions involving multi-center, multi-electron skeletons such as boron clusters are not common. Next, please. In this study, we are going to focus on a new non-covalent interaction between nidocarborine and pi systems that has been both experimentally discovered in intramolecular and intermolecular modes and quantum chemically proven. This new non-covalent interaction is discovered based on the nido cluster, but importantly, it's not the interaction between the open 5-member ring that it was considered the most aromatic, but it's not, because the strongest diatropic ring is just in the middle of the cluster. So we are talking about a whole entity, a whole aromatic 3D species and different aromatic species. On the left, you can see that the X-ray diffraction studies indicate that this needle cage pi bonding presents parallel displays or T-shape geometries depending on the different aromatic systems. In the center, the quantum chemical calculations show that these needle cage bonds share similar characteristics to an ion pi or pi-pi bonds that are found in classical aromatic like the benzene dimer. It's also important that the most important contribution is the electrostatic one, as we can see from the energy decomposition analysis, but also the orbital interaction as well as the dispersion components are important. Next, please. So as we can see here, the frontier orbitals are very, very similar to the classic compounds. Here we can see the energy composition analysis with more detail. As well, on the right, we can observe these non-covalent interactions present between the two entities, the aromatic system as well as the 3D aromatic species. But also important, this needle cage pi bonding interaction induces variable photophysical properties such as aggregation-induced emission or aggregation-caused quenching in just one molecule. So we hope overall that this work allows a better understanding towards a boron cluster-based non-covalent bond, and let's hope that it opens the door to next synthesis regarding this non-covalent interaction. So thank you very much for your attention. Thanks, Marcel.
Thanks. Thanks to all of you for your very interesting flash presentations and for keeping in time so well. So thank you very much to all of you. Thanks. Zoe?
Hans-Peter, will you introduce the next chair? Or I don't know if Hans-Peter can hear us. Maybe Radu, are you here?
Yeah.
So Radu will be our next chair. Radu, maybe you want to introduce yourself and the session?
All right, thank you. My name is Radu Dimitrescu. I'm from the Babeș University in Romania, and I'm going to host our session on biomolecular systems, and I should probably, yes, share my screen and presentations for our presenters. It should work, yes. Are they ready? They are a bit ahead of time. The first speaker is going to be Cristian Privat from the University of Barcelona in Spain.
Christian, can you hear us?
Yes.
Please go ahead.
Okay. Thanks for the introduction, Radu. Today I present this flash talk about deciphering constant pH molecular dynamics in short peptides. This work was done in collaboration with Sergio Madurga, Francesc Mas, and Jaime Rubio from the University of Barcelona. Next slide, please. First of all, I should talk about constant pH molecular dynamics, which is an approach that includes the effect of pH in the molecular dynamic simulations by allowing the change of the protonation state of the treatable groups during the simulation. For instance, Amber software implements this approach by defining these ghost hydrogen atoms that we can see in the picture in the treatable groups and activate them by assigning their charge when a new protonation state is accepted. I think that this technique is very promising for the study of the effect of pH on biochemical systems. However, after our first contact, with this approach, we detected an inconsistency in its implementation. This inconsistency is that the charge of the side chain atom changed during the simulation, but not the partial charge of the backbone atoms. So as we really think that this method is very interesting, we decided to carry out an in-depth study using this peptide, which consists of these two aspartic acids and capping groups at the extremes. And we performed constant pH molecular dynamic simulations and also conventional molecular dynamic simulations to compare the conformational properties of this peptide when the different methods are used. Unfortunately, the results show that the fully deprotonated system were not in agreement when both methods were compared. One example of this conformational analysis are these Ramachandran maps of the deprotonated peptide in the right. The two plots at the top correspond to the conventional molecular dynamics simulations, while the two in the bottom to the constant pH molecular dynamics. If you compare them vertically, we can observe how some regions of these Ramachandran maps disappear when we go from conventional to constant pH molecular dynamics, which is quite concerning. For that reason, we decided to extend the study to provide more information about this issue. Next slide. Yeah, thank you. Thus, we compare again the methods, but this time with a larger peptide consisting of this chain of alanine amino acids with two aspartic acids in distinct positions. The first in the left has close aspartic amino acids in the middle, and the second one in the right has separated aspartics in the extremes of the chain. So we carry out again extensive simulations and analyzed the conformational space with these energy maps based on principal components that we have at the top of the slide. In this case, we only illustrate the situation of the peptide with the protonated aspartic acids. And if you look at them, you will observe that differences are only significant when the aspartic acids are close, which corresponds to the two energy maps at the right of these four maps. So to quantify these differences, we illustrate the trajectory with this two-dimensional root mean square deviation graph. We observe that the values of this deviation are very high for a normal root mean square deviation value. So this is not very encouraging because it says that there is not a structural similarity between the representative of the clusters of each simulation. And on the other hand, if we go to the distribution of the radius of gyration in the second graph, we observe that most of the systems share similar distributions, except for the case of the fully deprotonated peptide in constant pH molecular dynamics, which is stand out with this peak. So, but finally, in the basis of the observations, we conclude the implementation of constant pH in amber should be carefully used. We strongly recommend using it together with experimental data in order to validate the simulations, especially when the protonated states are dominant. Thank you.
Thank you very much. Our next presentation is going to be from Giacomo Salvadori from the University of Pisa in Italy on the photoactivation of a bacterial phytochrome through a QMMM surface hopping approach. Giacomo, are you ready to hop?
Yes, do you hear me?
Yes, we do.
Okay, so I'm Giacomo Salvadori. I'm a PhD student at University of Pisa under the supervision of Professor Giovanni Granucci and Professor Benedetta Mennucci. In this brief contribution, I'm going to show you how we have investigated the photochemical process, in particular the role of the environment of the Enococcus ratidurans bacteriophytochrome. Switch, please. So in this phytochrome, the resting state absorbs red light, the PR state, while the activated state absorbs far red light, the PFR state. The photoconversion is initiated by the light absorption of the chromophore that induce a zeta-2e photoisomerization, and the new contacts within the protein binding pocket trigger a cascade of events which lead to the opening and into the biological activation of the protein. The structures of the possible intermediates are still unknown, as well as the sense of rotation of the chromophore. So we have employed the surface hopping method, where the biliverdin chromophore in green was treated as a EuChemS subsystem, while the MM subsystem was restricted to a single monomer and a sphere of water molecules. This method showed the presence of a conical intersection between the ground state and the first excited state as a non-radiative decay channel, achieved as a result of a Nulla twist mechanism. So a space-saving way to isomerize inside a tight binding pocket. All our simulations have shown the same route as the reaction path, arriving at a structure that could be the first reaction intermediate. Please, could you, thanks. In particular, the process is characterized by a counterclockwise rotation of this dihedral associated to a clockwise rotation in the dihedral adjacent. Once on the ground state, the hydrogen bond with tyrosine is formed. There is a large variability in the excited state lifetimes due to the environment. And I think there is a problem with the slide. No, okay. And so the variability in the excited state lifetimes is due to the environment. In fact, in the figure, we have in gray an example of long-lived trajectory, while in cyan a short-lived trajectory. The carbonyl hydrogen bonded to an histidine residue, and the steric size given by the amino acidic residues that make up the protein pocket hinder the rotation of the ring, lengthening the excited state lifetime. Thank you for your attention, and if you are interested in the topic, please feel free to contact me.
Thank you. Let's go to the next presentation then. It will be on a dynamic view on receptor-ligand interactions from Professor Marcel Bermudez at the Münster University in Germany.
Hello and good evening, everybody. I hope you can hear me.
Yes, we do.
Yeah, today I want to talk not about a specific result, but more on a general approach to include receptor dynamics to understand the complex pharmacology. And we are typically focusing on G protein coupled receptors, and which you can see here as one example, is the kappa opioid receptor. And we want to understand how one ligand can address several pathways, and therefore we have to include receptor dynamics. We typically work with pharmacophore models, and you know from pharmacophore models, and please go to the next slide, that they are very powerful to explain things and also to virtually screen large libraries, but it also comes with two shortcomings. First of all, they don't represent a dynamic view, they represent a static conformational state. And the second is that we are restricted to certain geometries for the representation of pharmacophores. And we want to cope with these two shortcomings by introducing dynamic pharmacophores, which we call dynophores. And the workflows as follow. We have a MD simulation with several frames. And for every single frame of the MD trajectory, we calculate a static 3D pharmacophore in an automated way. And also in a fully automated way, these pharmacophore models are then grouped together and we build up a dynamic pharmacophore. And this looks like that. This example here is pilocarpine, partial agonist for muscarinic receptors. And you see here the frequency occupancy in the, during the MD simulation for these different features. So this is a positive charge, hydrogen bond acceptor, lipophilic contact. You see here that we can also look at the percentages, but also look at the space representation. And we can also look at the feature occurrence in time. On the next slide, you see that we can also analyze these individual features in a more specific way. When we just look at the lipophilic contact, we see two clusters. The upper cluster, which you can see here in the upper part, and the cluster below. And when you look at the interaction partners of the protein side, you can also monitor over time when this interaction occurs. And here you see a shift in the binding mode after 1/3 of the MD simulation, and then it shifts back from one to the other cluster. So this is something you can monitor with dynamic pharmacophores. And we think that this is a very broadly applicable approach, and that dynamic pharmacophores have a huge potential for various applications, not only in understanding receptor functions, but also to enhance virtual screening. Thank you.
Thank you. Our next presentation then will be from Oksana Aspitarte from the Universidad del País Vasco in Spain on FMN containing mini singlet oxygen generators. Are we ready?
Oksana, can you hear us?
Yes, hello.
All right, please.
Okay, in this work, a structural and conformational study of flavin mononucleotide containing minisoc has been carried out. First of all, why are we interested in this kind of systems? Because in recent experimental studies, it has been demonstrated that under lighting radiation and epoxy conditions, the excited flavin takes 2 electrons from the surrounding and donate them to the platinum-4 prodrug, converting them into the active platinum-2 anti-cancer drug by oxidizing itself. Furthermore, not only flavins, but also flavoproteins do the job. And we have proven that the catalytic activity can be modulated by the selected mutations. In particular, we have altered the position 103 at the binding pocket and the position 50 at outside of the flavoprotein. And we have seen that the catalytic activity is greater for Q103V mutation and smaller for the Q50W mutation. So by using molecular dynamic simulations, we have tried to understand this. The next slide, please. So in the active binding site, we have observed that the main difference among the three systems is related to the glutamine 103 residue. In Q103, 103V mutation, sorry, this residue is not present. And in wild type, the interaction is weaker than in Q50W mutation. So this behavior has the opposite tendency to the catalytic activity, which seems that the degree of glutamine 103 interaction quenches the catalytic activity. The next slide, please. On the other hand, regarding to the entrance channel, we have observed that it remains open most of the simulation in the case of the Q50W mutation, contrary to the wild type and Q103V mutation. However, the access of the charged species to the active site, it is observed to be hindered in Q50W system, which would implicate a difficulty of the moment to access to the active site. And that's all.
All right, thank you very much. And with that, I think we can move to the next presentation from Liadis Mora Lagares at the Theory Department, Laboratory of Chemoinformatics, National Institute of Chemistry in Ljubljana, Slovenia, talking to us about structure-function relationships in the human P glycoprotein insights from molecular dynamics simulations.
Good afternoon, everybody. My study is focused on the P glycoprotein, or PGP for short, which is a very important target in drug development and toxicity assessment because it's a membrane transporter. More specifically, it's an efflux pump responsible for the elimination of many substances from the cells, and as a consequence, it is involved in the pharmaco and toxicokinetic properties of drug or drug candidates. It is also involved in drug-drug interactions and in multi-drug resistance. That is considered the main reason for the failure of cancer therapies. Next, please. Next. So we perform molecular dynamic simulations to investigate the effects that binding of different compounds would have on the conformational dynamics of the PGP and how these changes can be correlated to the transport mechanism that consists in a big conformational change of the protein that goes from an inward-facing conformation, which is the conformation we have in the slide, when it's open to the cytoplasm, to an outward-facing conformation when it's open to the extracellular phase. And all this process is coupled with ATP binding and hydrolysis. That occurs at the nucleotide binding domains that are the ones that are down in the picture at the cytoplasm place. And these nucleotide binding domains, they dimerize in order to bind the nucleotide. So the simulations were performed using the cryo-EM structure of the human PGP and a set of 9 compounds, including active compounds like substrates or inhibitors of PGP and inactive compounds. The starting poses that we used for the simulations were obtained from a previous docking study. So we ran 500 nanoseconds of simulation time, and related to the ligand-protein interactions, we observed simultaneous interactions of 4 residues. These are the ones highlighted with yellow color in the picture, in all the active compounds and none of the inactive ones. We also observed simultaneous interactions with residues highlighted in pink and green color in the picture in at least 3 of the active compounds and none of the inactive ones. But one of our more interesting findings is related to the mode of motion undergone by the PGP during the simulation time, because we observe patterns that can be correlated with the initial conformational changes that lead to the activation of the translocation mechanism. For example, next please. The largest deviations in the protein structure occur in the nucleotide binding domains region. And these variations were more marked in the active systems. Next, please. Here in these distance distribution curves, we can easily detect narrower curves for the non-active systems that suggest a more limited conformational flexibility for this set of compounds when this set of compounds were placed in the binding pocket of the protein. So thanks for your attention.
Thank you. And for our next presentation, Jose Canetti from the Institute of Organic Chemistry with Center of Phytochemistry in Sofia, Bulgaria, is going to tell us about computations on guanine quadruplexes and their heterocyclic adducts.
Jose, can you hear us? Are you there?
Moment. Do you hear me now?
Yes, we do.
Guanine quadruplexes occur in nucleic acids which form quadruple-stranded structures. And on the left, you see a 3D NMR structure of a telomeric quadruplex, where the gray ribbons are the sugar phosphate chains, and guanines are the purple plain structures within the sugar phosphate strands. This structure, which contains for different quadruplexes, it may contain between 8 and 1200 atoms, and it is incomputable. And for our computational purposes, we stripped off all sugars and phosphates. As the results, we obtained this structure on the right, which we call the naked quadruplex, which contains 3 planes of guanine quartets and several potassium, or possibly also sodium ions, which stabilized the 3D structure. This structure is very stable, and it can be produced by any type of guanine-rich nucleic acids, and it has been observed in all organisms, including protozoa and also up to human structures. On the next slide please, you see what is our computational protocol. The naked structure, which we produced by stripping the carbohydrate and phosphates, contains some relatively little number of atoms, from 190 up to 250 atoms, and it has the stylized view which you see on the picture. Computationally, this takes quite a lot of time on our old supercomputer, but what we do in order to obtain useful usefully accurate results is first to optimize the structure by DFT calculations, and then
Jose, I think you have another 30 seconds if you could close
yeah,
this.
we get correlated calculations on the optimized DFT structures, and these results from both DFT and correlated calculations also correlate with experimental biological effects of complexes of G quadruplexes. On the next slide, you will see what is our outlook. G4 dependent processes, they are very, very many in cells, but also as molecular mechanisms allow us to produce affinities of prospective drugs or any heterocycles to quadruplexes, and thus we can study the regulation and control of biochemical processes. Thank you.
All right, and thank you very much. For our next presentation, we're going to see a theoretical study of...
Much, everyone. This was a wonderful flash talk. Thank you, Radu, so much for chairing this session on biomolecular systems. Thank you to all flash presenters. This was fantastic. Thank you to all speakers of this first day. Thank you to all participants for attending and listening to the presentations and asking very nice questions. The Q&A is still open. If someone wants to ask, there is one Q&A which is open, ready to be answered by the flash presenter. And I would now pass on to Hans-Peter to present, and Tanya van Murik to present the awards.
Right, thank you. So, well, first I have to apologize to Radu. You were ahead of schedule and I went to the coffee machine and then missed to introduce him. Even spent an effort to pronounce your university properly. But anyway, it's, how to say, lost labor's lost, or how do the Brits say? Anyway, the awards. We had two complete sessions, the artificial intelligence in chemical research and the materials session. Tanya will present the winners of the materials session, and I have the pleasure to announce the winners of the artificial intelligence in chemical research session. For the popular vote, the audience, we had 113 responses or votes cast, and the winner is Theodoros Gaumans, who got 41% of the votes. Sorry, Yes,
that's correct. Mm-hmm.
That is correct, right? And but that's the winner of the scientific committee. Actually, I think the day was too long for me.
You're right. Yes, that's the winner of the scientific committee.
It's the winner of the scientific committee, right? I'm sorry, and the winner of the popular vote is Alexios Chatsiogoulas. He won the popular vote, or the vote of the audience. And now it's your turn, Tanya. I hope you'll be doing better than I.
So, the award for the materials session for today. The audience award goes to Adriana Pietropaulo. And the scientific committee award goes to Danielle Reta. So many congratulations to both of you.
Congratulations, really, congratulations for excellent presentations. We will be sending you the certificate of award. We will be sending this by email.
Thank you.
So again, congratulations to everybody. Thank you for participating in this first day. Thank you for staying so late. And we are looking forward to have you tomorrow with us. 2 p.m. CET, we will start again the conference. So thanks again. We close this first day on time, perfectly. Thank you so much to everyone again. And bye-bye.
Bye, and see you tomorrow.
Thank you. Bye.
Bye. See you tomorrow.
Okay, hello everybody. I'm Hans-Peter Lüthi, co-chair of this Computational Theoretical Chemistry meeting online together with Zoe Gurnia of Athens. We have quite a few new participants who registered, and I would like to go through the introduction again, the introduction we presented yesterday. Next slide. Well, there's a bit of a history. Originally, we planned to hold this meeting, the 13th European Conference on Computational and Theoretical Chemistry in Thessaloniki in Greece in September of this year. And, you know, for obvious reasons, we had to postpone to 2023. But instead, sort of last minute, we decided to have an online meeting, at least, you know, to cater to our community and to keep things alive. So, of course, you know, we hope to see you in Chalkidiki near Thessaloniki. It's the red spot there in the bay. There is Thessaloniki nearby, and the red spot is this resort area not far from the town of Thessaloniki. So we hope to see you there, of course. And but first, just a few words about today. You all noticed that the registration for this conference is free. And the one issue here is with the, you know, we have your email addresses, and we promise that we'll use your email addresses only for matter regarding this or the Thessaloniki meeting. It won't be given away to anybody. It will stay within our boundaries, just for you to make sure that this will work this way. Then, of course, without sponsors, you know, we wouldn't have a living. We're supported by IBM Research Europe, by the Journal of Chemical Information and Modeling. Zoe is an editor of, and by Sanofi, who will be presented by the next keynote address. The host, in a way, the Thessaloniki, if you like, is the Hungarian Chemical Society. Petr Salai, who's the head of the division, he will say a few words also about the society, I guess, and certainly about the division organizing this meeting. The organizing committee, this is these 10 wonderful, beautiful people here. They did most of the work. There's some behind the curtains, of course, people of the Hungarian society who got the whole thing going, certainly the web pages and the like. The schedule today, we have two sessions. We have the session on biomolecular systems, and chaired by Zoe later. And then we have the electronic structure theory or electronic structure session chaired by Evelina later this afternoon. We also, given the enormous return we had on return of abstracts, on return on our call for contributions, well, we decided that we have to give the, you know, in particular the young, the young people and a platform, and we introduced these flash presentations. They will have 3 minutes, you know, to present themselves and their research. so that is something we actually didn't plan before. Initially, we thought we would, we would close at 5 o'clock, but now you have to wait a little bit longer till you can, celebrate Friday evening, Friday night. Well, I mentioned that we have, quite a few registrations, more than we ever dreaming of. You see the, the split in countries. You also see the gender balance, which is quite balanced, which makes us happy too. But you see, pretty much all European countries are present with attendees. And the next slide will show the the speakers. Also there, we stretch from Russia. I think Portugal is missing, but we stretch from Russia to Spain at least, east, west. Portugal's there. Sorry. Okay. Thank you. We also have an award program, and the award program sort of is two tracks. One track is the scientific committee. They will decide on who did best. And then we also have a popular vote. I mean, you will be invited after the session, you'll be invited to vote for your favorite speaker of that session. The results will then be communicated at the end of the day. There's a code of conduct. Of course, in very short, you have to behave, otherwise we press the red button. The webinar is actually being recorded. All presentations will be recorded, except those where the authors preferred not to be, archived. There's another hint in the next slide, which is quite important for the communication as we're going along. Could you show me the slide with the Q&A? Sorry, I'm ahead of you. If you want to have a question, pose a question, use the Q&A. Yeah, here it is. If you want to ask the speaker a question, then use the Q&A channel. If you need help, or if you want to, well, we don't advertise this, but if you wanted to reach somebody else in private, then use the chat function. That's quite important. So again, Q&A is for your questions to the speaker. This is important. And the presenters, of course, have two ways to go. Questions will be selected, but your questions will be archived, and the presenters can respond after their presentation. Then, of course, speaker advice to the speakers. Please remain muted when you're not presenting. Flash presenters will be promoted for their presentation to a panelist, i.e. a speaker, so they can give their presentation. The slides they will be showing, they will be operated out of the office here. And then, very important as usual, and I'm probably the first violator, yes, I am, the allocated time. The program is extremely tight, and we wish to have coffee breaks in between. And so please watch the time. The session chairs will be, rough and tough with you if you exceed your time. Then, of course, advertise this event or this series of conferences, or the division as such. It's wonderful to see that we have 400+ contributions. The conference of the division of chemical theory and computation is growing. This is a wonderful, how to say, this is a wonderful fact. And we'd like to, we'd like to cater to this further. So this community is growing, is establishing itself. This is wonderful to see. And we have yet other plans I can't disclose now because I'm in overtime already, but we'll be back with you. So that's all I wish to say. And I'd like to hand over to Peter, the president of the division. Peter Salai, the screen is yours. Thank you very much.
Good afternoon to everyone. I hope you can see my screen. Welcome in the name of the Europe of the Computational and Theoretical Chemistry Division of the European Chemical Society. I am the chair of this division. And in the couple of minutes I have, I would like you to inform about the society which is behind this conference. So probably most of you are aware that there are chemical societies in your countries, and these chemical societies have an umbrella organization which is called the European Chemical Society, formed by 50 national chemical societies and other chemistry-related organizations from 33 countries. The aim is to nurture a platform for scientific discussion and provide a single unbiased European voice in key policy issues. The professional work is done in 19 so-called professional networks, and one of these is the Division of Computational and Theoretical Chemistry. We organized this conference. Our division was founded in 1988 by Fernando Bernardi. You know his name probably from the Boyce Bernardi correction, but he has much more than this. He contributed a lot to computational chemistry. Presently, we have representative of 31 national societies from 29 countries in the division. So you see, if you remember the previous number, we just have 2 members of EuChemS, which doesn't have a representative in our division. So we really cover whole Europe. The main task we do is we would like to encourage communication and cooperation within the field. The European Master on Theoretical Chemistry and Computational Modeling. It is now an independent project, but the first steps have been done in our division. We also promoting the European Open Science Cloud, and if I informed correctly, then Zoe will talk about this European undertaken a little bit more. And that there is the series of conferences which was already mentioned. We had already 12 of these conferences. We have it in every 2 years, and actually the rhythm is quite tight, because at every in the between years we have the conference of the whole European whole EuChemS. So this was the reason why we had to postpone by 2 years, and we saw that our field cannot stay without this conference for 4 years. So that's why we have this online conference, which seems to be but it seems that it was a good idea to do because of the large number of interested persons. So with this, actually, I finished this introduction, and I wish you a useful and enjoyable conference this afternoon. Thank you.
Thank you very much, Peter, for the very nice introduction to the European Chemical Society and to our division. And with that, I would immediately like Keta Palionchiou, I'm sorry, I don't pronounce the name, but Palionchiova from the Czech Advanced Technology and Research Institute of the Czech Republic. And the title of her talk, if you can share your screen, the title of your talk is Lipids in SARS-CoV-2 Vaccines, from Membrane Structure to Interaction with mRNA Fragments.
Okay, thank you for the opportunity to speak here. And I will guide you from the membrane structure to how the lipids interact with mRNA fragments. So first of all, the messenger RNA-based medicine is currently in our focus, not only because it's so interesting currently due to the 2 vaccines that are available, but it's been studied because of its possibilities in cancer therapy. Effectively, this is a tool how to deliver proteins into cells. We just do not deliver directly the proteins, but we code them into messenger RNA, and then we send the messenger RNA to our cells. But the RNA molecule generally is a very fragile molecule, and it cannot cross the membranes by itself because it's quite large and it's polyanionic. So far, the best way how to deliver it into cells is to encapsulate it into lipid nanoparticles that should look something like that. And if these lipids nanoparticles go into the cell, they usually go via endocytosis, and then they are encapsulated in the endosome. And during the endosome maturation, there is a drop in the pH, and the RNA is released into the cell. And the drop in the pH is pretty important because current mRNA vaccines are 2 made by companies Moderna and Pfizer, and both of them are based on ionizable lipids. These are these 2 lipids. So these can be ionized at that nitrogen, so they can get a proton there and have a positive charge at low pH. Apart from these ionizable lipids, the lipid mixtures have a pegylated lipid that has a long polyethylene glycol chain that is supposed to be on the surface of the nanoparticle, and then they are composed of 2 natural lipids as cholesterol and 1 of the phosphatidylcholine. And generally, when we study lipids in the simulations, we usually study them in the form of lipid bilayers. These are just small patches of 2 lipid leaflets, and in our bodies, they are usually in various phases. Two most common phases are liquid disordered, which means that the lipids can diffuse freely within the layer quite quickly, and they are disordered, which means that their tails are oriented in various ways. On the other hand, the liquid ordered phase, which is usually rich in cholesterol, is still composed of lipids that diffuse very quickly. But in this phase, the lipids have all their tails oriented more or less in the same direction. So these 2 phases are the most common ones. This one is more for skin or something similar. So in these cases, so we will focus on modeling something like that. So we took our ionizable lipids and we wanted to study what are their properties, how they behave, and how they affect the lipid phase. So first, we used them for building bilayers. We built bilayers of both ionizable lipids in the charged and in uncharged form. As you can see, when we compare it to a regular phosphatidylcholine membrane, the bilayers made of the charged ionizable lipids are much thinner, and they are really very, very disordered. When we look at the lipids that are deprotonated, so uncharged, these do not keep the bilayer at all, and they make something like a bulk phase. And we can explain that, let's say simply by geometry, because in case of phosphatidylcholine, we have lipid with quite a large head and two lipid tails. So the shape of the molecule is cylindrical. But in the case of ionizable lipids, the shape of the molecule is conical because we have small lipid head groups and 3 or 4 lipid tails, which make then really the molecular shape something like that. And if the lipids are charged, then the head groups repel from each other. So therefore, the size of the head group is effectively a little bit larger. So then if we try to make a layer of these lipids, in the case of a cylindrical molecule, this is pretty easy. But in the case of these charged, of these ionizable lipids, either in charged or uncharged form, we can see that we have huge gaps in the head group region. This can be either filled with water or we can just go to a disrupted structure, which in the end was the result of both unionized forms of these lipids. So when we knew how the pure lipid membrane behaved, we added other components of the system. So we had here 4-component lipid mixtures. In the case of charged membranes, which were these two, we had quite stable bilayers. In the case of uncharged systems, we saw a phase separation, especially for the case of the mixture used by Pfizer, where we really saw that we have parts that the ionizable lipids here in yellow just started to separate from other lipids, and they make really a separate bulk phase. So even in the form of 4-component bilayers, in the unionized form, these were not stable in the shape of a bilayer. We can conclude for the bilayers that the uncharged form is not stable at all, but in the charged form, we see that the lipids used by Moderna are a bit more stable and a bit more ordered than the lipids used by Pfizer. And we can explain it quite easily based on the molecular structure. Because when you look here at this lipid, which is the one that is used by Pfizer in Comirnaty, it has 4 lipid tails, 4 very short tails, and none of these tails is able to stabilize the membrane. But on the other hand, Moderna has just 1 long lipid tail here and 2 short here. And this long lipid tail behaves in the same way as normal regular phospholipids that usually make bilayers. So this long tail is probably the thing that is stabilizing the whole structure. So we were quite aware that the bilayer doesn't have to be the best way how to model these membranes because they may not be in the bilayer at all. So we did self-assembly simulations, which means that we just threw lipids into the system and we let them go in the shape in which they wanted to go, which, as you can see here, is definitely not a bilayer. Well, usually it is not a bilayer. So we ended up in 4 cases, let's say. 2 which were not that common was the case of an intact bilayer or a porous bilayer, which you can imagine just as a normal bilayer with a hole. But much more often we saw cubic phases, which was a phase which is connected in all 3 dimensions. And we also observed nanodisks, which you can imagine as lipid clusters that are solvated in water. We also saw that the lipid mixtures do not behave as homogeneous mixtures. In both cases, we saw that the ionizable lipids separate from the other lipids that are in the system. And they concentrate at the places with high curvature, which means at the edges of pores, here in the bridges of the cubic phases, or they were quite often at the edges of the nanodisks. And when we added the RNA molecule, we observed that the RNA molecule interacts preferentially with the ionizable lipids. When we looked at the surface of the RNA that interacts with lipids, on average, in the cases which we simulated, we had more than 80% of interactions with lipids made by the ionizable lipids, which is much more than what would be if the lipids would be just randomly distributed in the system. We can understand that it is quite natural because naturally the sugar phosphate backbone of RNA is negatively charged, and the ionizable lipids here are positively charged. So therefore, there are electrostatic interactions that quite easily explain that. When we analyze the structure of our RNA fragment, we saw that it behaves more or less similarly to what it behaves in water. So it is quite stable in global point of view. But when we looked at it locally, we saw that some fluctuations which we observed in water were not observed in lipids. So when there was a mass of lipids, naturally some residues could not flip or could not be flexible. So that was the thing which we just this week published in Journal of Physical Chemistry Letters. And now we are in a state where we think what to do next, where to focus next. And we would like to describe what happens with the lipid nanoparticle during the whole production process. So in the production process, you start from acidic pH, go to neutral pH, and then go back to the acidic pH. So we used our structures which we have from the ionized form of lipids, which are really rich in their 3-dimensional structure, and we deprotonated them. This is kind of hard to describe in some metrics, what change we see. We see that here the structure was very rich, full of thin bridges made of lipids. When we deprotonate them, the structure is much less rich, but here we lack the large scale resolution. So therefore, we decided to go to coarse grain resolution, where so far we do not have a model of RNA. So far we focus only on lipids. And here, if we have at the beginning something like a lipid droplet or lipid nanoparticle, and simulate it in the neutral conditions without any charge, the droplet is stable. But if we simulate it in acidic conditions, which means with a positive charge, we can see that the droplet gets distorted. The water goes inside and make water bubbles inside the lipid droplet, and then we have there something like a lipid nanoparticle with several water bubbles inside. So this really supports the hypothesis that when you decrease the pH, there will be a massive change in the interior structure of the lipid nanoparticle, which will support the releasing of RNA in the cell. And that is something that we are working on now. So the final results will be sometimes later. And so from me, basically, that's now all. I would just like to conclude that what we saw in the case of ionizable lipids is that they really behave in a very different way than what regular lipids in our bodies behave. They are very disordered and they are not stable when they are not charged. They make a bulk phase. The ionizable lipids separate from other components in the lipid mixture, and the part that is rich in ionizable lipids is the one that is actually interacting with RNA. And that's all from me. So thank you for your attention.
Thank you very much, Marketa. Brilliant talk. I really enjoyed it. So can you tell us which vaccine is best for RNA release, in your opinion?
Well, I think that this is something that the simulations cannot yet fully say, because we can say that the Moderna lipid mixture is more stable than the Pfizer lipid mixture, which could rely to the fact that the Moderna requires less strict temperatures for storing than the Pfizer. But we cannot fully say that it is better or not, because you have to quite carefully balance whether your nanoparticle is stable enough and protects the RNA well enough, and whether it's unstable enough really to release the RNA in the cell. And this is something which I think that in current state of the art, the computer simulations cannot fully describe.
Okay, there's a question in the Q&A. Ionic strength and more specifically interaction with counter ions might be expected to have a notable influence on lipid organization with ionized lipids. Did you explore this?
Excuse me, once again, please.
You can find the question in the Q&A if you wanted to check it on your own.
Yeah, I will try.
Here, the question relates to ionic strength.
Okay.
And whether your ionic strength is influencing your results and whether you have checked it.
Well, actually, we haven't really checked it. We have ions we have ions to neutralize the ionizable lipids. So quite a large ionic strength in the simulations. So well, the answer is that we have not really checked it, and it's a good suggestion to check it now.
And I have another question regarding the self-assembly, because we know that the self-assembly of lipids is in the microsecond time scale, but you showed us results from 500 nanoseconds. How are you confident that these results relate to realistic conditions?
Well, I think that more problematic in this case is the size of the system. We didn't do a single simulation. We did 6 simulations for each of the systems. So from that, we are quite confident that what we saw in the time scale which we had was something that was reliable, because the results were pretty much similar. So I am more concerned about the size which you can have in atomistic resolution, where the periodic boundary conditions could affect it.
Yes.
So we didn't want to conclude that exactly that size of lipid nanodisk or exactly that size of cubic phase is the thing that you would see in the lipid nanoparticle. The conclusion about which I'm quite confident is that It's definitely not a vesicle. It's definitely not something like a bilayer, but it's pretty much disrupted phase.
So you are continuing with coarse grain simulations in this regard, I guess?
Yeah.
Yeah, I think that's the way to go here. Excellent. Thank you so much. Very nice presentation. With that, I would like to move on to our next speaker, Birgit Strodel from Forschungszentrum Jülich, who will present the effects of in vivo conditions on peptide aggregation, computational approaches.
Okay, thank you. Can you see my slides?
Yes, we can see. We can hear you very well.
Okay, thank you. Yeah, thanks for for giving me the opportunity to present my work here at this conference. And the talks I already listened to, they are very exciting. Okay, so the title was already set. So the topic of my work is that I present here is a bit different than the other topic, the topics of the other talks. So and in my group, we spend a large amount of time and work on the aggregation of peptides, and one peptide is in particular, that's the amyloid beta peptide, which plays a role in the development of Alzheimer's disease. So the amyloid beta peptide, it's being produced from the transmembrane amyloid precursor protein, which sits in the membranes of the neurons. And by the action of two enzymes, two secretases, it's being cut, and then usually it goes into the extracellular space where it is cleared from the brain. But when it comes to the disease, it's the clearing mechanism is somehow disturbed, and the peptide starts aggregating. First, oligomers are formed, which grow into fibrils, and these fibrils, they also lump together, forming these so-called plaques, which were already discovered by Alois Alzheimer more than 100 years ago. In my work, we focus on the smaller oligomers. First of all, it's easier to tackle the emergence of oligomers by molecular simulations than if we wanted to see fibril formation. And second, and this is the more important aspect, it's now known that the oligomers are far more toxic than the fibrils. So with the fibrils, it's not even clear whether they're toxic at all, but the oligomers, they are toxic. So, and the tools, what we are using, it's mainly molecular dynamic simulations. Here you can see such a typical simulation where we placed 20 of these peptides in a simulations box and we let them aggregate. So that's one kind of simulations what we perform. And of course, by doing so, we produce a lot of data which needs to be analyzed. And for the analysis, we use different tools, for instance, Markov state models. So if here you can see the Markov state models for the monomeric peptide. So this is not about aggregation. Here we really focused a lot of the monomeric amyloid beta peptide. A beta 40 means it has 40 amino acids. That's something I forgot to mention. The peptide comes in various lengths. The most common lengths are 40 amino acids or 42 amino acids. 40 is the most prevalent allo form, but the one with 42 residues is more toxic. But here we analyzed this data for A beta 40 because from the David Shaw Research Center, we obtained these trajectories, so they are open access, 30 microseconds of MD, and they performed simulations at different force fields, and we analyzed them in detail. And the Markov state, here you can see the Markov state model from two different simulations, one using the EMBER 99 SP force field with UCB, University of California, Berkeley, because the group of Teresa and Gordon made changes or adaptations to this force field. That's why this acronym, and the CHARM36M, that's which is based on CHARM36 and which was adapted so that it's better for intrinsically disordered proteins. but nonetheless, you can see differences. We calculated different NMR observables like the 3J coupling constants. We calculated chemical shifts. We calculated the end-to-end distance and the thread efficiency. So all kinds of data which are available from experiments, we also calculated from our simulations, and we made the comparison. And the main conclusion is that this force field is the best one for amyloid beta. And it's basically, we have like 95% of the time, the amyloid beta is completely more or less extended in a random coil state, and only 5% of the time it forms some transient beta sheet. Whereas with CHARM36M, we have a bit too much of beta sheet, so only 81% is random coil and the rest is beta sheet. However, a problem with this force field here is that with this force field, the peptides and proteins do not aggregate anymore because the protein-water interactions were increased, and this way, the proteins and peptides are too soluble. So it means in the end, we want to simulate the aggregation of peptides. And because of this shortcoming, we cannot use our the EMBER-99 as we use CB in our simulations. Instead, we now use mainly CHARM36M because we found that this is the current best force field when it comes to the simulation of peptide aggregation. And another thing what we found is that only to obtain converged results for the monomeric A-beta peptide, we need about 20 to 30 microseconds of these simulations. Only then we could, these transient transitions between these rare states here can be sampled with certainty. Okay, here you can see some structures. These are like in the top row, these are good structures, meaning they're in agreement with all kinds of experimental data. These ones, they are not so good structures. At first sight, they look quite similar. If one looks into detail into these structures, one can finds out as here that especially the N-terminal region here, that they are like too curved, they have too many turns with a tendency to form helices, and therefore they disagree with the data from NMR. So meaning that now one can also use this information to go back to the force fields and make further improvements. That's something we work on, but this is work in progress. So I talked about Markov state models. Markov state models, one can understand like a kinetic clustering for what one needs a completely converged trajectory data. Not always we have access because the time scales are too long. So it means we have data, but they are not completely converged yet. But of course, also these we want to analyze. And here we use kinetic, conformational clustering. For instance, here in terms of peptide aggregation, we use different features or descriptors to characterize these aggregates, for instance, in terms of the oligomer size, the number and types of interpeptide interactions, or also the oligomer shape. In the movie that I showed you in the beginning, we analyzed these data exactly this way and calculated the transition networks, which then looks like this. The numbers, these are the aggregate size, meaning we start with monomers, which grow into dimers, trimers, tetramers, pentamers, and so on. And the color refers to the shape. Blue are for more almost spherical-like, so globular oligomers, and red is for ellipsoidal oligomers. And an interesting feature here is that the ones which are blue, which are more globular, they have a very small tendency to aggregate into larger oligomers, whereas which are more extended, like this one here, they grow into larger aggregates. And this is because these ones have more hydrophobic residues on their surface, which are of course then prone to further aggregation. This, but it's what we calculate, what is shown here. So the x-axis is the hydrophobic surface area for instance, for the elongated tetramers, and you can see the distribution is at larger values than for the more compact tetramers. And this is an interesting finding because this can be correlated to observations from experiments, because from experiments it was shown that the amyloid oligomers, which are more hydrophobic, these are the ones which are more toxic. So it means from here we would suggest that, okay, the elongated oligomers which we see should also be more toxic than the other ones. But of course, it's difficult to assess toxicity of our oligomers from our MD simulations. But nonetheless, we can make this correlation, and which can then also create ideas for further experiments. The comparison to experiments is something what is very important to us. Here you can see, for instance, the results from our collaboration partners in Düsseldorf. They used analytical ultracentrifugation to characterize the aggregation process, and then they found, okay, smallest oligomers which can be captured by this method, they have like sedimentation velocity coefficient of about 2.56. And we can calculate these so-called S values also from for our oligomers. And then we saw, okay, only pentamers and hexamers have S values which agree to this value from experiment. So that by the joint application of experiment and theory, we could then conclude that the smallest detectable A-beta oligomer in solution is a hexamer or maybe a pentamer. Okay, but the title of my talk is about beta aggregation in vivo. Till now, I only showed you data about aggregation in vitro. Let's come to in vivo. So quite often one sees pictures of neurons which are like an empty space. But of course, the space between neurons and glia and astrocytes, that's not empty. The space is filled with the so-called brain extracellular matrix. And here you can see like a cartoon with a neuron which is surrounded by the perineuronal nets. So the perineuronal nets, this is the brain extracellular space, which is in direct neighborhood of the neurons. And for instance, the blue lines, this is hyaluronan. Then we have proteoglycans shown. This little thing is a proteoglycan, and so on. And in red, this should be A-beta. What this cartoon is supposed to demonstrate is that after secretion into the brain extracellular space, the A-beta peptide is surrounded by many different other molecules, by ions and so on. And from biophysical experiments which probe the interactions of these different extracellular components, it is known that all these molecules and ions do have an effect on the aggregation of A-beta. And that's something what we also want to study using simulations. At the moment, we focus on the individual components, like what does a change of the pH do? What does oxidative stress do? What does crowding do? What does, even though crowding is more important, like intracellular, what do ions and osmolytes do? Today, I want to talk a bit about the interplay between amyloid beta and lipid membranes. And for this, we set up a neuronal membrane with 6 different components. And we added, so first we characterize this. It's in the liquid ordered membrane phase. In the previous talk, you already heard about these different membrane phases. And we saw the main lipid clustering is between GM1 and the ganglioside GM1, something what you can see here shown in yellow, that because they have sugar groups sticking out of the membrane and they form hydrogen bonds between the sugar groups, and that's why the GM1 has a high tendency to cluster with itself. Then here you can see some snapshots, how E-beta adsorbed to the membrane. And what one can already kind of see is that also E-beta has a tendency to adsorb to the GM1. And this is confirmed when we analyze the interaction energies between the different lipid components and the E-beta peptides. So we added 2 peptides called monomer 1 and monomer 2 here. And then we saw, okay, with sphingolipids and POPC, E-beta has only a very small tendency to interact with, whereas with the GM1 and POPS and POPE, there are a lot of interactions, and they are especially via the N-terminal residues. And these interactions are mainly via hydrogen bonds, and especially also with the sugar groups between GM1 and E-beta. We characterize the aggregation pathway with the so-called transition networks on the x-axis. So going from left to right, we have monomers here, dimers here. The number of interpeptide hydrophobic contacts grows from left to right. The amount of beta sheet grows from bottom to top. And then you can see some snapshots here for different states which are highly populated. And as a comparison, we run, so what I didn't say, these are 12 microseconds in total. And then we run also 12 microseconds for the aggregation in solution. And these are like intrapeptide contacts. And this is for the peptide here, which is the one which is membrane absorbed. And there you can see, okay, there are not many intrapeptide contacts. Whereas when we look at the same for the aggregation in solution, first of all, you can see we have more beta sheet. The whole peptides are more extended. We have a very ordered structure in the dimer. So, and for the monomer, we saw random coil, and now we have this transition into beta sheets with these so-called beta hairpins. So this is here characteristic for a beta hairpin, which you can also see here in these snapshot figures. We can analyze the secondary structure in more detail. And again, we find that the peptide, which is directly adsorbed to the membrane, so this is this panel here, the amount of beta sheet, which is shown as in red, is being reduced. So the take-home messages from this study were like the interactions between A-beta and the membrane, neuronal membrane, reduces the beta sheet amount, which is interesting because the transition into beta sheets is the one which drives the whole aggregation process into amyloid oligomers and then fibrils. The key interaction partner are the gangliosides, but the gangliosides form hydrogen bonds with the amyloid beta peptide, and therefore amyloid beta does not form beta sheet with the neighbored peptide, and therefore we have a reduced amount of beta sheet. And something else like the amyloid oligomers which form are toxic, but it's not quite clear why they are toxic. One hypothesis is that they insert into the membrane. That's something what we did not see, but we have to consider that we did simulations on a small microsecond time scale, as I said, 12 microseconds, and most likely these time scales for membrane insertion are much, much longer. Yes, in my group, we study also like the influence of extracellular matrix, but I'm at the end of my talk, and especially the time is up. Just here, so for this we constructed a model for proteoglycan, which is called aggregane. It's a huge extracellular matrix proteoglycan, something, it looks something like this. It's a huge peptide, not peptide, it's a protein. We added amyloid beta, and then we really see that the pH plays a big role in the interaction. That's something that makes a connection to inflammation, because Alzheimer's disease is always connected to inflammation processes in the brain. And with this, I'm at the end. So that's basically, these are the different lines of research surrounding amyloid aggregation in the end. So the long-term goal is to really put everything together at one point using multi-scale simulation techniques. But yeah, I want to thank you for your attention, and of course my group. Without them, this work would not be possible. The people highlighted in blue did the work that I presented today. And yeah, I'm open for your questions now.
Excellent. Thank you so much, Birgit, for showing us the interface of computational chemistry with in vivo experiments, which is really exciting. So I have a question regarding, you mentioned the length of the simulations. You mentioned that you found that you needed 30 microseconds of simulations, but how many, is this an aggregate number of the 30 microseconds, and how many replicas, how many what is the number of the actual simulations that you need to construct the Markov state model?
So so in general, the good thing with Markov state models is that you don't need like one long trajectories. You can have several shorter trajectories. The initial trajectory Markov state models that I showed for the monomerica beta, these were one long trajectory, which we got them from the David Shaw Research Center. As a comparison, we run 6 × 5 microseconds. We obtained the same results. And like then with the neuronal membrane, what we did there, it's like 6 × 2 microseconds. And what we do, we usually run one initial simulation, pick different structures there, and then start new simulations from further structures. And of course, the idea is for Markov state models would be adapted simulations that one picks them by extracting structures from undersampled regions.
And Carmen Domini, she has a follow-up question related to that, which I think is also very important. How did you check that you have enough sampling to construct the Markov model for this particular problem of aggregation?
So for aggregation, so what I showed here is like transition networks, because at the time when we wrote the paper, we didn't have enough sampling yet for the Markov state model. So we use PyEMMA for constructing the Markov state models, and basically there are different tests which show you whether you reached convergence or not. And actually, if the convergence is really, really low, then at the end you cannot construct the Markov state model because some transitions are not sampled enough. So for the dimer in solution, we continued the simulations, and we were able to obtain a Markov state model with about 40 microseconds of sampling. So just to give you an idea of the time scales involved.
Okay. Thank you very much for the exciting talk. There are some more questions for you in the chat and in the Q&A, so maybe you want to answer them in writing.
Okay.
And thank you very much again. And I would like to continue with our next speaker, Pedro Fernandez from the University of Porto, who will speak about fine details of the pre-organization of enzyme active sites and their role in enzyme catalysis and engineering. Pedro, do you want to share your screen?
Yes. Okay, so do you see my talk, I believe? I'm sorry.
Yes, excellent.
So first of all, I would like to thank the organizers, so namely for the kind invitation to be present in this conference and to show my work in this wonderful setting. So I'm going to talk about the fine details of enzyme pre-organization. And basically, to begin with, I would like to tell you about the research fields that we work right now. So we work in enzyme mechanisms in engineering, which is our main research field. We try to understand and determine enzyme reaction mechanisms and to make rational mutations to the enzymes to synthesize what they want to synthesize and at the rate that we would like to. But we also work a lot in molecular dynamics of proteins in membranes, and also peripheral proteins and transmembrane proteins. We do algorithms for computational alanine mutagenesis, which identify specifically the residues in a protein-protein complex that are responsible for the main bulk of the binding free energy, so that we can split protein-protein complexes with small molecules, hitting the key residues that are responsible for the binding. We also developed scoring functions for protein-protein docking, and we also work in docking algorithms in drug discovery, the later more in collaboration with pharmaceutical companies for outsourcing. But our major field of research is enzyme mechanisms and enzyme engineering now. Two of the subjects that we work the most now, even though I'm not going to talk about them today, is the bioplastic recycling. So we are working in engineering two enzymes, PETase and METase, which can decompose PET plastic, which makes this is the polymer that makes our bottles, to the original monomers that can be reused to resynthesize PET. So it's a perfect cycle in which you have the monomers, you produce the polymer. Once you get the polymer, you put the enzymes and you get back the monomers. And this is a work that is recently going on. And a big part of the computation is done. Now we are moving to experiments in collaboration with other partners, of course. And we are also working in snake venoms. In snake venoms, we are basically trying to use enzyme toxins to make drugs, because it may be surprising for many, but in fact, if you isolate some of the toxins of the venom, they are very toxic in the context of the whole venom. But separating from the other toxins, they are not very toxic. Their action alone is not very toxic. And so you can use their bioactivity to create new drugs. And there are some in the market that came from snake venoms. Some others in clinical trials, you are trying to develop new ones. And we're also trying to develop new antidotes that are less species specific. So current antidotes are these antibodies. So they work for the species which are used to immunize animals from which antibodies were taken. They're working a new generation of very small molecules and very stable molecules that can be preserved in rural settings without refrigeration and can be used to gain some time as a complementarity for snake bite, for snake envenoming. So, but my main topic today is about enzyme reaction mechanisms and the defined details of pre-organization. So we use basically two techniques, one more based in adiabatic mapping, in which we make molecular dynamic simulations, and we take snapshots from molecular dynamics, which are the snapshots are taken from a Boltzmann distribution. They more or less is a small number of snapshots, but they follow the ensemble distribution nevertheless. And we also do QMM molecular dynamics, in which we calculate free energy profiles. So in the first method, which is more similar to single molecule experiments, we get a lot of information about the origin of the catalytic power of enzymes. In the second method, based in QMMMD, we get more converged averages, so more robust numbers, but less atomic level information. So both are very useful, and it's interesting to do both at the same time. And well, I'm going to tell you about some small stories of enzyme determination of enzyme catalytic mechanisms that I think are interesting and teach us a lot of lessons. The first example, I took it from a study of fatty acid synthase. So fatty acid synthase is a multi-enzyme, so it has 7 active sites which catalyze different reactions. In total, the dimer has 14 active sites, but they are, as is a homodimer, only 7 are different. Nevertheless, to create a palmitic acid molecule, you need to run through these 7 active sites, and multiple times through each one. You need to run through 43 times each active sites, and then in total you have a very, very complex transformation. And we were studying the reaction mechanism of each active site of fatty acid synthase to try to decipher the whole catalytic mechanism, the whole turnover mechanism. Each active site is a catalytic mechanism, but we want the whole turnover. And during these studies, we found something very interesting in one of them, which was annual reductase. And in annual reductase, the reaction mechanism is very simple. So we wanted to study for the sake of completeness, to understand the whole catalytic mechanism of fatty acid synthase. So we did a model with about 8,000 atoms, in which we had 2 quantum mechanical layers, when we DLP or CCSDT, which we extrapolated to the complete basis set, just to have a more accurate region in which bonds are being broken and formed. Second layer at B3 lip level with 150 atoms, and the rest in molecular mechanics, to study a mechanism that in principle was very simple. And this classical this mechanism has decades. So you have a carbon-carbon double bond and an NADPH cofactor, which is an hydride donor. And you need to reduce this to a single bond. So the idea is that you just transfer a hydride to a sp2 carbon, and you generate basically a circle which has a oxyanion and shared with the carbanion. So most of the time, the most relevant resonance structure will have here a double bond in the single bond, and most of the charge will be in this oxygen. But if you calculate atomic charge, you understand that this carbon is more electronegative than normally. So it has some carbocationic character, which readily deprotonates a nearby lesion and gives a single bond. So it's a very simple mechanism, it has decades. But Tobias Erb, during the study of a similar enzyme, a homologous enzyme, he experimentally found 2 intermediates, 2 substrate NADPH covalent adducts. One in each the cofactor was attacked in carbon 2, and the other one in which the cofactor was attacked in carbon 4, and they were more or less stable. They could be visualized by spectroscopy, they could be characterized by NMR, so they are more or less stable intermediates. And nevertheless, the reaction proceeded to the product. And it was very surprising, and because the mechanism is so simple that we are surprised that no one thought that this carbanion-like structure could attack the electrophilic ring and give origin to a different reaction path. Even though it was evident, nobody thought about this before during so many years. So we started investigating this mechanism. But before proceeding, I would stress that this C4 adduct was not found in the wild type. It was only found in the mutant enzyme. So we studied the reaction mechanism, and so we get these free energies for the classical pathway, an hydride transfer with a very reasonable barrier in kcal per mole, a stable intermediate, and then another fast reaction to give the product. And this was clear, and the activation free energies more or less matched the experimental rate constant using the transition state theory to convert one in the other. So it was okay. And then we tried to form the observed adduct, C2 adduct, but whichever reaction mechanism, reaction coordinate that we tried, we could never reach this adduct without going through a very high barrier, even though it was more or less stable. So with a free energy not very different from this intermediate, you could say that this could be observed if it was formed, but you don't have a path to form. Then we tried to form it from this intermediate, and this has a manageable barrier, still high, but manageable. So you can more or less accept that the reaction can proceed to the intermediate, and from here to the covalent adduct that was observed, whose free energy matched the fact that it was observed. But from here on, again, whichever we tried, we never got any path that could lead us directly from this covalent adduct to the product, because all barriers were too high. Then we tried to form the C4 intermediate that was not visible in the active site, but only in a mutant. And from the reactant or from the intermediate, we could never form it with a reasonable barrier, and we could not move it from here to the product, even though it was stable. So we introduced a mutation that was introduced experimentally, that was near the active site and displayed slightly the NAD pH from its original position. And with here, the barrier lowered very, very much, and we could observe the intermediate. So basically, this whole potential energy surface justifies the detection of these two intermediates. But they also tell us that the true reaction mechanism, dominant reaction mechanism, is still the classical mechanism. And in fact, from the reactions, from the main reaction mechanism, you can derive to these two intermediates, but they are dead ends in the potential energy surface. Once you reach these intermediates, you have nothing to do except to come back to the main pathway and follow the main pathway. They are dead ends in the catalytic mechanism. So they are not really in the reaction pathway. And basically, what this makes us think is that many times we have a reaction mechanism and we detect intermediates. And the fact that we detect intermediates doesn't mean that these intermediates are on the wild type reaction pathway. They can be side pathways that go back to the main pathway. So we should not force us to pass through all intermediates, even though we should justify that they are observed. So the other very interesting thing that we saw was with HIV-1 protease. So basically, we made a very large molecular dynamics, regular molecular dynamics simulation, 130 nanoseconds. We took a number, about 30 conformations, and repeated the reaction mechanism from this. And we found fluctuating barriers depending on the starting conformation. That was expectable. But we also found two different reaction mechanisms. So depending on the conformation that we have, we get a different reaction mechanism. And these two reaction mechanisms have similarly low barriers. So both are contributing to the observed, to the macroscopic transformation. So basically, we try to explain why we have two different reaction mechanisms. So basically, the mechanism depends a lot on the distance of attack of the water molecule, because it's a peptide hydrolysis. One protonate aspartate has protonated the carbonyl bond, and then either the water molecule is deprotonated by one aspartate or by the other aspartate. So we have two competing bases. And if you have basically for example, a very large distance to this base and a short distance to this one, and you have two long hydrogen bonds here, which do not stabilize very much these aspartates, basically you have the right conditions to follow a mechanism in which this aspartate will be the base. So it is not very stabilized, the base is not very stabilized, and it's very short to the water molecule. So created basically a collected variable in which we adapt these three large distances and subtracting the fourth. And the hypothesis is that if this is irresponsible for the choice between mechanisms, there will be a correlation between the choice of the mechanism and the collective variable. And in fact, you see the correlation. With this collective variable is large, you only have the mechanism with two aspartates, with the exception of the high energies, which are not representative for the observed phenomenon. And when the collective variable is short, you only have one aspartate mechanism, the exceptions with high barriers, which again are not relevant because they'll not be observed in the real world. So it's the network of hydrogen bonds that justifies the choice between one and the other mechanism. Now shortly, and to finish, I'll explain why the barriers fluctuate. Now we'll take an example of one aspartate mechanism. So we suppose that for the mechanism to have a low barrier, you need instantaneously a short water-carbon distance, a short deprotonating distance, a short protonated distance, in the long distance between this aspartate and the water molecule. Because at transition state, this water molecule will be it will be negative, it will be an hydroxide, and this interaction will be repulsive. And so again, we create a collective variable, just add up these three and subtract the fourth without any waste. And we correlated this with the activation free energy. And again, the bigger the collective variable, the bigger the reaction energy. So which justifies that these are the main interactions responsible for the magnitude of the barrier. And so basically the conclusion is that there's a very tight network of hydrogen bonds that are constantly fluctuating, and depending on the overall arrangement of all of them, you can follow one chemical mechanism or other chemical mechanism, and within a given chemical mechanism, the very fine distances of the hydrogen bonds give you a high barrier or a low barrier. So it's not enough to have residues pointing in the right direction to have catalysis. You need specific distances and a specific arrangement of specific distances all at the same time. So I would like just to thank the people that do this work, Maria Ramos, which has been working together with me for many years, and all the students that contributed for this. Some of them are not here anymore. And we also thank our financing agency, FCT, and the supercomputing infrastructures of European super infrastructure price and the US super infrastructure of the Oak Ridge National Laboratory. And thank you all for your attention. Thank you.
Thank you very much, Pedro, for showing how these fine details can really affect how enzyme active sites rearrange. So I wanted to ask, and again, I remind everyone that you should post your questions in the Q&A. I wanted to ask if you think that we are going to see machine learning advances also in this area, in enzyme pre-organization in the active sites, or is every enzyme unique in its own way, and we could not use big data to somehow predict what is going to happen in enzyme active sites?
I would say that in principle, our perception is that the enzymes are very unique. But the main problem for me is that we don't have enough data to train a machine learning algorithm. If we have enough data, I believe that a machine learning algorithm will help a lot.
What kind of data are you thinking of?
Basically, accurate reaction mechanisms, which are more or less demonstrated and not controversial in large numbers and for a lot of different enzyme families.
I see. So you think that the current reaction mechanisms that are known either from experiments or computational work are not going to be enough?
I think are not going to be enough, to be honest, but it's a personal opinion. I'm not an expert. I would love to, but I think that the number of examples that we have does not cover the diversity of the chemistry diversity of enzymes, and many enzymes are not very well studied. The very reliable mechanisms are not enough in number.
Yeah.
But I hope in the future this could be solved.
Definitely so. And there is one question in the Q&A from Ernest.
Okay.
For the Gaussian onion calculations, what embedding approach do you use, mechanical or electronic, and which do you recommend from your experience?
I think that we use electronic embedding, even though no one is perfect. Both have problems, but electronic embedding somehow put us rid from the problem of parameterizing the substrate at a transition state where all these bonds are being broken and formed, which is very difficult to parameterize with point charges and without a way of testing the parameterization against experimental data. So electrostatic embedding avoids the problem of parameterization of very difficult species. So we use it, electronic embedding.
Okay, excellent. Thank you very much. And in the interest of time, because we are a little behind schedule, thanks, Pedro. And I would like to welcome on stage Katarina Nikolic from the University of Belgrade, who will speak next about epigenetic drug discovery and the successful examples of computer-aided drug design of histone deacetylase inhibitors. Welcome, Katarina, and if you could now share your screen.
Yes, just 1 second. Okay.
Excellent. We can see your screen.
Okay. Just 1 second because of my presentation. I hope so that you see my screen well.
We see it very well. If you can go into presentation mode.
Presentation mode, I think so, is already on, but
if you click on the icon which is next to the minus sign on the bottom left side, can you see? Can you go with your cursor with your mouse? We don't see your mouse
here. I cannot.
Yeah, down. If you go to the bottom, can you see the icon next to the minus sign on the bottom? On the bottom?
On the bottom, yes. Okay.
Do you see the minus sign?
No, I cannot see the minus
sign.
sign.
You see the 57%? On your screen, it says 57%.
No, I cannot see it here. Maybe here? No. Yes, here, yes.
If there's an icon next to it, can you click on that? That makes you, yes, exactly.
Okay. And can you see my screen now? No?
No. You have to click on that icon to go into full presentation mode. Nonga showed you where it is.
Here? Okay. No, it doesn't work from my side. I'm not quite sure why it is like
that's
this.
That's why we had the rehearsals earlier, but okay. So you have to go into slideshow. Can you go into the slideshow?
Can I make a suggestion? Yes. So please stop screen sharing first.
Okay. Yes. Now we can, yeah.
Yeah, okay.
Yes.
You're still sharing the screen.
Okay. Now if you go on display settings and change, presenter view. Just go up a bit. Yes. Here, exactly. Right.
Okay.
Here, display settings, click on that.
Yes.
Swap presenter view.
Here we go.
Okay. Is it okay now?
Yes, we can see it. Thank you.
Okay. Okay. Thank you for your help. So just 1 second. I hope so that I will see. Thank you for your nice introduction and giving me the opportunity to present results of my research group. So during this presentation, I will show you 3 successful examples of computer-aided drug design of inhibitors of epigenetic enzymes. First, I will explain the development of inhibitors of histone deacetylase 6 and sirtuin-2 as a group of histone deacetylase inhibitors, and also one small group of inhibitors of histone methyltransferase, actually DOT1L inhibitors. So first, let's start with histone deacetylase 6. Histone deacetylase 6 is responsible for the acetylation of lysine. That is a very important part of the regulation of transcription and some other function in cell, like motility of cell. So overexpression of histone deacetylase 6 is very common in many types of cancer. That's why the histone deacetylase 6 is validated drug target for cancer therapy. So far we have some inhibitors of histone deacetylase that are on the market, but they are not so selective for histone deacetylase 6 isoform. That's why we started the rational and computer-aided drug design of selective histone deacetylase 6 as a promising drug, cancer drug
candidate. Histone deacetylase 6 contained 2 catalytic domains, and we were working on the catalytic domain 2 as the main catalytic domain of histone deacetylase 6. Actually, I have some problem. Yes, here we can see the procedure, how it actually histone deacetylase 6 work, and the deacetylate the lysine as an essential step in the activity of histone deacetylase. So in order to develop the selective histone deacetylase 6 inhibitors, we have selected the group of the inhibitors with the experimentally determined activity on histone deacetylase 6 and also on histone deacetylase 1 as the isoform of histone deacetylase from the either group of histone deacetylases, in order to define the molecular determinants that are specific for selective inhibition of histone deacetylase 6. In that way, we first defined the data set and made the geometry optimization, and we extracted the bioactive conformation of the inhibitors from after the molecular docking in the histone deacetylase 6 and also in histone deacetylase 1 isoform. These bioactive conformations are later used for pharmacophore modeling based on the molecular interaction field energy derived as a result of interaction between 4 chemical probes and our ligands. This interaction is later converted to the green descriptors, which are used later for partial square regression and formation of 3D QSAR models. These 3D QSAR models are later used for pharmacophore analysis, and based on this pharmacophore, we were able to suggest further structural changes and design of novel inhibitors. So at the beginning, we started with the Campbell database. We selected this data set with compounds with the activity, experimental activity on histone deacetylase 6 and also on histone deacetylase 1, in order to be able to create both 3D QSAR models and also in order to select the specific structural determinants that are important for selective inhibition of histone deacetylase 6. Based on these 3D pharmacophores, are later designed the novel compounds, they designed the novel ligands, and apart from the 3D QSAR modeling and this pharmacophore modeling, we have also performed the molecular dynamics analysis and examined the interaction of the ligands in the binding pocket of both HDAC isoforms. Based on all these results, we have selected the best candidates of the designed compounds, and as a lead compound for this design, we have used the scriptide molecule. Is inhibitor that is selective for histone deacetylase 6. This is a delta pKi value between histone deacetylase 6 and histone deacetylase 1. So we can say that almost 1 log unit is a difference between activity on one and on the histone deacetylase 6 and histone deacetylase 1. But again, the scriptide has some other characteristics that should be overcome in this design. These are related to its physicochemical properties and also pharmacokinetic properties. So our goal for next step was to actually to change the cup group of scriptide and select by fragment-based design to select the novel cup groups. So we use the 2 chemical fragment-based libraries and calculated the descriptors in the Dragon 6 software, and these selected fragments were used instead of the 1,8-naphthyl amide in structure of scriptide. The designed compounds are further used as a test set in our 3D QSAR models for histone deacetylase 6 and histone deacetylase 1. And also these designed compounds are further analyzed by molecular docking. So the designed compounds are examined by docking, and the interaction in both binding sites of histone deacetylase 1 and histone deacetylase 6 are compared in order to see the key interaction of the designed ligands. So we can say that design ligands are further examined by 3D QSAR modeling as well, not only by molecular docking, and the best candidates with the best selectivity ratio between histone deacetylase 6 and 1 are further selected for synthesis. So as you can see here by prediction, the delta pKi is almost 2 for the designed compound, comparing with the scriptide where the delta pKi was about 0.8. So after the synthesis, we performed the in vitro testing, and some of the compounds, as is presented here, exerted the selective histone deacetylase 6 activity. The most promising compounds are further examined by in vitro ADMET profiling and physicochemical characterization, and finally were examined on the cell-based assays. One of these selected compounds presented here with this general formula were further examined for wound healing assay. Actually, this assay is presenting the anti-migratory properties of this novel compound, showing that this compound has anti-migratory properties and a potential anti-metastatic activity on this MCF breast cancer cell line. Also, the invasion is also examined for this designed synthesized compound, and it showed that the invasiveness of this MDA-MB231 breast cancer cell line is also decreased. So we can say that this group of synthesized compounds has possible anti-metastatic potential, not only anti-cancer potential. The other group are the sirtuin-2 inhibitors. Sirtuin also belong to the group of histone deacetylases, but its substrate specificity is quite low. Therefore, observed the high flexibility of the binding domain of binding cavity of sirtuin-2, and also because of that. We couldn't define the specific pharmacophore for the sirtuin-2 inhibitors for all of them, and also the docking study couldn't explain properly the activity of the sirtuin-2 inhibitors. Some of the results was not in good agreement with experimental activity of sirtuin-2 inhibitors. Therefore, we performed the molecular dynamics simulation in order to target the global minimum of sirtuin-2 in order to find this minimum conformation that could be effectively used for design of novel selective sirtuin-2 inhibitors as potential anti-cancer and also anti-metastatic agents. So after we performed the molecular dynamics simulation of cofactor loop, where we simulated the APO enzyme, and also with the cofactor, with this blue, and also with two inhibitors, serine and thienopyrimidinone, as two different inhibitors in order to examine the different conformations of sirtuin-2 in contact with various inhibitors. Based on this RMSD graph, we can conclude that there is a big fluctuation of and difference in conformation between these examined complexes, and the highest fluctuation is in this cofactor binding loop, as it's shown on this graph on the left. By principal component analysis and positioning of C-alpha atoms of sirtuin-2, we can conclude that there is some kind of overlapping between conformations of sirtuin-2 in complex with inhibitors, with different inhibitors, but also there is also significant flexibility and significant changes in conformations of sirtuin-2 in complex with different inhibitors. So we should further examine these trajectories of molecular dynamic analysis, and based on principal component analysis and RMSD clustering and linear discriminant analysis, we defined this free energy landscape that this centroid one is actually touching this global minimum, and also centroid 2 in complex with pyrimidinone also is with quite similar minimum free energy. Between these two centroids is, we can say, low energy barrier, so it could explain this flexibility of sirtuin-2 and the easy change of conformation from one to the other global minimum. Linear discriminant analysis actually selected this centroid 2, that is a real complex with sirtuin-2, as the best conformations for discrimination between active and inactive inhibitors of sirtuin-2. So here on the left, we compare the starting X-ray structure of sirtuin-2 and also the centroid 1, and we can see that big changes in the conformation of sirtuin between these two complexes. And on the right side, we can compare the centroid 1 and centroid 2, and also we can observe the differences in conformation, that giving us the actually conclusion that the sirtuin-2 has many conformation states, and we should work with this consensus or centroid structure for the further analysis. Therefore, we use this centroid 1 and centroid 2 conformations obtained after the molecular docking of sirtuin with different inhibitors for structure-based virtual screening of the library of the compounds. And for this structure-based screening in the FLAP software are calculated molecular interaction field energies of the ligands, and also for the active site of sirtuin-2, and based on the similarity score between these two MIFs calculated, all the ligands in the database are ranked, and the top ranked the ligands are actually the ligands with the highest possibility to effectively inhibit sirtuin-2. Here on the graph, we can see the results of virtual screening. Actually, we created the database of active sirtuin-2 inhibitors on one side, also the inactive sirtuin-2 inhibitors, decoys, and based on the results of this virtual screening, we can conclude that early enrichment factor is significantly increased by using this multi-structure conformation. This multi-structure conformation of sirtuin-2 is created by combination of centroid 1, centroid 2, and X-ray structure of sirtuin-2. So in this multi-structure of sirtuin-2 are actually combined in the most relevant conformation of sirtuin-2, and therefore the enrichment factor of this combined multi-structure virtual screening model is with the highest performance. So comparing with this single X-ray model that has 10 times lower early enrichment factor. It means that after this molecular dynamic simulation, the accuracy of and success of virtual screening is 10 times higher. Therefore, the possibility to find the truly active SIRTUIN2 inhibitors are significantly increased. So here are the top ranked the inhibitors from our virtual screening. The compound 6 is here selected, and as one specific structure with additional activity on bromodomain 4 as potential hit for dual SIRTUIN2 and bromodomain 4 inhibitors. But for us are the most important, this compound 2 and compound 1 as two selective SIRTUIN2 inhibitors, and these two compounds could be later used for design of novel ligands. Compound 1 and compound 2 will be used for the change of this tenovin 6 structure in order to design novel ligands. So here is presented actually one of the synthesized compound after combining the structure of tenovin 6 known SIRTUIN2 inhibitor and these two previously selected compounds from virtual screening, compound 1 and compound 2. Based on all these structural changes are created a set of novel inhibitors, and some of these inhibitors were examined on these breast cancer cell lines, and they show significant activity. Apart from the activity, they show this altered phenotype that is actually giving the promising results for the further study of these ligands. And finally, third case study.
We have to finish. We have exceeded the time, I think.
Okay, if you have to finish, we can stay here, or just I have a few more slides, as you say.
Okay, 1 more minute.
Okay, for this DOT1L inhibitors, we applied a different approach. We are applied ligand-based virtual screening, and after the ranking, we applied docking on the virtual database. And based on this virtual screening, for this virtual screening, we use this selective DOT1L inhibitor as a template, and we had a quite high performances of this virtual screening. Area under curve is 0.98, is giving the information about the quality of the screening. Based on the docking study of our compounds and this template starting compound, we have selected the A7 and A8 as the most promising ligands for the synthesis. These two ligands were synthesized, and first the docked, and after the docking we selected the most promising A7 compound, and both A7 and A8 were synthesized and examined for the DOT1 activity. So we can say that their activity is quite acceptable. We can say that this activity is in range with the starting compound, and also they exerted the activity on the leukemia cells. So it showed that these selected compounds could be very good drug candidates for further study. And at the end, I would like to thank my colleagues from University of East Anglia, from Institute Pasteur, University of Eastern Finland, from Hofer Institute, and my colleagues from University of Belgrade Faculty of Pharmacy for their cooperation on all this work. And thank you for your attention.
Thank you very much. Thank you, Katarina, for this talk. And I would like to ask if there's any questions. Okay, we're a little bit behind the schedule, and I know that some of our speakers have to leave for the next session, so we have to start on time. Unfortunately, we have to start at 4:15 sharp, so Marcus, don't worry, you will be on time. So I would like to close the session. If you have questions for Katerina, please drop them in the Q&A, and Katerina will be able to answer the questions. So apologies for the short 3-minute break, but while we are on this break, I would like to take the opportunity to have our first poll of this day, where everybody will vote for their favorite presentation. So we will now run the poll on the 4 speakers that we had, and please vote. You will see a question popping out on your screen. So please click and vote for the best short talk in the biomolecular system session. Anna, is it coming in? So I do not see any votes coming in.
Yep, it's coming in on my side.
Okay, maybe I'm not a host, so I cannot see it. So I cannot see the votes. So we will leave it open for 2 minutes. And when this will close, we will start with our next speaker immediately, as he has to leave on time. And at this point, I would like to remind the scientific committee to also vote for their best preferred talk as well. Okay, I think we can close the poll now. And I would like to introduce Evelina Georgieva, who will chair our next session on electronic structure. Evelina?
Yes, good afternoon to everyone. And I open the next session, electronic structure. It's my pleasure to chairing this session. I would like to invite the keynote speaker, Markus Ryan from Swiss Federal Institute of Technology in Zurich, Laboratory of Physical Chemistry, to present us a talk from electronic and vibrational structure to quantum dynamics with matrix product states. And are you ready?
Of course.
Oh, thank you.
Thank you for the introduction. I share my screen. Just a second, please. Should be this one. Okay, can you see my slides?
Yes, yes.
Excellent. So the title you have already seen. I don't know how many of you have heard about matrix product states, but these are the states that are optimized by the density matrix renormalization group algorithm. And so I understand that the audience is very mixed. And so I first give you a brief introduction in what this is all about, and then I tell you about some of our recent work. So we start with this brief recap of the density matrix renormalization group algorithm, in short DMRG, which optimizes the wave functions that we will study. And so just to set the stage, here you see an overview of the typical equation that we solve, which is on the left-hand side here, the stationary Schrödinger equation, which gives us an energy, and on the right-hand side, the time-dependent Schrödinger equation, with which we can study non-equilibrium processes, quantum dynamics, and so forth. And of course, how complicated the problem actually is depends on the Hamiltonian, which describes our system. And here below you see three examples, right? On the first one is the electronic structure Hamiltonian, which is here in this form, the exact non-relativistic Coulomb Hamiltonian with the kinetic energy of the electrons. And then you see all the Coulombic operators, which depend on 1 over the distance. The vibrational structure problems are more complicated because the nuclei move in the potential of the electrons, which is the electronic energy, the Born-Oppenheimer surface, and that surface needs to be expressed in terms of operators, right? And there are various ways to do that. And in principle, this is a challenge by contrast to the electronic structure problem where you have these seemingly simple Coulomb operators. And then, of course, if you talk about vibrational electronic coupling, you look into vibronic processes, you might want to study Hamiltonians as the one below here, which actually couples nuclear and electronic motion. Okay, the problem I should say is that this many particle state that you might want to approximate in order to get its energy or dynamics is suffers from the curse of dimensionality, because when you try to construct it from single particle states, for instance, orbitals, you will face an explosion of states that need to be taken into account. And typically, this construction is done in terms of occupation number vectors. That's just one way to formalize it. You can also think about configurations or determinants. In the case of electronic structure fermionic problems. But essentially, when you take these occupation number vectors, which tell you something about the occupation of your basis states, the orbitals or modals, then you take all of them, and this number is the one that is exploding, in a superposition to get the total state. You can ignore the subscript vibrational there, because this principle holds for all those wave functions that we are considering. And then there is some expansion coefficient, right? And this you call configuration interaction. Problem is that there are too many basis states, and at some point it will become unfeasible to solve this equation. And so, just a second. So this is kind of the problem, right? We have a expansion tensor, a CI tensor, which refers to all the individual information here encoded in terms of orbitals, and that is difficult to construct. There's no hierarchy introduced, and instead, if we focus on, say, on a single orbital like this one here in the black box, which is a system, and we consider the rest of the orbitals which construct the states as the environment, our CI expansion can be simplified. I mean, the equation looks much more difficult than before, but in fact, it's a simplification. Now we have three parts. So our occupation number vector consists of a part on the left, that's why there's an L, and on the right, and there's the orbital that we're actually looking at here in red, right? And there's this sum over all the states that are available to the spatial orbitals, and there are two sums for the states defined on the left and right of this single orbital. Right, to the left, we have part of the environment, and to the right, 2 in green, right? And then these sum run to m left and m right, and these numbers are huge. And that is a problem for computational purposes. But now you see already from this representation, that's also a way to reduce the complexity. Let me go do this again. So we have this situation, and now we reduce the complexity by restricting the sum to m, right? So instead of a huge number, we use a much smaller number, and this number m is called the bond dimension. It's a key parameter in the approximation that we will be looking at. So we have a reduced number of states that is considered important to the left and right to construct the total state together with our explicitly treated side. And this is actually what DMRG is all about. This is the key principle. You can do that for every side, and then you end up at a matrix product state, right? Now you see we have done this for every orbital in our system, and we construct a CI type coefficient from a sequence of these matrices M. Let me go back. These M matrices here are the expansion coefficients in the partitioning. Okay, of course, I haven't told you yet how to optimize this M. I will do that in a minute, but the whole CI coefficient is now decomposed here. And of course, for each CI coefficient, you need a number. So the first M is actually a vector, the last one, 2, and so in between here have matrices. Okay, now in this representation, you can compute, of course, expectation values like the energy here, the electronic energy, for instance. And in this occupation number vector representation, any expectation value can be written as such, which would mean basically that in the pictorial representation, you have this blue blob over here. But that does not represent the structure of the problem because we have site information, which is orbital information. So we can rewrite our Hamiltonian. Looks again very nasty. This is an exact decomposition of our Hamiltonian where we have this sequence of H's, right? And now we have an explicit structure where rather than the total occupation number vector, we have the information on each of the sites, each of the orbitals. And so this is kind of the structure of the state that we are working with. And how to optimize that? Well, we go through this chain of states step by step and solve local eigenvalue problems. And also the local eigenvalue problems look a bit horrible. And you see this equation over here. But you have the key point here is that you have one eigenvalue problem per site, for instance, per orbital, right? And this is then solved step by step. And so you go from left to right through the lattice of sites, through the ordering of orbitals, and solve eigenvalue problem by eigenvalue problem. And when you do that, this is called and this is of course iterative, and you call it a sweep optimization, right? Let me show you what that means. That for an example from a vibrational structure calculation. Here you see again our representation of the energy in terms of these MPS and matrix product operator structure in blue, and we go through this through the lattice of orbitals step by step. Now you hardly see anything, but there is right now there is a thin green line emerging here on the left, which gets larger, longer and longer the further you go through the lattice until it drops down here. And now you have reached the end of the lattice, and what you do is you reverse the optimization direction and you take information from your way from left to right. And so you reverse, you go back, that's a backward sweep, and then you go again forward and backward and forward, and you see the energy has dropped and basically converged. This is how DMRG optimizes this structure, this matrix product state structure of a quantum many particle state. Now, DMRG has been applied to electronic structure problems for the last 20 years about, roughly, right? And recently it has been extended, and I'd like to talk about recent extensions. For instance, we have looked into vibrational structure problems a couple of years ago, 3-4 years ago, which defines vibrational DMRG. We recently studied preborn Oppenheimer Hamiltonians, so theories that do not adopt the Born-Oppenheimer approximation and treat electrons and nuclei on the same footing. And because it's NIAP DMRG, and I will tell you a bit about it also during this talk. Then I will switch to quantum dynamics, because it turned out that with this very general formulation and the implementation that we have in our hands, it was easy, comparatively easy, to extend this towards the time domain, where we can now solve the time-dependent Schrödinger equation. And the last part of my talk will address the dynamic correlation problem, which is a problem for all DMRG type calculations, because you need to select your one particle states and you cannot have arbitrarily many. So if you consider about an electronic structure problem and you have, I don't know, 1,000, say, or 2,000 spatial orbitals, you might be able to treat 100 of them, but most of them you will neglect, right? And so this, what is encoded there, the electron correlation that is encoded there is called dynamic electron correlation, and that will be missing. And so then you need to incorporate this somehow, and perturbation theory is not necessarily the most efficient way. So that will be the last part of my talk. So let's start with the vibrational problem. Here again, you see the vibrational Hamiltonian. Again, also this complicated structure of the interaction operators. That follows, of course, Bose-Einstein statistics, and you need to get a representation of your Hamiltonian from some step where you typically fit a potential energy surface. Then you can use, for instance, canonical quantization. So you, what you know from the quantum harmonic oscillator, to represent the single particle states on the lattice, right? And then for each of the modes, as you depicted here for ethene, you will have the same harmonic oscillator functions for the respective coordinate. And you need this in second quantization because the whole formalism, of course, operates in second quantization. And you know from the standard quantum mechanics lecture that there are these ladder operators, which are actually creation and annihilation operators for these bosonic systems. You could also choose a different basis, like this n-mode representation, which is more flexible because it gives you one particle functions per mode. Right? It can all be used in this context. And that's actually not the problem. The problem is that for vibrational DMRG calculation, you need to have access to excited states. And say in the electronic structure problem, that is often not that much of a challenge because say if you are in the ground state and you consider the excited states, how many excited states do you need? 2, 3. So you can compute them sequentially as indicated by this Hamiltonian here. But that is not possible for vibrational states because there are just too many vibrational states that need to be considered. You will see later on an example. And so it's necessary to have methods in our hands that allow us to address just some state in the spectrum. Right? You see the example here in this sketch. Say if we are interested in the red state, in the sequential approach, we would need to compute all the states below the red state. But we could also use a shift, and this is this omega here, set up as this operator, which is the inverse of this shifted vibrational Hamiltonian or electronic Hamiltonian, in such a way that the red state is now the ground state. And that's, of course, you can imagine that this is computationally expensive because you need to invert this operator. But there's more to it because it's also not necessarily a stable optimization. When you do that in the local formulation of the eigenvalue problem for each site, you get solutions which you need to select for the state that you're interested in, and you can do that with the maximum overlap criterion just to make sure that you converge on the right state. Okay, but like I said, there are two issues with this, not necessarily stable. And the other thing is you need to invert an operator. A possible solution, which we studied, is what we call folded DMRG. And that is, we apply this square operator over here, which is basically applying H minus a shift twice in the formulation that you have seen. And so that's easy to implement, straightforward to implement. And as you will see, it also allows you for stable convergence. You see, I give you an example here for the OH stretching vibration, which is the highest energy fundamental vibration in this dipeptide on the right-hand side. So with this shift and invert technique, you get convergence. You see on the x-axis is again the sweeps depicted here in green. You see convergence, but it's noisy, right? With a folded implementation, you see fast convergence and it's super stable. And in fact, you can even improve on algorithmic developments for targeting excited states by using the Feast algorithm, which we recently published on arXiv. Of course, we also have access to the spectrum. You see the spectrum of the dipeptide. In the experimental spectrum is given here as a dashed black line. The harmonic vibrations and intensities you find here as the red lines, and you see that the green ones, which we calculate with DMRG, are much more accurate when compared with experiment, as they should be. Okay, quickly on Preborn-Oppenheimer theory. That is a theory that has been studied by various groups, and we have developed together with Edith Matjusz a theory that is based on explicitly correlated Gaussians. There are also orbital-based methods available, for instance, by Hamish Schiffer and Hiromi Nakai. And we used this theory to in combination with DMRG to arrive at more accurate results. So how did we do that? Well, first of all, this is the Hamiltonian. The Hamiltonian is simple in a sense that this is a standard kinetic energy operators. Here are all the Coulomb operators of all particles, including the nuclei, right? And then, of course, you need to watch out whether you're talking about fermions and bosons. So the whole structure in second quantization is a bit more complicated, but can be dealt with. And then we optimize basis functions for each of the sets of particles that we are dealing with. And this is indicated here with a very selected CI expansion. Once we have done that, we unite all the single particle or two particle basis functions for all the individual particles in the system, like electrons and protons, and then do a CI expansion, which we optimize with DMRG in order to get a more accurate result. And here you see convergence of energies for the BH3 molecule. We compare also to data from the Nakai group. These are the NOMO-HF and NOMO-HF plus MP2 data. The blue curve is the selected CI optimization where we produce a basis set, and then on top of it we use DMRG, and as you can see, the convergence of the energy is smooth and gives us a variational energy that is below the energy of the Hartree-Fock plus MP2 result. Let me switch to quantum dynamics. There are actually a couple of variants now available for time-dependent DMRG. Not all of them easily transferred to the full Coulomb Hamiltonian that you have seen. So not all of them fulfill this challenge too. Which is that they need to be able to deal with long-range Hamiltonians such as the Coulomb Hamiltonian. And there's another challenge for matrix product state representations, and that is when you let your state evolve with time, it explores larger and larger regions of Hilbert space. And so this restriction to the number of basis states M, the bond dimension, will be more and more difficult. Our solution has been to apply an idea that has been called the tangent space time-dependent DMRG, where the bond dimension is kept fixed and one searches for the best approximation under the constraint that there is this fixed bond dimension. The working equation looks like this. You see there are these propagators that have to be implemented, and that has been done by a Trotter decomposition of the exponential, which is advantageous because you can apply them sequentially, and that is in line with those tensors that we need to propagate and can propagate one after the other in this approach. Can also be generalized to imaginary time propagation. Let me show you an example. Here I pick a third type of Hamiltonian, the vibronic Hamiltonian, where we couple electronic and vibrational degrees of freedom. So the electronic states are represented on the lattice here by these blue dots, and then we have the nuclear modes represented by red dots. And we have implemented this and applied to, for instance, this aggregate of organic molecules, for which then the lattice, the DMRG lattice, has 72 sites. And you can run the simulation, the DMRG simulation. You get the absorption spectrum, for instance, through this autocorrelation function. And you see here a result for the dimer and for the hexamer. The hexamer was on the slide before. And you see that it converges rather quickly for small bond dimension, right? M equals 10 to M equals 60 is basically the same, and that also holds true for the large hexamer case. So these calculations can be done. I should say that convergence is easier for non-local properties. If you go for local quantities, for instance, you look at population dynamics, you will see that the dependence on the bond dimension is much more severe, and you need to go to larger bond dimension in order to see converged population dynamics. This brings me to the third part of my talk, and that's trans-correlated DMRG. I told you already that DMRG is basically an active space method where you select an orbital space or a modal space, and you leave out one particle state that actually contributes significantly to the result, and you need to capture that somehow. And perturbation theory is actually difficult because of the higher order reduced density matrices that you need to compute. So we had actually been looking into short-range DFT to solve this dynamical correlation problem, which was very efficient, but comes at the cost of introducing approximate functionals into this ab initio method. And so it is much more natural to use the trans-correlation approach, which is actually an idea that is more than 50 years old. As you can see, this is old paper by Boyce and Handy. The idea is to introduce explicit distance information into the wave function, right? You see this here on the right-hand side, a typical Jastrow factor, where in the argument of the exponential, you see functions that depend on the distance of the electron coordinates. You can do that also in orbital space, and then you would work with something shown here on the left-hand side. Now, the point is that this is a similarity transformation of your state, which changes then your eigenvalue problem in such a way that eventually you work with the similarity transformed electronic Hamiltonian, or Hamiltonian in general. The good thing is that it deals with the dynamic correlation problem, or with a significant part of it. The main problem is that it's non-emission. However, you can solve that by imaginary time evolution. So as such, the method does not work with variation, does not easily work with variational methods. And that is why it was applied by, for instance, by Ali Alavi and his group for full CI quantum Monte Carlo, because of the projection that is involved. Here for DMRG, it's different. DMRG is a variational method, but the solution is you can exploit imaginary time evolution, which is this technique that is available through tangent space time-dependent DMRG that I've talked about before. It can be done in real space and also in the momentum space. I spare you the details here and switch to results that we obtained first for the Hubbard Hamiltonian, which is a model Hamiltonian from physics. But we also have now in our hands an implementation for the full Coulomb Hamiltonian. There you just need to make sure that you have all the integrals necessary to represent your trans-correlated Hamiltonian in second quantized form. I'd like to draw your attention to these columns in the middle. So first of all, you see the bond dimension M. You want to keep M as small as possible because computational effort scales with some power of M. Then there are regular DMRG results, and you see the trans-correlated DMRG results. And as you can see immediately, convergence is faster for trans-correlated DMRG. So you see that the efficiency is increased through trans-correlated DMRG as it should be. This is almost my last slide. Everything that we develop and implement will eventually become available through the QC Marcus project, which is available as an open source code. The electronic version is hooked up to OpenMolcast. The latest version has not yet been released. It will be released soon. It will be more efficient and also parallelized, and we will have also then all the methods that you have seen today available in that code. That brings me to my last slide. Of course, the work was done by very many people in my group, and I'd like to especially thank the QC Marcus team, which currently consists of Alberto Bayardi, then Stefan Knecht, who recently moved to GSI Darmstadt, then Leon Freitag, who was at the University of Vienna, but now moved to Belgium to work for a company that was founded by Toru Shiozaki. And I have 3 recent PhD students working on these topics: Robin Feldman, Nina Glaser, and Max Mörchen. That's all I wanted to tell you today, and I'm happy to answer any questions that you might have. Thank you very much.
Thank you. Thank you for the interesting talk and progress. We know about the progress in DMRG methodology. It was very interesting. And now it's time for question. You can use option raise hand for question. No one question. I will Okay, someone? I'd like to ask you about the size of the molecule. For which molecule, just about the size of molecule is appropriate, this methodology. If you compare the size of molecule and time-consuming calculations.
Yeah, so depends on what kind of problem you want to solve. Say you're in electronic structure theory, and then DMRG is a competitor of CAS-SCF. And you know, with CAS-SCF, you can treat on the order of 20 spatial orbitals. With DMRG, you can push this to 50 to 100 orbitals, right? So it does not depend, it does not scale with the size, but with the number of orbitals that are relevant for the static correlation problem. For vibrational DMRG, it was out of the box competitive with high-end MCTDH approaches, for instance.
Yeah. Okay, thank you. I do not see any questions. Okay.
There isn't one question in the chat, actually.
Okay, just we can open chat. Okay. Just we wait Q&A.
I can answer that in the chat, or I can.
Yes, can you repeat the chat? Can you repeat
I see the chat.
question?
I can answer in the chat if that's fine. As you wish.
Actually, if that's okay, if you could repeat the question for everybody, because our attendees cannot see the chat.
Okay, I see. Are you planning to apply, for example, the trans-correlated DMRG approaches on quantum computers? Which DMRG framework you expect to be most promising to be used on quantum computers?
So the answer is yes. It's
Okay.
work in progress. I can't tell you more about it.
Wow, that's a trade secret. What's going on?
Okay.
Yes, maybe. I mean, Marcus, you can maybe share a more general perspective. You know, if you wanted to, regarding work in progress on quantum computers.
On quantum computers, okay, I can do that. So that's my perspective. I mean, when you look into the literature, more and more people are working on this. A lot of the work is on the so-called variational quantum eigensolver, which uses the quantum computer to get the parameters in a parameterized wave function. And the parameterization is a couple cluster parameterization. That will be very accurate, but not necessarily of full CI quality. What we have been working on was quantum phase estimation, where you get basically the full CI result approximated, but with a known error bar. And that's the difference. So we know the error if you do quantum phase estimation. We also believe that quantum phase estimation is eventually more efficient on a future quantum machine. Currently, the machines are too small to sustain quantum phase estimation. And what I believe is, if you could do quantum phase estimation on a quantum computer that would allow you to represent your state, the quantum state, on a few thousand qubits, say 2000, then things would be very different for theoretical chemistry or computational chemistry, because that would basically mean that for a problem with 1000 basis function, you would get a full CI quality answer. And everything will depend eventually on whether we will get this hardware or not. And if you ask me, there's a chance to get there. Maybe it takes another 5 to 10 years, probably more or closer to 10. That's my perspective.
Wow, thank you. So we're looking forward to see your upcoming work on that matter. Before we continue, and thank you so much, Marcus. Sorry, Velina would like to make a logistics comment here. For the flash presentations, they have to be promoted to panelists, and I have to do this right now. So if you decline to be a panelist, you will not be able to present your talk. So please allow and accept the promotion to panelists. You can keep your camera and your microphone off, so nobody will hear you. But if you don't accept the promotion, you will not be able to present. So thank you. Back to Evelina.
Okay. I don't see any questions. If no, I want once again to applaud Professor Reyer for the presentation. Thank you. Thank you very much.
Thank you for having me. Thank you very much.
And we continue with the next presenter, Dr. Boris Mariasin, and which will present a talk about computationally driven organic chemistry, making theory practical.
Thank you very much for introduction and for having me here. Can you see my screen? Can you hear me?
Yes, yes.
And you can see my screen, right?
Yes.
Okay.
Thank you.
So thanks a lot for having me here. My talk will be very different to the previous one of Professor Reyer. So it will be about the application of quantum chemical methods, and namely to organic chemistry. So what can we do nowadays? I'm currently affiliated to two groups at the University of Vienna, Organic Chemistry Group and Theoretical Chemistry 1. And we try to solve the problems which usually comes from the experiment using the whole arsenal of theoretical chemistry methods. We iterate a lot with our experimental colleagues until the problem is solved. So I show it here in this catalytic cycle. I'm actually the bridge in between. And today I want to show you, like, briefly 3 projects where we discover organic chemistry with this iterative approach or bridge between organic and theoretical chemistry. The first one is about Claisen rearrangement. So the Claisen rearrangement is a textbook, old, more than 100 years old, discovered reaction with advantages and disadvantages, but still very relevant to organic synthesis. Here you see the new version of this reaction. The alkyne substituent reacts with sulfoxide. In the heart of the mechanism, we have Claisen rearrangement event. Why this very reaction is so interesting? It's a chirality transfer event. So if we have sulfoxide here, which is chiral, and we can reproduce the chirality in our alpha-related carbonyl compound, which is on the right, this is great because this compound is expensive compared to the sulfoxides. So, but there are problems, right? So one of the problems we got from the laboratory was that dependent on the substituent of alkyne intermediate, this R, we have very different enantiomer selectivity, different outcome. With alkyl chain, the enantiomer selectivity of the reaction was bad. With tetrabutyl, that was good. So why and what to do with that? And another even more mysterious problem is that depending on the catalyst, the triflic acid or triflamide, which should be only source of proton, but not, it's very important for the mechanism. We see that enantiomer selectivity was bad for TFOH and good for triflicamide. Why? How can that be? I calculated the barriers of the chirality transfer, the Claisen rearrangement event, for the path to the R product and for the path to the S product. So I show them as blue the R and the red S, this is the barriers. And I vary substituents here, as you can see with green, keeping catalyst and this X, it can be sulfur or nitrogen constant. We see that indeed we have a huge gap between the barriers in case of tetrabutyl, and for instance, it's close to 0 in case of methyl, which is in accordance with the experiment observation. And then we keep methyl and methyl constant and using enamide, right? So nitrogen, but only change catalyst. It's a triflic acid here and triflamide here. And again, there is a huge gap in case of TF2N, exactly in accordance with the experiment. So why? We want to know why. Of course, we just cannot be happy just with this. And in order to know why, we take a deeper look to the transition state structures. On the right, we see the best transition state to get the S product. On the left, we see the best transition state to get the R product. what we immediately see is that in the transition state for the S product, the methyl group, the substitute on sulfur, and the substitute from the alkyne fragment, this tetrabutyl in this case, they have to come, they're like doomed to come close to each other. And then there is, of course, steric repulsion, which makes it in general unfavorable. And on the bottom, I show you 3 trans S, so transition state to the S, to the to 3 different cases. So on the left, bad non-selectivity with OTF. On the right, the good non-selectivity with NTF2. And what we see, and this is the pure effect of counter ion, so the NTF2, the part of the catalyst, that the fragment within the transition state, they come closer to each other. The SO distance is way smaller than in the case of OTF. That means that we have tighter transition state. And that if we have tighter transition state, then the repulsion between these 2 groups is even bigger. So this makes gap bigger, huge. And then comes idea for me, for my experimental colleagues. So if this steric repulsion is so important, what about making this group on sulfur even bigger? Maybe we have even better EE. And I was very happy that indeed. So in that case, the experimental observation was that E was better. So we can design reactions purely based on the calculations. The second problem was connected to sulfoxide. So if we have special substituents on the sulfoxide, like ortho position substituted with methoxy, in addition to the normal product, which is expected, we have seen an unusual product, meta-related. How can that be if we have only 1 Claisen rearrangement transition state? And it was even favored in case of X substituent in their meta position here, chloride. And the mechanism becomes way more complicated. I show here you again only the part which is Claisen rearrangement, starting from the same intermediate before Claisen rearrangement. And instead of having 1 transition state, we have 2 transition states with a break in between. So it's completely not what expected from the consorted classical Claisen rearrangement. This blue means X equal H. In this case, normal relation product was thermodynamically and kinetically better, in agreement with the experimental observation. And the same shown on the right by red, with chloride, the same mechanism, but just kinetically and thermodynamically meta-related becomes more favorable. So we have an agreement with the experiment and we know why. Also important for me as a theoretician to say here is that this was completely done with MP2, both geometry optimizations and energies. You know, sometimes organic chemists call everything what is done in this area DFT, which is not true with DFT, for instance, fails in this case. So Claisen rearrangement is not that innocent. That was Claisen rearrangement. Now, briefly about alpha functionalization of amides. So we have amide, and it's usually difficult to do alpha functionalization of that compound. We were able to do it, and actually with very different nucleophiles using lutidine as an additive. And what the idea was is that if we have lutidine, and probably we have this enelonium, this was known in literature, published before us, enelonium intermediate, and we thought, okay, maybe it will just the nucleophile comes and lutidine comes away, and that is why we have our nucleophilically substituted amide. But actually, the scope of nucleophiles was so big is that it was kind of unclear, because even OTF, which is a very weak nucleophile, reacts. But calculations reveal what happens. Instead of enelonium, which can be computed, we have thermodynamically and kinetically warmly stabilized epoxide, extremely reactive. So without any barrier, it can react with OTF, and that's why we have in NMR the signal of our triflated product. And of course, any other nucleophile can do the same. So that's why the scope of nucleophiles was so huge. But that was only possible to understand through the calculations. And the third, so the last part of my talk today, I want to show is about synthesis of imidazoles. I find this mechanistically funny transformation, so I want to show you. Imidazole shown on the right side, and this is for some pharmaceutical, very important essential molecule, we found a way to synthesize this one using acetonitrile as both solvent and reactant, tritic anhydride, and amide again. And, you know, usually we in chemistry use so-called chemical intuition. So chemical intuition tells us nothing complicated. We have cationiminium intermediate, like for Claisen rearrangement as well. Acetonitrile comes, makes the intermediate A, and then just cyclization, and you already have your heterocyclic compound F. Yeah, but calculations completely deny this. But what was kind of clear, we thought it's like that from the point of view of chemical intuition. Actually, what calculations show is totally different. The tosylate fragment by the oxygen here attacks the carbon, and we have very unexpected exotic 7-membered ring intermediate showing here. I show it here. This one is thermodynamically not that cool, but through small barrier interconverts to the intermediate C, a cyclic one again. This acyclic intermediate does now CN bond, and then we have tosylate here with jumps, rotates like 180 degrees, making CS bond. And finally, with this new CS bond forming, we come to our product. Yeah. You know, it's my hobby, the Brazilian martial art capoeira, and what I see here, what tosylate fragment does, it's kind of similar to the wheel jump of capoeira fighter. I would call this reaction capoeira reaction like that. So the mechanism was really unexpected from the point of view of like normal organic chemistry thinking. I didn't tell you about the methods I use here. For instance, this is a classical what we are doing. It's a DFT for geometry optimizations, using of course dispersion correction and implicit solvation, and then usually we calculate energies with higher levels of theory, like in this case MP2. And of course, prior to DFT, we do always extensive conformational search. It's extremely important for flexible organic molecules. So this is a standard thing which we usually use for our studies. So I hope I was able to show you with these 3 parts of my research that that type of interconnection between theory and experiment works. And as a product of this catalytic cycle, in addition to the problem solved product, we also have the product which is new ideas usually. And this is maybe even the most important part, because we can start another catalytic cycle of iterative work between us theoreticians and experimentalists, and design finally new reactions, which of course gives us new chemical problems, which will finally will be of course solved. So today I was talking more about the left part of this bicycle. I hope next time I will show you how we design new reactions, so that the right part of the bicycle. And I want to thank the both groups I affiliated to, so the group of Professor Gonzalez and the group of Professor Maulide. And I'm currently leading computational organic chemistry research in between at the University of Vienna. And yeah, I'm happy with that. Happy to be here. Thank you all for your attention. And yeah, I hope that I will get some questions. Thank you.
Thank you. Thank you very much, Boris, for exciting talk. And I see a question. You were using SCS-MPI to study the first mechanism, mentioning that the DFT would fail.
Yeah.
A while later, you were using a bit-relib D3 setup.
No, I mean, the DFT is our like working horse. Usually it works very nice for organic chemistry. But for this very specific case, of course, we start from something easy like DFT. But for this very case, different functionals gives us different results. And this break intermediate, the DFT we're not able to find. And if they are not able to find it, but we see the transition state is extremely asynchronous, should be something in between. Then we start to go beyond. So that's why I used here NP2. But in case that if I see that the easy method like DFT works, why should I go beyond? So this is impractical. I mean, of course, it would be ideal to use for every possible question like the best ever method, but this is not a computational compromise we want. This is too expensive. So yeah, so this is always specific to the problem.
Okay, the question continues. Could you comment more precisely on why DFT fails in the first case? Is there a special reason why DFT fails?
That's very
functional level.
Yeah, that's very interesting question. I also want to know. I also would like to study by myself. So I'm actually going to publish something about that, only about the, like a pure computational paper. I mean, the different functionals I have tried, PB0, B3, Web06, they have big problems with that type of break intermediate. So the NP2 always finds it without any problem, independent on the basis set. So you increase basis set, which is actually necessary for post-Hartree-Fock method, of course, and you still have it. You use or you do not use counter ions, or you calculate it as a naked cation or as a neutral species, you have this. Yeah, but DFTs have the problems. It's difficult to say just for me right now why exactly. Maybe one of the known problems of DFT, but we will study that for sure.
Yeah, and did you ever consider approaches like RPA to have a correlation method that might be more stable when going towards more?
No, try it now.
And that you could use on top of case reference. Some reference. This is the question.
Yeah, no, we didn't.
Do you see chat with the questions also?
I'm not sure.
If you want to.
Yeah. Okay, I see the question from. Yeah. Yes, and that you could use on top of the. I mean, interesting. So we didn't try that. So maybe we can do this. Thank you.
You replied already. Okay. Any other questions? I don't see.
I also do not see more. So
if there is more questions, you can write to Boris. Thank you. Thank you very much.
Thank you very much.
Bye. And we continue, go on to next speaker, Anna Hen from University of Zurich, which will present a talk about increasing efficiency for theoretical absorption and emission spectroscopy of extended systems. Please, are you here? Yes. Would you share your presentation? Share screen. Do you see?
Oh yeah, one second, please. I switched my laptop. That's the worst you can do probably before such a conference. And now it's telling me that I should first.
Do you see share screen?
Yes. I still tried it on the other.
Don't worry, we have 2 minutes. We're 2 minutes ahead of schedule, so take your time.
Yeah, I'm really sorry. I switched laptops. I have a new Mac.
But you already shared your slides in the
yes,
rehearsal, and it was fine.
Yes.
So I don't think
just one. I will try to.
Don't worry, we have 1 more minute to start.
Yeah.
So, it's we're scheduled.
Try to get this done and open.
Really, we are in time.
Yes, we are on time. Alternatively, Anna, you could send your presentation to one of us by email and we could share it for you if you wanted to do that.
Okay, so I'm very sorry. Now it should hopefully work.
Okay, but if it doesn't, you can just email us your presentation.
You're seeing my screen?
Okay.
I'm very sorry. So thanks a lot. Good afternoon. First of all, thanks a lot to the organizers for giving me this opportunity. Sorry for the short interruption. It's nice to present our research here. It has so far been a really inspiring conference, seeing the research that has been presented today and yesterday, also including, for example, the talk by Fedor Gumans on how you can exploit time-dependent density functional theory for large-scale screening of molecular systems to tune their fluorescent properties. And I hope I can show you in connection really to this work that we now have a, I think, really promising setup in the program package CP2K that allows for an efficient and accurate treatment of absorption and emission spectroscopy, not only as it was shown yesterday for molecular systems, but also for extended systems. And since we are having a lab course in the framework of the Children's University at the University of Zurich tomorrow, where we always try to amaze young kids with showing fluorescence of, for example, this substance called fluorescein, I hope that I can really equally amaze you now in the following by showing you how fast and how efficient we can actually calculate the fluorescence of such a solid, such a substance with CP2K. Okay, so if you want to go for an efficient description of excited state properties of extended systems, the program package that you would like to choose, the theoretical method that you would like to choose, should not only give you an accurate description of the ground state, but also of the excitation spectrum and also of the excited state, really giving you access to optimized excited state geometries, adiabatic excitation energies, and fluorescence energies spectra. If you take a look at the literature, the list of available approaches reach here from highly accurate quantum mechanical approaches to relatively cheap force fields, of course, all having their advantages and disadvantages, but especially when aiming to treat extended systems, one has to say that highly accurate MRCI approaches or CAS-Ansätze would be quickly unfeasible due to the steep scaling. And then on the other hand, these cheap force fields would only have a limit transferability, especially when going from the ground state to the excited state, especially when the geometry changes upon excitation, which would require a tedious reparameterization of the force field for each excited state. That's why we decided to go for two approaches in between that I would like to show you in the following. The first one being in the framework of approximated time-dependent density functional theory, which is of course the well-known working horse when it comes to the treatment of excited states. And then the second one within the framework of semi-empirical tight binding, since this field has also recently seen a significant and really important revival in the last years. I will show you that setup that we have now accomplished based on these two approaches in CP2K for describing excited state properties. And then I hope I can convince you with showing you benchmarks, not only on molecular systems, but also on extended systems, that we now really have an efficient ansatz to get access to the properties listed here in the background. Okay, so the overall framework is time-dependent density functional theory, and more precisely, it is the so-called Tam-Dankoff approximation, which was shown to be a really robust and accurate enough method to treat absorption and emission spectra, since it gets not only the position of the peaks correct, but also the band shapes reproduced relatively well in comparison to full TDDFT or experiment. What you do within TDA is that you solve such an eigenvalue problem where you have to diagonalize an emission matrix A to get access to the excited state eigenvectors X and the excitation energies omega. In a lot of quantum chemistry program codes, these matrices, these quantities depend on the number of occupied and virtual orbitals. CP2K is special here. It has an AO-based formalism, which means that the matrices actually do only depend on the relatively small number of occupied orbitals and on the AO space. However, regarding computational efficiency, this eigenvalue problem, which is shown in more detail below here, still has really a significant bottleneck, and this is due to the contribution of exact exchange, which you might know is most expensive in comparison to the Coulomb contribution and the contribution due to the exact exchange correlation functional. This is the reason why there have been several algorithms introduced in the last decade to reduce the computational cost of exact exchange. For example, exploiting techniques of semi-numerical integration, or by defining local fitting domains as within this pair atomic resolution of the identity method. A third method that we chose is called auxiliary density matrix method, in short ADMM. And in comparison to these other state-of-the-art approaches to reduce the costs for exact exchange, it was shown that ADMM is yielding only a slightly less high accuracy. The accuracy is slightly reduced. However, when it comes to computational cost and efficiency, ADMM is simply unbeatable. And the way how you gain this speed up is by evaluating the exact exchange integrals only within a relatively small auxiliary basis, indicated here in blue, and by compensating the so introduced basis set incompleteness error by adding a first order correction term, which is based on a relatively cheap GGA exchange functional evaluated in the large orbital basis and in this small auxiliary basis. There are several ADMM variants. The one we chose, and which is probably the simplest one, is constructing the auxiliary density matrix by simply relying on basis projection, with the projection matrices being constructed out of the overlap matrix of the different basis sets. An even more efficient, but also, of course, more drastic approach is to go to the second framework that I mentioned, to go towards semi-empirical tight binding, or more precisely to the so-called simplified Tam-Dankov approximation. Looking again at this complete TDA kernel expression that we had for the TDA eigenvalue problem, comprising Coulomb and exchange contributions and contributions due to the exchange correlation kernel, the gain in efficiency is here achieved by not calculating any electron repulsion integrals at all, but by approximating Coulomb and exchange contributions using a semi-empirical electron repulsion operator, which captures by construction the correct long-range 1/r asymptotics, which is needed to get a good, well-balanced descriptions of valence, Rydberg, and charge transfer states. Moreover, exchange correlation contributions are neglected, and if you want to speed up equations calculations even more, you can also rely, of course, this excited state treatment on semi-empirical tight binding ground state reference. This STDA approach was initially set up and is also mostly tested for molecular systems, where it was shown that you can not only treat large system sizes, but due to the fact that it is only based on a minimal number of global parameters, you can also treat systems over the whole periodic table, really allowing you to go for broad applications. That's the reason why we chose these two methods within the two different frameworks of approximated hybrid functional theory and semi-empirical tight binding. And we went for excited state gradients within these two approaches using the so-called Lagrange formalism, where you start from the eigenvalue problem that I just showed you on a few slides before, and then construct the so-called Lagrangian. Based on this eigenvalue problem, adding two more constraints, which ensure first of all that the ground state stationary conditions are still fulfilled, the so-called Briand condition, and then secondly, that the geometry dependence of the atomic orbitals is taken into account when changing the geometry. The second constraint is required since our implementation in CP2K is based on a mixed Gaussian and plane-based framework. By doing so, by setting up such a Lagrangian, you no longer need the first order response of the molecular orbital coefficients, and thus you gain a really efficient expression for the excited state gradient, now being defined as the straightforward derivative of this Lagrangian with respect to the nuclear coordinate. We implemented excited state gradients for ADMM and STDA in the CP2K program package, and I think that we now really have a powerful setup in CP2K with the TDDFT module allowing you to really choose a ground state reference method amongst GGA functionals, hybrid functionals, approximated hybrid functionals, or semi-empirical type binding references, and combine this ground state setup in a flexible way with the excited state approach, comprising also this complete list of possible functionals. We benchmarked our implementations on state-of-the-art molecular test sets proposed by Jacquemin, including 35 molecules, and investigated first of all the area that ADMM introduces with respect to conventional hybrid functional DFT, showing here the area in the excited state geometries in bond length and angles for different auxiliary basis set sizes. And as you can see, a double zeta auxiliary basis set still leads to relatively large errors, while as on an auxiliary basis of triple zeta size ensures that the mean absolute error is below 0.2 picometers and that maximum errors do not get larger than 1 picometer, which I think are sufficiently good results. To compare also STDA and ADMM kernels, we also investigated the error in the excited state geometries with respect to highly accurate couple cluster reference results. And as you can see here, the STDA kernel is not performing too bad. The error spread is slightly larger than the one obtained with the ADM kernel, but still mean absolute errors are below 1 picometer for triple zeta basis sets. A similar result can also be found for adiabatic excitation energies, with the upper plot showing again the error of ADMM with respect to hybrid functional DFT, where maximum errors are really smaller than 0.1 EV for triple zeta basis sets, and the lower plot showing again the comparison of the STDA kernel with ADMM results and a conventional hybrid functional kernel, with ADMM being just on top of conventional DFT and STDA also only increasing the errors slightly, with mean absolute errors still being in the range of 0.4 EV. But I think the most important and most powerful result is really the gain in efficiency that you can achieve with these two approaches. And for this, we investigated not only molecular test sets, but also extended systems like this covalent organic framework shown here on the left, comprising 260 atoms in the unit cell. Choosing conventional hybrid functionals like PV0 would lead to memory requirements in the range of terabytes and to computational costs for the computation of 10 excitation energies or to perform one excited state geometry optimization cycle, which amount up to hours. In contrast, ADMM really reduces the requirements, memory requirements to gigabytes and the timings to minutes, so that you really have an overall gain of 2 orders of magnitude here. You can achieve another 2 orders of speed up when going to the semi-empirical setup using an STDA kernel, where only seconds are now required to do the same, to perform the same computations. We also investigated organic co-crystals, which are synthesized by combining 2 different materials using this so-called co-crystallization strategy, which is an interesting approach to really tune luminescent properties of such crystals, for example, to modify the color from green to blue, as shown in this application. To describe such systems accurately, the treatment of exact exchange would of course be desirable. However, studies often do not rely on hybrid functionals as stated here in the study, because the treatment would be beyond what is feasible. We tried our new approximated hybrid functional modules on these systems, and the results that we got for the corresponding fluorescence spectra are shown here on the left, with the table summarizing the first vertical excitation energy and the fluorescence from the first excited state. And what we found is that the error range for these systems is really in agreement with the one that we obtained for the molecular systems. However, to really discriminate between green and blue fluorescence and to match well with the experiment, you would need to choose an ADMM kernel here. And the STDA error is nevertheless within the range, as I said, of the molecular systems in between 0.3 to 0.5 eV. But again, I think the most important result here is that we can go from hours to minutes. And I hope this convinces you that the current implementation in CP2K is really a powerful tool. And this is also the main result that I would like to conclude with. I would be really happy to see the new TDDHT module in CP2K used also for more application studies. Also, for example, for such large screening studies as they were shown in the talks yesterday, either exploiting this approximated hybrid functional setup, which yields nearly hybrid functional accuracy, but drastic speed up, or going towards the semi-empirical setup, which might be beneficial, even faster pre-screening tool when, for example, going for broadband spectra. And with this, I would also like to come back to the example I showed in the beginning with the green fluorescence of fluorescein. And I hope you can agree that I think it's kind of amazing that we can now achieve with the ADMM or STDA at ADMM ground state reference setup to perform a excited state geometry optimization cycle for such an extended system within 5 minutes, or calculate a broadband spectrum of 500 excited states corresponding to 6 eV, several hundred nanometers within 10 minutes. And with this, I would really like to thank my collaborators for this nice, fun work, and you for your kind attention.
Thank you, Anna, for interesting talk and for your presentation about new approach and really very efficient. And one question, Anna, what are the main approximation of TDA, and in which cases does it not? In which cases does it not work? Do you see the chat also, the message in the chat? You can read also the questions?
Let me see.
Below chat. Okay.
Yes. Where's the mean of STDA? In which cases does it not work? So, I mean, the main approximations of STDA are clearly that you don't calculate the electron repulsion integrals, but that you approximate them using this semi-empirical electron repulsion operator. This is, of course, introducing some empiricy. You introduce empirical parameters, and for that, you no longer have an ab initio treatment as you would have within, for example, within TDDFT. However, I think STDA is doing quite good. It's only having really, as I said, a limited set of global parameters, and it can be used without needing any bond-specific parameterization or whatever on each system that you would like to choose. It depends a bit, I think, on, from my experience that I have now from calculating extended systems, it depends a lot on the amount of exact exchange that you choose within this setup. So if I can go back to the slide where STDA is explained, you see here a relatively general formula of how to re-express the electron repulsion integrals, the Coulomb or exchange contributions using this electron repulsion operator. And this is done differently for Coulomb or exchange contributions, and the exchange contribution includes also such a scaling parameter for the exact exchange. In the original work by Grimme, they optimized this parameter based on the molecular test set that they found. And from my experience, this scaling parameter needs to be chosen really dependingly on the chosen ground state reference. So you really have to ensure that the amount of exact exchange that you include in the excited state treatment is well balanced to the amount of exact exchange that you have in the ground state treatment. And depending on that is also the accuracy of STDA. But of course, you would also like to see more. I think to be able to also reply to this question regarding on which systems you could try to address and so on. One also has to say that we would need more.
There are more questions
of extended systems.
Okay, there are more questions about STDA uses some parameterization, at least in Grimme's version. Do you also parameterize STDA?
Do I also reparameterize STDA for the extended systems? I'm sorry, could you please?
Just this is not the
questions are in the Q&A. You can also see them.
Q&A. Do you see the questions in Q&A?
So I see that
below.
Yes, I see it.
Okay, you can open.
So we use the same parameterization as Grimme. We just took the same parameters as they did for Grimme. Maybe I think I have, it's not so many parameters. It's basically the hardness, the chemical hardness that you have for different systems. And we use the same parameters.
Okay. There's any references that had used the ADMM for heteroconjunction maybe structure. Is this method accurate for the study of plasmonics excitations and maybe de-excitation? Maybe.
So I never studied plasmonic excitations. And I am not aware that ADMM was used already in this regime. But you would certainly, I think there's no reason for that. I'm sorry for that.
Okay, I think that's
Anna, there's more questions for you in the
okay.
chat as well as in the Q&A. You could go on and answer the questions in the chat and in the Q&A in writing.
Yeah. Questions from, okay, is it possible?
Evelina, we need to proceed because we're a little behind. So Anna can respond in writing.
Okay.
Let's
okay.
go to the next talk.
We have no time. Okay, thank you very much, Anna.
Thank you as well. Okay, I will respond in writing. Thanks again for the
Thank you. Thank you. And we continue with the next presenter, Professor Daniel Escudero from Catholic University in Leuven. And the title of his presentation is Benchmarking Excited State Decay Rate Theories.
Anna, can you stop sharing?
Anna?
Yeah, that's great.
Okay.
Now I should be able.
Hi, Daniel.
Good afternoon, everyone.
Good afternoon.
Let me go to the, so this is the presentation. Okay, so first of all, can you hear me, all of you?
Yes, perfect.
Thank you. So thank you very much to the organizers, especially to you, Zoe, and to the rest of organizers for giving me the chance to talk today. So as Evelina was just mentioned, so my talk today is about benchmarking excited state decay rate theories. So it's again another talk about excited states. So my field of research is computational photochemistry. And the answer we want to get by the end of this talk is whether we can already get semi-quantitative determinations of photochemistry. So what do we mean with semi-quantitative determinations of photochemistry? Of course, we just saw that for molecular systems and beyond, as we saw in the previous lecture, we can get fluorescence spectra. But if we want to get time resolved information and quantum yields of the photoprocesses, so lifetimes of the excited states, radiative rates, non-radiative rates, then we need to go beyond quantum chemical methods for the excited states. And in the community, we have two approaches. So we could, in principle, perform quantum dynamics or non-adiabatic excited state dynamics. But of course, those methods are still very expensive. So, and if we want to model processes that occur beyond the picosecond regime, like fluorescence and phosphorescence, then we need to go for a static approach. So in this static approach, what does it consist? So we're gonna combine state-of-the-art quantum chemical methods to get excited state information, yeah, about the geometries, the energies, the gradients, the Hessians, vibronic couplings, spin-orbit couplings, so on and so forth. Then we will need to rely on diverse excited state decay rate formalisms that will give access to radiative and non-radiative rates, basically based on Fermi-Golden rule expression. And then we will need to develop realistic kinetic models and derive the kinetic master equation. So very simplistic here for fluorescence coming from S1. So basically that means we will need to determine these two rates, yeah, the internal conversion rate and the fluorescence rate. So what's the current challenge from this static approach? It's actually the non-radiative deactivation decays, yeah? So we have two types of situations, yeah, in photochemistry. On the left-hand side, we have the weak coupling regime. So that means that the excited state and the ground state potential energy surfaces are nested. And therefore here, the mechanisms of non-radiative decay is due to the overlap between vibrational wave functions of both states. So this is the case where we do not have no large amplitude motion. So we're talking about semi-rigid molecules, fluorophores, basically, yeah? So small reorganization energies. So what happens in the strong coupling regime? So in the strong coupling regime, the potential energy surfaces are not nested anymore. So we have real crossings and we have non-adiabatic phenomena, yeah? So the non-radiative decay here is ultra fast. Yeah, so basically the static approach is gonna be only applicable, so to say, in the weak coupling regime. So the situation, this is simple, but it can be as complex as you can imagine, yeah, because we have developed, for instance, computational protocols to predict the photoluminescent quantum yields of those type of molecules. And actually, also for organic molecules, you have higher line excited states, and basically you may have even the two type of mechanisms at the same time. So the first task is to explore the excited state potential energy surface. So if we do not have information about it, so beforehand, it's difficult to predict whether those methods are applicable to a situation or not. So let me go to the excited state decay rate theories in the weak coupling regime, of course, for these semi-rigid molecular systems that we're going to use. So we're going to evaluate both the internal conversion and the radiative rate with excited state decay rate theories that are based on Fermi-Golden rule expressions or perturbation theory. So here we have the interacting Hamiltonian between the final and initial states, von Oppenheimer states, which basically we have here the non-adiabatic couplings. So applying Condon approximation, we can split the nuclear from the electronic degrees of freedom. So we have here finally expression for the internal conversion in this case, for instance, that depends on the partition function of the initial vibrational state that runs over all vibrational states of the initial and the final state. And we have also the nuclear momentum operator and also here the electronic, so to say, non-adiabatic coupling. So there are different ways to evaluate this. So we have a time-independent approach. So that means that we're going to do a sum over states expression here, this Dirac delta function, which we can also simulate with broadening, yeah, which can be of Gaussian or Lorentzian function. So if we Fourier transform, so to say, this expression, we get this analytical expression over here. That we get this, so we go from the energy to the time domain. So we get this time vibrational correlation function for internal conversion. So this is what it's called in the community time-dependent approach, where temperature effects are taken into account. So basically here we're using a multidimensional harmonic oscillator model. So this type of adiabatic Hessian. So we consider the geometry, some vibrational modes and frequencies from both the excited state and the ground state, coupled to quantum chemical calculations. Yeah, so we will introduce those as ingredients in those rates, where in this adiabatic Hessian model, we are including displacements, distortions, but also the Chinsky rotations of the potential energy surfaces. So how those ground state and excited state coupling modes connect to each other. So basically we need ground state and excited state geometries, vibrational modes and frequencies, non-adiabatic couplings, so on and so forth. And for that, basically for the Hessian, yeah, because we have analytical expressions for the second derivatives, we are restricted basically for, at least for the geometric and Hessian part of the DFT. So what about the radiative rate? So radiative rates in principle, we can estimate very easily for an instant spontaneous emission that depends on the square of the gap, or also by integrating the computed emission spectra. There is also basically a thermal vibration correlation function, in this case for radiative, yeah, rate, where basically the term that comes here into the perturbation is now this transition dipole moment between the final and initial state, which we can express in a zeroth order expression, so Frank Condon only, or by doing a Taylor expansion and including Hertzberg-Taylor effects. Yeah, so basically how those transition dipole moments change with respect to the nuclear degrees of freedom. And then by integrating this spectra, then we can get the rate. So we have applied this this static approach for azulene. Azulene is a very quite rigid molecule, yeah, and to study precisely whether we could have an insight into the anti-Kasha emission of azulene. So anti-Kasha means that we are going to emit from a higher line excited state instead of S1. So as you can see, those are the experimental findings. There is only experimentally, it's only observed this S2 to S0 emission. So this is the kinetic model then we have to use, yeah, for such a situation. And these are the kinetic master equations based on a few approximations over here, yeah. So basically we have to evaluate 6 rates at the same time. So 3 internal conversion rates and 3 radiative rates. So this is what we're gonna do. But first, we want to benchmark these excited state array theories. The first way to proceed is to push the accuracy of the quantum chemical calculations. So here in this slide, this is the work of Kumbase that did those calculations for these azulene molecules. And we push the theories to high-level ab initio ADC2 calculations with respect of TDDFT. So the conclusion is that, of course, for the non-radiative rates, those are the most challenging ones, they depend exponentially on the gaps, on the energy gaps. So only with ADC2 we were able to obtain a good S2 to S1 WAP, and therefore the rest of calculations are going to be based on the energy gaps, transition dipole moments, based on the ADC2 data. So the first thing we want to say is, are we able to simulate the vibronically resolved absorption and emission spectra? And here you have the experimental ones and the computed ones, with such a procedure. And you can see that for S1, Frank-Condon approximation is perfectly fine, but if we go to S2, this is the Frank-Condon here in the middle, and this is the total one, which includes Herzberg-Teller. So in the case of S2, Herzberg-Teller effects were really important to reproduce the S2 band. So for the moment, we see that for the spectra, so we have to benchmark a little bit, some of the settings. What about the radiative rates? So we integrated those Frank-Condon spectra, and those are the values we obtained. So in between parentheses, you see here the experimental values. So we are about in the same order of magnitude than the experiment ones. So both for S2 and S1 and S1 to S0. Here, S1 to S2 to S1 is negligible, because the adiabatic gap again is smaller than in the case of S2, S0. So what about internal conversion rates? Well, those are the challenges. And as I was mentioning before, we have an exponential dependence here on the energy gaps. So that means that we need to be really accurate in the S2 to S1 gap here, basically. So you see that with all these settings, of course, we had to obtain also the non-adiabatic couplings between excited states that in that case they were not available with ADC2, so we moved to CIS, but that was benchmark and there was not a problem. So we obtained the internal conversion rates, which again, as we can consider this as a success. We will see that it's very tricky to get those internal conversion rates really accurate, and they are about of the same order of magnitude, or one order of magnitude difference, as compared to the experimental ones. Of course, this is where I show you that high-level ADC2 calculation do really make a difference. Only when we move to ADC2 values here, compared to TDDFT, we get really accurate values. So those are kind of 2 order of magnitudes, in some cases overestimated. So put everything together, finally we could understand, and using those kinetic master equations, why this molecule azulene possess only anti-Kasha emission. So we got the yields from S2 and from S1, which really correspond to the experimental ones. So some of the trends, even within the series of compounds, were recovered, but the take-home message is that the combination of this state-of-the-art electronic structure calculation with excited static array theories and kinetic modeling can be used to obtain semi-quantitative determinations of photochemistry, of course, for semi-rigid molecules. Of course, everything is based here on the harmonic approximation, so we'll see that there will be some challenges. So the idea is not, we have seen that obtaining a good accurate for the electronic structure part is important. So what about the vibronic part? So can we systematically improve the accuracy of the spectrum of the rate calculations? Basically, the point here is that we have those fitting parameters for the rate calculations that are not implemented in all possible quantum chemical softwares. So we did the evaluation first whether the combination of the quantum chemical part software and the vibronic part software was really coherent. So we did that for anthracene molecule. So we can see that finally after quite some work, because not all these softwares, for instance, have the same type of, so to say, grids for the convergences and things like this, but finally we managed to get the same results. And now we want to test the vibronic parts, the other parameters and variables. So adiabatic Hessian, this is the preferred one, as we mentioned before, but what about harmonicities? Are they important? It's important to use Cartesian instead of internal coordinates. Is it better to use a time-dependent versus a time-independent approach? What about if we switch off on Dushinsky rotation effects and Hertzberg-Teller in a systematic way? What about the broadening? Yeah, I was mentioning whether on off, which is the broadening we have to use. Yeah, so this is a work by a PhD student of the EuChemS, Manon Busquet and Kumbe is my PhD student. So very briefly, for instance, what about time-dependent versus time-independent approach? For instance, here for anthracene molecule, this is the experimental spectra. So we can see that regardless whether we use a time-dependent or time-independent approach, so some of our states approach, we get converged, so to say, radiative rates over here. So those are basically the details. Yeah, so we move to FC classes because that's the one that we can systematically change all those parameters. This is the program by Javier Ferez and Fabrizio. So what about using Frank-Condon versus Hertzberg-Teller approach? That of course the expansion can be expanded in the initial modes, which this is what it's represented here in the final modes. So you can see that here maybe it makes a bit of a difference, yeah. But basically, if we analyze the rates, yeah, so we have kind of a bit disagreement, yeah, so to say. So we're getting closer to the experiment, but still we're a bit off to the experiment. So let me tell you that this is still in the gas phase. Those are ongoing investigations, and we still need to push maybe the theory here. So we're using TVDFT, for instance. So let us investigate.
Daniel, we have to finish.
Yeah, so I'm finishing. So this is the effect of broadening, which was very important for the internal conversion rates, but not for the radiative rate, whether Gaussian or Lorentzian, and also choice of coordinate system. So I'm sorry that I took a little bit more of time. Other models. So let me go to the conclusions. So semi-quantitative predictions of complex photochemical scenarios for semi-rigid molecules are possible. We have strategies to improve the accuracy in the radiative and non-radiative rates. Of course, this is ongoing. Computational protocols for the radiative is robust, but for non-radiative is a bit more challenging. So we are evaluating maybe to use an harmonic effect. And we need models for molecules with large amplitude motion. So very different excited state and ground state geometries. Let me thank, of course, the students involved, Manon, the PhD student of Denis and Kun, and all of you for your attention. I'm sorry for it if it took more time. Thank you.
Thank you very much. I think we have a bit time for some question. No question at the moment. Soon we will receive a poll to vote for the best presentation in this session, electronic structure, for all attendees.
Yeah, I mean, if anyone has a question for Daniel, I don't know if our chair has a question, but if not, if you have a question for Daniel, please post it in the Q&A and he will be answering in writing. Or if you have a question, type it now.
Chat, maybe. Mm-hmm.
Okay, we don't have a question. So
thank you very much.
Thank you.
Thank you. If not, you can write. Thank you very much, Daniel. Thank you. And now will be the poll for the vote of the best presentation in this session, electronic structure. Okay, we'll wait. Okay, please vote for the best short talk.
Yes, and may I remind also the scientific committee to vote for their preferred talk internally, so that at the end of the day, we will announce the winners of the best award from the scientific committee, as well as the best award voted by the audience. So the poll is still open. Please vote. We have 1 more minute. You have the chance to vote and select your best talk. And may I ask all the flash presenters to get ready? I have tried to promote some of you as panelists, but you are not accepting the invitation. If you don't accept the invitation, Charlotte and Maria, you will not be able to present. So please accept the invitation to be promoted to panelists. We will now go on a break, a 10-minute break. We will start at the flash presentations. We will start at 6 p.m. sharp. So we go on a 10-minute break. Yes, Maria, I'm asking you to promote to panelists. You will see a chat box on your screen. Please accept it, as well as Charlotte from the University of Namur. Yes, we go on the break. We will close the poll. We just closed the poll. We have a winner. We will announce the winner at the end of this day. And we now go on a 10-minute break. During the break, if anyone wants to stay on, I will be presenting the European Open Science Cloud, as was announced earlier by Peter Salai, so that our division, the division of Computational and Theoretical Chemistry of the European Chemical Society, supports the European Open Science Cloud. So we go on the break for 10 minutes. Anyone who wants to stay on, I will be presenting the European Open Science Cloud in 1 or 2 minutes.
Thank you once again for all presenters of our session, Electronic Structure. Thank you.
Tu disais?
Okay, may I ask you to mute, if possible? So I'm just gonna mute people who are unmuted, and I'm going on to share my screen. And speak a little bit about the European Open Science Cloud. As mentioned, our division is supporting the European Open Science Cloud. And I want to share with you a few details about what the European Science Cloud is and how everybody can benefit from it. So in the past decade or 20 years, we had a model of the European data infrastructures where everything was fragmented, data computing, storage, applications, and software. You see here EGI, UDAT, GEAN, OpenAir. Everything is fragmented. Also, the public institutions, commercial providers, databases such as the one hosted by EBI. The European Open Science Cloud vision is to go from fragmented and uneven access to information and services to a federated model where access to all the data, services will be universal. So with the European Open Science Cloud on a portal, based on the portal, you will be able to have access in all the services instead of looking every time for a service, for applications, computing, software, storage, and data. And that will proceed materializing through the EuChemS service catalog. So the European Open Science Cloud is one federated platform for producing, curating, distributing state-of-the-art, findable, accessible, interoperable, and reusable data, scientific data, which hopefully will enable us to have interdisciplinary research. We saw one big example of that during the COVID time, how the vaccine was able to be created in a very short time, and also new medicines are now in clinical trials, and everybody was contributing structural data and every kind of data, posting thousands of archive preprints, which we were able to use all this data to proceed very fast. So essentially, here what we want to do is to develop an internet of fair digital objects and to offer researchers anywhere in the European Union the resources that they need. So to facilitate this process, the European Open Science Cloud has regional projects. So every country in the European Commission, and some more countries, actually associated countries, can contact their own members of the European Open Science Cloud. So essentially here are the regional projects. So EuChemS Pillar contains Italy, France, Germany, so many countries that are basically in Central Europe. Then we have the EuChemS Synergy with Spain, Portugal, Poland, UK, so more countries. We have the EuChemS Nordic, all the Scandinavian countries and Iceland that are connected through this project. And then we have the Balkans together with Armenia and Georgia and Cyprus. So the EuChemS project for the Balkans and associated countries that you see here is called NIFOS Europe. So every single project is a member of the European Open Science Cloud, and every country has a representative, which you can find in our portal, and you can essentially contact the people there to give you access to storage, manage an analysis of produced data. You can share your data sets. You can access data sets from colleagues without duplicating data. You can use more efficient dataset searching based on metadata. You can actually onboard, if you have a software and you want to create a web server, then you can onboard your service through the European Open Science Cloud. So if you contact your country representative, they will help you. They will tell you how you can do this. So there's also help and evaluation with certification of datasets, training on best practices, and all of that, of course, will enable open innovation. So some examples of how you can bring a software to the European Open Science Cloud. And actually here, for example, I'm showing that we had a thematic service called the GemBio server, which is used for post-processing of virtual screening results, which with the help of NIFOS Europe, the European Open Science Cloud, we were able to build a web server and onboard this service onto a central portal where everybody can use our service. So it is quite important also for people who are writing software to give this software as open access or as a web resource into the European Open Science Cloud, so that you can publish, share, and advertise your services. The European Open Science Cloud will provide statistics about access of your service and feedback. This will be a free online platform to manage your service requests, and you will be able to interact with your users more efficiently and understand their needs. You will get support for user authentication, so you can open your service to a wider base and boost visibility and discoverability of your service, and also increase your computational power of your lab, because EuChemS is also providing computational resources for you. One example is through the COVID-19 Fast Access Channel, where we give access, we provide access, fast track for generic services, computational, high performance computing and cloud, data analyzing tool, storage services, thematic services. So you can apply to that service using this email in IFOS Europe, but also for all the European countries, please refer to your country representative and they can help you to use actually the services provided by the European Open Science Cloud. And I would like to close this very short presentation with mentioning that global open science can be a driver for new, transparent and data-driven science that will accelerate innovation, and as we have seen this in the case of COVID. So it is really a big opportunity to use the European Open Science Cloud to make your data findable, accessible, interoperable and reusable, as well as your software, and also to use it for computing. So thank you very much for your attention for this very short presentation. So I will close this now. And in 2 minutes, we can proceed with our flash presentations.
So, welcome back, everybody, after this very, very short break. But I hope you have had some recovery from this very long session. But I think this is a really exciting program that it's really worth the time staying in here. So my name is Stefan Kast. I'm German representative within the DCTC of the EuChemS, delegate from the German Chemical Society. And it's my honor to host now this and to chair this first flash talk session of today. So just to give you some advice, as yesterday, you have exactly 4 minutes. And that means we have to be really sharp. You have to stay on time, because otherwise I would need to cut you off in one way or the other. And please also recall that questions should be asked through the Q&A panel. And all presenters are advised to really look at these questions and try to respond in writing. So I hope everybody can see the slides. I'm going to share the slides, and please tell me, next slide, please, as it was in the old days. So many of you will not actually recall how it was when there was somebody in the back to actually change all these slides. But please tell me, and I will try my best to be on time to do that. So our first speaker of this flash talk session is Nicolas Chéron, and he's from the Département de Chimie in ENSPSL CNRS Paris in France. and he will talk about binding site of bicarbonate in PEP carboxylase. So the stage is yours.
Hi, thank you, Stefan. Good afternoon. So the world population is strongly increasing, as you can see by this number on the top right of the slide. And very soon we'll have an issue to provide food for all these people. So one very optimal solution will be to increase crop yields, and that means performing bioengineering of photosynthesis. So if we go into the details of photosynthesis and the carbon capture part of photosynthesis, we see that 23% of terrestrial plants uses a mechanism where CO2 is first hydrated to H2O3- bicarbonate in purple in the diagram in the middle. And hydrated CO2 react with the molecule PEP to become another molecule OAA, which goes in another cell and react and then is fixed by the organism. And the key enzyme here is called PEPC. It controls the carbon flux, but we still don't know it very well. We don't know the loop motion, we don't know the rate determining step, so we want to study it. And strangely, we don't know where the bicarbonate is binding. So we want to study it. Next slide, please. Thank you. So what we've performed is we took the enzyme, we placed bicarbonate at 20 different positions around the enzyme, and we pushed bicarbonate inside the enzyme, doing 20 different simulations. And at the end of each simulation, we let bicarbonate evolve in the active site during 100 nanoseconds. And we found that bicarbonate can populate 6 different pockets that you can see here in different colors. And then we wanted to rank these different pockets. So next slide, please. Thank you. So first we tried stirred MD and umbrella sampling, and it didn't work. So we relied on alchemical transformation with FEP, which is a way to compute very accurately the binding free energy according to the diagram in the top right. So to keep the bicarbonate in each pocket, we've used a flat bottom potential with plumed, and on each pocket we've used 3 different starting points, and we've computed the binding free energy in each pocket. So the error for each single simulation is below 0.5 kcal per mole, and you can see in the table with the results that if we look at the 6 different pockets, one of them, called P6, is way more stable than all the other by almost 3 kcal per mole. So the binding free energy is minus 5.3 kcal per mole. And if we compare that to experiments, we have access to Km. Km can be roughly said to be equal to Kd, and we are in a very good agreement between experiments and computations. So now we know that bicarbonate is going in the P6 pocket. So now we can look at the reactivity of this enzyme, and we will try to find the rate determining step and perform then bioengineering. And yeah, this will be published or submitted very soon. Thank you.
So thanks a lot. So to be more precise, you have exactly 3 minutes, but I mean, we don't need that much time between changing presenters, and that means you have maybe a bit more, but don't try to. So the next talk will be from Charlotte Bouquillon. She's from University of Namur, and she will talk about multi-scale theoretical investigation of the second harmonic generation of a specific molecule in unsaturated lipid bilayers, and specifically about the effect of the cholesterol content. So we're happy.
Okay, thank you for the introduction, and hello everyone. So I'm Charlotte Bouquillon and I'm from Namur, Belgium, and today I will talk about the effect of the cholesterol content on the second order nonlinear optical responses of diethanate embedded in phosphatidylcholine lipid bilayers. So first, we study cell membranes because of their importance. Lipid membranes perform diverse and essential functions in our cells, and those functions are controlled and enabled by the vast lipid structure diversity. Here we focus on two main classes, glycerophospholipids and sterols. And more specifically, the glycerophospholipids, you can see DPPC, POPC, and DOPC with various levels of unsaturations, and also the cholesterol molecule. One technique able to study the membranes is the second harmonic generation. It is a process where pairs of incident photons of frequency omega are converted into photons of frequency 2 omega. And this technique is specific to interfacial regions like the lipid bilayers, and it also presents low photodamage and photobleaching. Also, most biomolecules possess few groups with exploitable nonlinear optical properties, so that generally we use exogenous dyes to improve the contrast in the tissues. And here the chromophore is called dietanates. The first step in our work is to perform the molecular dynamic simulations of the dyed lipid bilayers and to extract snapshots. And then on these snapshots, we compute the molecular SAJ response at the QM level. And so for this, various systems with various concentration of PC lipids and cholesterols were created. From pure PC systems to systems containing nearly 66 cholesterol mole fraction. Next slide, please. Thank you. And so by analyzing the structural parameters of the bilayers, we observed on one hand what is known as the condensing effect of cholesterol that had an impact on the alignment of the lipid as well as on the alignment of the probe. And this induced an increase of the NLO response. And on the other hand, we also observed the disordered effect of the double bond, which had no impact on the alignment of the lipid or the probe, but also resulted in an increase of the NLO response. And all in all, this is a solid foundation and a tool to be able to determine the composition of a given lipid bilayer based on the NLO response of the embedded dye. Next slide, please. Thank you. And so I thank you for your attention. And if you want more information on this subject, you can find them in our recent publication presented here. And also don't feel free to ask questions in the chat or directly via email. Thanks again.
Yeah, thanks a lot. And we are absolutely perfectly in time. So we can directly move on to our next speaker, and that is Pierre Beaujean. And he's from the Laboratoire de Chimie Théorique, again from Namur Institute of University, Institute of Structured Matter, and he will talk about all atom quantum mechanical calculation of the second harmonic generation of fluorescent proteins. So there's some relation. Stage is yours.
Thank you for the introduction. So good afternoon. My name is Pierre Beaujean and I'm from University of Namur. And today I would like to introduce you to our latest results. As Charlotte mentioned in the previous presentation, we are interested in second harmonic generation, so a process when two photons of frequency omega are converted to a photon of frequency 2 omega. And this photon is exploited in many different techniques, including second harmonic imaging microscopy, which is a microscope technique, when we probe the material using this phenomenon. And for that, we need to use a biotag, which allow to focus on the part of the material which is in which the biotag is formed. At the molecular level, the second harmonic generation response is controlled by the beta tensor, which is defined as the second order response of the molecule to an electric field, as you can see in the equation below. And we would like to compute the beta response of fluorescent proteins since they have been recognized and they are used as a promising biotag for second harmonic imaging microscopy. Next slide, please. Thank you. And to do so, of course, we had to do approximation to make choice. So we used the GFN2 XTB method, which is a tight binding approach for the geometry optimization. And we used the simplified TD-DFT as developed in the STDA code that was presented in the previous session. And we reparameterize this code so that it can be used to compute beta. And as you can see on the bottom of the slide, you have the beta response for the bacterial rhodopsin. And you can see the experimental frequency dispersion in blue, the extrapolation in red, and our calculation result in green that follow well the extrapolation for the low energy part. So we are quite happy about that. Next slide, please. So if you want to know more, I advise you to read the paper for which you can find the reference at the bottom of the slide. But nevertheless, the main conclusion are that we are not able to compute the beta response for large structures such as fluorescent protein. And now we would like to apply this methodology to further compute beta for the protein and then propose new improved structure with nice beta response. So thank you for your attention.
Thank you, Pierre, very much. Very interesting. And we can directly move on to the next talk that will be given. Oh, I'm sorry, this was the wrong. That will be given by Maria Renoir. I hope I have pronounced it more or less correctly, about mechanistic and electronic structure aspects of a hydrolysis of a glutamate derivative by glutamate carboxypeptidase. So the stage is yours.
Good afternoon. I'm happy to share my results on this topic. Next slide, please. Here is the reaction that we studied. It's hydrolysis, a C-N bond cleavage in the main chain of N-acetyl-aspartyl glutamate that converts to N-acetyl-aspartate and glutamate. We utilize molecular dynamics simulations with the combined quantum mechanics, molecular mechanics potentials. Importantly, we use quite high level of theory in the QM subsystem, namely hybrid functional PB0 and all electron double zeta potential basis set with the polarization functions. So what we found is that this reaction happens in 4 elementary steps, and using umbrella sampling, we obtained the standard GIPS energy profiles of each elementary step and found that the first is the nucleophilic attack of the OH minus, and then the proton rearrangement happens, and the latter stage is the C-N bond cleavage. Next slide, please. Another topic that we were interested in is the mechanism of substrate activation. And to study this, we analyzed not only the wild type enzyme, but also its mutants that are less catalytically active. I mean that they have lower kcat value. And here is the activation. What we mean by activation, it's the polarization of the CO bond of the substrate due to the formation of coordination and hydrogen bonds with the neighboring groups. So we can study this from the geometry viewpoint. We performed MD simulation of the enzyme substrate complex and found that the distances distributions of the oxyanion hole formed by zinc cation and tyrosine are responsible for the differences, variations of the catalytic properties. Also, the same conclusion can be obtained from the natural bond orbital analysis. We found these so-called reactive species, the electronic structures and biostructures corresponding to the lone vacancy on the carbon atom and 3 lone pairs on oxygen atom that are an activated structure. And also another way to find this activation process is analysis of the Laplacian of electron density maps. Namely, on the left graph, we can find the reactive species that corresponds to the area, well, that depicts the area of electron density deconcentration in the region of nucleophilic attack, so on the line between the carbon and oxygen nuclei. And in the non-reactive species, we can find only electron density concentration area around the carbonyl carbon atom. Thank you very much.
Thank you. Still perfectly in time. So we can directly move on then to the next talk. Will be given by Sergei Katsyuba from the Arbusov Institute in Kazan in Russia, collaboration with Stefan Grimm in Bonn, about how to simulate infrared spectra of conformationally flexible molecules in liquids and in hydrogen bonded solvents. So
thank you for presentation, Stefan. Well, dear colleagues, nowadays experimental infrared spectra are almost routinely interpreted by comparison with spectra quantum chemically simulated for isolated molecules. This gas phase approximation doesn't work in the case of spectra of aqueous solutions or other solutions where hydrogen bonds are in action, because hydrogen bonds with the solvent strongly influence the infrared spectrum of the solid. This problem may be tackled within the framework of ab initio molecular dynamics, but this is bloody expensive. Recently, we have developed a much more economical approach to accurate quantum mechanical simulation of the infrared spectra of such systems. We combine implicit and explicit treatment of media effects. First, about the implicit part. We generate liquid state conformers using the novel sensor protocol developed by Grimm and calculated Boltzmann populations for each implicitly solvated single conformer. Then we explicitly solvate each conformer with the first shell of solvent molecules using an automated cluster generation algorithm and calculate the infrared spectra of the conformers at the DFT level. Then we average the spectra of significantly populated conformers using Boltzmann factors obtained with Stenzo. Next slide, please. Liquid ethanol is a representative example of results of our approach. The spectrum A is simulated for the cluster formed by anti-conformer of ethanol. B, the same for the gauche conformer. C is the sum of the spectra A and B weighted with Boltzmann factors from Stenzo. And D is the experimental spectrum of liquid ethanol. C and D match each other quite well. We can even distinguish the spectral markers of anti and gauche conformers, despite the strong effects of hydrogen bonding blurring the infrared spectra of the conformers. Next slide, please. Methyl lactate in water is an even more complex system. Here the intra and intermolecular hydrogen bonds compete with each other and strongly influence both the conformer structure and their spectrum. Applying our protocol, we were able to show that not only relative abundance of the conformers, but even their structures change dramatically. You can see that intramolecular hydrogen bonds are replaced by intermolecular hydrogen bonds with water. The whole procedure of spectral simulation for this rather complex system took only 2 hours on 14 processors. With when we used the highly efficient battery leap 3C computations. The quality of the spectral simulations was practically the same as in the case of much more expensive DFT methods. The computations are even faster if we use B97 3C functional. Application of these composite methods becomes progressively advantageous with increasing the size of the system. Thus, these methods are recommended as the methods of choice in the case of modeling infrared spectra of drug-like molecules or biomolecules. Thank you for your attention.
Thanks a lot. Very interesting approach that I personally will continue to discuss maybe with you and Stefan. So the next talk will be given by Gudel Rose from the glycobiology unit of University of Lille in France. And she will talk about histidine versus cysteine bearing heme-dependent halogen peroxidases, parallels and differences for chloride oxidation. So we're looking forward to your talk.
Thank you very much for the introduction. Indeed, I'm going to present on chloride oxidation by histidine and cysteine bearing heme peroxidases. We studied in detail human myeloperoxidase. It's a key protein in the immune defense system. It's a heme protein, and its porphyrin ring, which you can see here, is covalently attached to the protein with 2 esters and 1 sulfonium linkage. It bears a proximal histidine, and it can produce strong oxidizing agents. It can do chloride oxidation at the same efficiency as chloroperoxidase at pH 7. Chloroperoxidase is a cysteine-bearing heme peroxidase. And the fact that myeloperoxidase can perform the chloride oxidation is a unique feature of myeloperoxidase. Can you change the slide, please? Both the myeloperoxidase and the chloroperoxidase catalyze one and two electron oxidation reactions. So here is a 2 electron oxidation, here is a 1 electron oxidation pathway. In both pathways, the peroxidases undergo a series of redox reactions. In the 2 electron pathway, the native enzyme is recycled back directly from compound 1 in a single step 2 electron process. In the 1 electron pathway, the native enzyme is recycled back from compound 1 through a sequential 1 electron reactions. Halogen oxidation is a single step 2 electron process, and the 1 electron oxidation reactions are futile and needs to be avoided. Yes, can you change the slide, please? So for the cysteine bearing heme proteins as chloroperoxidase, it has been described before, for example, in that reference, that installation of the negatively charged cysteine thiolate as a proximal ligand shifts the equilibrium towards the 2 electron pathway. This is referred to as the push effect of the negatively charged proximal ligand. For histidine-bearing heme proteins, as histidine is neutral and not charged usually, they operate through 1 electron reactions and are thus unable to catalyze chloride oxidation. The exception forms myeloperoxidase. Here, the hydrogen bonding environment consisting of asparagine and an arginine shifts the equilibrium towards the 2 electron pathway by the deprotonation of the proximal histidine. And this makes that myeloperoxidase can perform the chloride oxidation. And you can read all details in the reference given below. Thank you very much.
Thank you. So we are again in time. So we saved some time during the last talk. And I'm happy to now announce the next talk will be given by Shaima Hashem from University of Pisa, working with Benedetta Minucci. And she's going to talk about from crystallographic data to solution structure of photoreceptors, the case of Ab-A-Bluff domain. The Bluff domain.
Thank you very much for your introduction. So I'm Shaima Hashem from the University of Pisa. I'll talk to you about our recent investigation on Ab-A-Bluff domain, and I will show you some of our main results. Next, please. So APA is one of the most important proteins of the blue light using flavine photoreceptors that is involved in the photosynthetic gene regulation. This protein contains flavine as chromophore, which upon excitation induces a conformational change in the protein, changing it from a dark resting state into a signaling light state. And this transformation from dark to light is seen as a red shift of 10 nanometers in the absorption spectra. This transformation has also been known to arise from the rearrangement of a hydrogen bond network between the flavine, the glutamine, and the tyrosine in the binding site. Next, please. But since this rearrangement of hydrogen bond network couldn't be visualized experimentally, two models were suggested in order to describe it. The first model proposed that the light state was formed due to the rotation of the glutamine. However, the second model proposed that there was a tautomerization of the glutamine instead. Next. So there are two conflicting X-ray crystal structures that were resolved that actually both of them represent the dark state of APA. The first one contains a tryptophan inside the binding pocket and is known as trypin structure. And the other one contains a methionine instead and is known as met-in structure. Next, please. So the main goal of the project is to elucidate the structure of the dark state of APA and characterize it using a microsecond molecular dynamics simulations and a polarizable QM-MM approach. So what did we find? The most interesting thing we found is during our MD simulations, starting from the trypin conformation, we were actually able to see the rotation of the glutamine within the first hundreds of nanoseconds, which actually suggests that this rotation is a fast, low barrier motion. And this result actually posed a challenge on the first proposed model of the dark to light mechanism that was actually based on this rotation. We also had computed the NMR chemical shifts of the protons of the flavine and the surrounding residues and compared them to the experimental for both trypin and metin simulations. And we found that there was an unusual shift of one of the protons due to the strong shielding effect of the tryptophan. And actually this result challenges the position and the orientation of the tryptophan in the trypin X-ray structure. If you'd like to know more, I invite you to check our chemical science paper that I cited in my slide, and thank you very much for your attention.
Thanks a lot for your talk. So, and now we can move on to the last, but certainly not least talk of this Flash Talk session. And this will be given by Isabelle Navizet from Université Gustave Eiffel in Paris, in France. And she will talk about QM-MM studies of firefly bioluminescent system.
Thank you for the, yes, can you hear me?
Yeah.
Thank you. So I hope I will convince you in 3 minutes that what we are doing at the Université Gustave Eiffel to be able to simulate some spectra of the emitter of the light emitter in the firefly bioluminescence is quite well done. Firefly are emitting light, and the reaction of the bioluminescence is the reaction of the oxyluciferin with ATP and the oxygen inside the luciferase, and is lead to an emitter which is in the first excited state, and when this go back to the ground state is able to emit light. And depending of the surroundings of the proteins, the color will not be the same in different kind of firefly. So we will first, so next slide, please. So we first focus to get the protocol to be able to take into account the environment in the light emission. And the first example I will give you is the case of simulating some absorption spectra. The way to do it is to first have parameters for the oxyluciferin and do a molecular dynamics, a classical molecular dynamics, take some snapshot and do some QM-MM calculation of the transition. And then we can understand and simulate the spectra, for example, of this analog when change, which is changing depending of the pH. So you have the experimental spectra, and when we do the calculation of the spectra for the phenolate or the phenol species, you can see that we can get very good information on the experimental spectra. This is not possible if we are not taking into account the environment which was there, the water. Next slide, please. So now with this same protocol, we are also able to do the emission spectra, but inside the proteins. So we have to have the parametrization of the oxyluciferin in the excited state. And now we will get the transition energy to get the spectra and inside the proteins. What we can get as information is that some mutation of the protein will lead more or less H bonding network on the right or the left of the molecule, and will be explaining why there is some blue shift or some red shift in different species of firefly. And I thank you for your attention.
Thanks a lot. And also thanks a lot to all speakers of this session, because as I can see, the official end was planned for 1832, and it is exactly 1832 hours. So thank you, and enjoy a short break until I think 1840, when we start with the flash presentations on electronic structures, chaired by Peter Salai.
Thank you, Stefan. Thank you to all Flash presenters of this session. Really impressive work. Even in 3 minutes, I'm so impressed about what you can present in 3 minutes. Very impressed about the quality. So we have a short break, as Stefan mentioned. We'll come back at 1840. Please enjoy a short coffee break. And in the meantime, perhaps I can draw your attention to another sponsor presentation. So here we have, as mentioned previously, our sponsors. JCIM is one of our sponsors, and I would like again for this audience today to present our journal. This is the Journal of Chemical Information and Modeling. The journal publishes in all regions that were discussed today, as well as yesterday. So biomolecular systems, electronic structure, materials, artificial intelligence in chemical research. And our article types are viewpoints, full-length research articles, perspectives. You can write a review, you can write a letter, or even you can write an application note on novel software packages, databases, and web servers. And I would like to draw your attention to our special issue on advancing women in chemistry. Actually, this idea came up with the recent figures that were announced by the European Commission on research that has been performed called SHE figures. And it was found that among doctoral candidates and graduates, we are very close into reaching gender parity. So 48% of all doctoral graduates are women. But when we go into higher ranks, we see that only 26% of women are full professors. And probably this drop in ranks happens because the promotions, these promotions of the tenure usually come at the time of optimal childbearing for women. And as we all know, unfortunately or fortunately, women have to face the dilemma of raising the child at the time where they should be getting the tenure, which is very difficult. And so we're launching this special issue in the spirit of inclusion. And we invite scientists from around the globe to submit manuscripts focused on a combination of experimental work and chemical information and modeling, or just theoretical work. for the special issue of Advancing Women in Chemistry. And we welcome all authors, irrespective of gender, of course, but for the manuscript to be considered for publication in the special issue, we would like authors to provide a statement that they are committed to supporting and advancing women in chemistry. And I hope that many of our speakers, flash presenters will, and also attendees, will consider submitting original research to this Women in Chemistry issue, but also viewpoints, perspectives, and reviews. So thank you very much for listening, and I will close this until 1840, and then we have our last flash presentation. Please stay with us, because at the end of this session, we will be announcing the winners of the biomolecular system session, as well as the electronic structure. And I see that we're almost 100 people still. So stay with us for this last session.
All right, I think it's my turn, but we still have a couple of minutes.
Yeah, well, let's wait. Let's give people a chance.
Sure, we wait.
Peter, we can start. You're muted if you want to unmute.
Oh, I'm not muted anymore. All right, so good evening. Thank you for those who stay with us. This is the last session of our meeting, and we will have six flash presentations. And I announced the first one, which is by Sergei Vyboshchikov from University Girona in Spain. Sergei?
Good evening. It's my pleasure to be here. This talk is about a method of calculating solvation energies, which we did together with Alexander Wojciuk. Next slide, please. Next slide, please. The method is based on the COSMO approach by Klamte Schurman, in which the solvation energy of a solute is calculated from the atomic charges. These are those capital Qs. So this is the Coulomb energy of the interaction of atomic charges with the induced charges on the surface of the cavity, plus the mutual repulsion of the induced charges. Those induced charges in the COSMO method are obtained from the simple system of linear equation, which is given on the bottom of this slide. But of course, the purely electrostatic energy is not enough. The electrostatic is calculated here from the gas phase atomic charges. Next slide, please. And this electrostatic energy in our approach is augmented by the correction term, which depends on the atomic surfaces of the cavity. This is the first term here, as well as the induced charges, which is the second term, as well as it includes also a short-range correction in order to describe essentially the specific interactions such as hydrogen bonds. Those parameters which are in blue here are adjustable. They should be adjusted on some reasonably large set of known solvation energies, and the results obtained, which are on the next slide, please. So these are the results for the aqueous solutions, essentially in the comparison with the standard SMD method available, for example, in Gaussian. So the blue bars are our results, and one sees that virtually for most categories of molecules, of neutral molecules, our method is superior to SMD, while for ions, the advantage of our method is even more pronounced. The method works also for non-aqueous solution. We tried it for many dozens of various solvents of different classes. And the last thing is that the program for calculating the thing using this method, which we called EuEasy, so Universal Easy Solvation Estimation, is available. It can be downloaded. Thank you for your attention.
Thank you, Sergei. And I announced the next speaker, who is Carlos Rocha from Leiden University.
Good evening.
Carlos?
Yes, good evening. Thank you very much. First of all, my name is Carlos Rocha. I'm currently a Marie Curie postdoctoral researcher at the Leiden Observatory. And today I'm talking about the most recent work that I've been involved in together with Harold, which is related to the theoretical spectroscopic characterization of C2N-. Next slide, please. So to obtain the near equilibrium potential energy surface, or approximately the quartic force field of its ground state linear species, we have here resorted to a high level composite energy scheme, which is based on the summation of several energy increments. The first here is associated or obtained using energies obtained from coupled cluster or CCS-DT level, extrapolated at the complete one particle base set limit. The second component includes the effects of scalar relativistic, while the last one accounts for larger order corrections beyond gold standard. And this includes then the effects of triplet and quadruplet excited determinants in the coupled cluster, in addition to an approximate correction toward the any particle base set limit, which is obtained using a continued fraction approximate. Using this potential or quartic force field has been then subject to nuclear motion calculations using both vibrational perturbation theory and a variational approach. Next slide, please. This table here shows the calculated spectroscopic attributes for both main and singly substituted isotopologies of the ground state linear C2N-. And as you can see, apart from the standard spectroscopic attributes, we have also paid particular attention and calculated the possible fine structure in the rotational spectra, as evinced here in the electron spin-spin and spin rotation complete constants, in addition to hyperfine structure. And this includes the effects of magnetic dipolar interactions between electron spin and nuclear spin, as evinced in the isotropic Fermi constant and anisotropic dipolar complete constant, in addition to a nitrogen quadrupole complete constant. Although not shown here, for simplicity, we have also taken into account the effects of the magnetic interactions between nuclear spin and molecule rotation. It is then expected that the calculated spectroscopic attributes may aid in future laboratory and hopefully observational surveys on C2N-. This paper has been recently accepted in PCCP, and I address you all to its latest volume for further details. Thank you very much.
Thank you, Carlos. And now we go to France, and I would like to announce my friend Stefano Evangelisti, who served actually for a long time in this division. Welcome, Stefano, and we are listening to your talk.
Thank you very much, Peter. So in these 3 minutes, I hope I will be able to give you an idea of our approach that have recently been developed in Toulouse to treat periodic systems. For periodic system, the usual strategy is to take a supercell, then impose Born-von Karman boundary conditions, and to use, you can use Hartree-Fock or DFT and so on. The problem is that in presence of long-range interactions, the supercell must be quite large. And this is a problem if you want to use the typical methods of quantum chemistry, like coupled cluster or CI or CASSCF. Next slide, please. So the key ingredients of our approach are 2. One is the topology of the supercell, and the other one is the distance in the supercell. As a topology, we take a torus in order to to take into account the periodicity of the system. A normal torus has a problem, is that it has a curvature, so you can't fit, for instance, a crystal in a three-dimensional torus. So this is why we used an object developed by Clifford. This is why we call Clifford boundary conditions, which is the Clifford torus. The Clifford torus is a flat surface, periodic, but with zero curvature. The problem is that it is difficult to imagine this object because it must be embedded in a complex space. A three-dimensional crystal must be embedded in a Clifford torus which lives in C3, in the complex space of dimension 3. Next slide, please. The second point is the distance. If we take the normal distance, which I gave you in the slide, an example, a one-dimensional example, you can take the arc distance, which is you have two possibilities for this distance between points 1 and 3, and the other possibility is to take the core distance, which is the Euclidean distance defined in Cn, in the complex space where the torus lives. And you see in the bottom of the figure, if you do this, the Coulomb interaction becomes a continuous function at a large distance, which is not the case for the arc distance. So we have been applying this strategy to several systems. Next slide, please. This is an example. We computed the energy of a two-dimensional Wigner crystal. A Wigner crystal is when at very low density you have a crystallization of the electrons in a gallium background. And so there are two structures in competition, the square lattice and the hexagonal lattice. And we have been able to compute these, the energy of these two lattices with a very high precision. You can see at the bottom of my slide, the underlying, the underlying figures are, digits are from reference results. And we have been able to add 3 more digits to the precision of these results. With very easy, the advantage, one of the advantage of this strategy is its simplicity. Next slide, please. This is the list of the people involved in this research, and a list of the system where we have been able to use this strategy. So thank you for your attention.
Thank you, Stefano. We go to Germany now. The next speaker will be Kathi Tinzel from Dresden. Kathi? Kathi, are you here?
Kathi, you have to unmute your microphone.
Okay, thanks. Can you hear me now?
Yes, now we can hear you.
Thanks. The bifunction formalism is an alternative approach how to handle density functionals. The issue in orbital free density functions theory is to approximate the non-interacting kinetic energy. In conventional functional design, TS is approximated by some local kinetic energy density. Local kinetic energy densities are not uniquely defined, an aspect that additionally complicates the search for approximations. Conventional functional approximations fail to provide structured electron densities during energy minimization. This behavior is due to an improper performance of their functional derivatives. The bifunctional approach resolves this problem. In the bifunctional approach, full control is given over the derivative and thus over the final electron densities. However, no access is given to the parent functional because the formalism employs formal functional derivatives. The functional value, however, can be extracted from the density potential pair. Next slide, please. In the 80s, it has been shown that the functional value for a functional f, which obeys homogeneous density scaling, can be obtained as a spatial integral involving the electron density and the functional derivative. In this context, the second line is still a density functional because the density dependence of the functional is known. This changes in the bifunctional approach, which is based on the same formula, but employs a formal functional derivative. The functional value, however, is the same for a pointwise correspondence between the formal and the true functional derivative. This procedure allows to handle functional approximations via their derivatives. In contrast to local kinetic energy densities, those potentials are uniquely defined and thus can be compared pointwise in space, an aspect that facilitates the search for approximations. Next slide, please. Finally, with the bifunctional formalism, one can systematically approach the problem of orbital-free density function theory because it allows to handle functional approximations via their potentials. This is the first important aspect. Second, fermionic and bosonic contributions are treated separately. This separation is equivalent to the introduction of a new set of quasi-particles. The corresponding eigenvalue equation incorporates the Pauli potential. Third, because the Pauli potential is known exactly in terms of Kohn-Charm eigenfunctions, approximate and reference potentials can easily be compared. Based on the idea of the covalent separation, numerically accurate orbital-free Pauli potentials for molecular and solid-state systems can be generated. With these concepts at hand, it is finally possible to provide systematic progress in the field of orbital-free density function theory. Thank you very much.
Thank you, Kathy, also for keeping the time. And now we go to Spain again. The next speaker is Cohen de Graaf from Tarragona.
Okay, I will try to give an overview of our implementation of non-orthogonal CI. And in 3 slides, I will try to explain what we study, how we study it, and where we study it. What we study is intermolecular energy and electron transfer. And to name a few examples, I printed here some charge transfer result where we can compare ground state with charge transfer states. We study magnetic interactions, and another important point that we study is singlet fission, in which a chromophore is excited to an excited state, and then by energy transfer to a neighboring chromophore, a second hole pair is generated from the one single photon. So that is a short overview of what we study. And on the next slide, I will try to explain how we study it. We study with non-orthogonal CI, and that's important because in these processes, a full orbital relaxation is important, since we describe very different electronic states. And as an example, here we have these 2 components of a charge transfer result, in which we first calculate local states on fragment A, the molecule on the left, and wave functions of different electronic states on fragment B on the right. And then we make antisymmetric products of these fragment states to generate the ground state of the dimer. local excited state in the second line, then a local excited state on the right. We can also combine two triplet local states to a singlet. And we can, of course, from the cation and the anion on A and B, make a charge transfer state. Now, all these A-B states are non-orthogonal because they are described with their own optimal orbitals. And all these fragment and these dimer states are interacting and non-orthogonal. So we have to solve the non-orthogonal general eigenvalue problem with the S matrix in it. And what we get out are electronic couplings. These are important to describe electronic transfer. And very importantly, we will get very compact wave functions that are easily interpretable. We include full dynamic, full static correlation, and we also can include dynamic correlation. And on the next slide, yes, this is where it is implemented, this non-orthogonal CI, because that is computationally very expensive. We have implemented that in the Chrono code, which is massively parallel. It's also GPU accelerated. We actually only run on GPUs. It's open source. It's interfaced to OpenMORCAS for the fragment calculations, and it's of course on a constant development. And just to show you a very, give you a short, small impression of the scalability, the plot in the middle is the scaling plot on Summit, which is the second largest supercomputer in the world, which has 4,096 nodes, each with 6 GPUs. And you can see that we have full linear scaling up to the machine limit, which is more than 24,000 processes at the same time. It's also very much GPU accelerated. On the right plot, you see in the top curve, that's CPU only. And then if you offload a part of the code to the GPU, you gain 5 times, 10 times, or 16 times. This plot is a little bit old. At the present, we are even at 20 speed up. And so that is where it is implemented. Oh, no, this is not me.
Our time is up.
Okay.
Already
no, I was done.
Okay.
Yeah.
You can finish your sentence.
Yeah, no, there's nothing more. Just to say that in May we are organizing a summer school on this. So anybody's interested can contact me for that.
Thank you, Cohen. And we are already at the last talk. Silvia Scaiola from Girona.
Thank you, Peter, for the introduction and the opportunity to give a talk today. In this work, we use aromaticity to characterize the first triplet and singlet excited states of paraquinodimethanes. And based on our findings, we propose guidelines to increase the Berg character, since molecules with Berg aromatic excited states have potential applications in optoelectronics. In order to predict and understand aromaticity, it is very common to use Hickel and Berg rules, which based on the number of pi electrons determine whether a compound is going to be aromatic or not. In the case of closed shell rings, molecules with 4n plus 2 pi electrons are Hickel aromatic, while if we have a half-filled shell with 4n pi electrons, the cyclic molecule will be Berg aromatic. One form of paraquinodimethane is TMTQ, which was introduced in 2015 as a triplet state aromatic system. As it is common for triplets, the authors characterize it as Berg aromatic. However, in order to explain Berg aromaticity here, a double charge transfer from the central ring to the external positions has to occur. This charge transfer involves a large electronic change in the structure, and this is rather difficult to achieve. Another possibility to explain the aromatic character is a D-radical with the pair electrons located at the cyanomethyl groups, leaving a closed shell central ring with 10 pi electrons. And this will mean that we will have a Hickel aromatic triplet state. This possibility was explored by some people in our group who did a detailed computational study of the aromaticity and found that the system was a Hickel-Berg hybrid dominated by the Hickel form by an 88%. However, recently Kim and Casado claimed that TMTQ is Berg aromatic in the S1 state. And in light of these new experimental results, we revisited the case of TMTQ and other kinoidal molecules, including the S1 state. Next slide, please. Next, okay. We consider neutral and ionic systems with different ring sizes and substituents, and by means of DFT and TDFT, we characterize it through the analysis of the spin densities, charges, and aromaticity. We observe that in general, an ionic system with small central rings present the highest Baire character. We also found that the triplet and the singlet excited states are electronically very similar, confirming that the TMTQ has a small Baire character even in the singlet state, in contradiction to what Kim and Casado claim. Next slide, please. Finally, based on our results, we have proposed for the first time the guidelines to increase the Baire character in the excited states of kinoidal compounds. We explored two ideas. One is to use small anionic rings with pi electrodonating groups and add in para position strong acceptor groups. In this way, the rings can become aromatic after accepting electrons. The second option relies on the opposite strategy, which will be to force the charge transfer from the external substituents to the central ring. To achieve that, we need an electron deficient core with electrodonating exocyclic substituents. I hope that you enjoy the presentation. I want to finish thanking again the organizers, the organization, my supervisors and collaborators in this work, and of course, all the audience for the attention.
Thank you, Sylvia. And with this session is also ended. Now we have only one task to do, namely to announce the winner of the awards. And to announce the Biomolecular award, I asked Stefan to announce it. Are you here, Stefan?
Yeah, thank you. It's an honor, and actually it's quite a funny thing because I mean this is a European conference, and we essentially do the same like the Eurovision Song Contest. So we have a popular vote and we have a jury vote, and both can be independent and both can agree. And I'm happy to announce the two different results from both the audience and from the scientific award, from the scientific committee. And our 12 points from the audience go to Marketa Palomkiova about the ionizable lipids in SARS-CoV-2 vaccines. A very interesting talk, and I'm happy to congratulate you for the audience award. And the scientific committee award, yeah, absolutely. And the scientific committee award, and I think this was a very, very close decision in the end, goes to Birgit Strodel about the massive simulations about the A-beta association and the extended system simulations, particularly for in vivo conditions. So congratulations to both of you.
Thank you, Stefan, and it is my honor to announce the Electronic Structure Awards. The popular vote goes to Boris Mariashin. You should remember it was the computational driven organic chemistry from Vienna. Congratulations. And the scientific committee found that the best presentation was by Anna Hahn from Zurich about the efficient calculation of absorption and emission spectra. Congratulations to you as well. And before I hand over the microphone to our chair of the conference, to Zoe, I would like to thank, first of all, for the European Chemical Society, Anna, who hosted our meeting on Zoom, the Hungarian Chemical Society, Esther, who was responsible for the homepage and the registration, and the whole organizing committee, but in particular Zoe, who took care everything. He even found errors in my slides, so she did really everything, took care of everything. So thank you very much, Zoe.
Thank you to everyone.
And we are really looking forward for your next organization in person.
Thank you, Peter. Congratulations to the awardees. At this point, I would like to make a small comment for the Electronic Structure Award. In fact, Anna Hen was the winner of both awards, both the popular vote and as well as the scientific committee. She won the popular votes by 53%. So she will get both awards. Congratulations, Anna. And Boris, indeed, it was the second, quite close to receive the second award, and he will also receive, of course, his award as the second place. So we thought it was worth mentioning that she won both awards. Also, let me close this conference by saying how much we all enjoyed this, how much we would love to see you again in 2023 at the European Conference on Computational and Theoretical Chemistry, which will take place in Chalkidiki, close to Thessaloniki, in northern Greece, this yellow spot that you see here. And so I would like to thank all attendees for staying out so late, and also for being there in both days, for participating in the discussion, for facilitating nice questions. I would like to thank our sponsors, IBM Research Europe. I would like to thank JCIM, the journal, and also I would like to thank Sanofi. I would like to thank our keynote speakers for delivering really nice, exciting presentations, state of the art and beyond. I would like to thank our organizing committee for a really hard work for facilitating this conference. Of course, our awardees, congratulations on your award. I would like to congratulate the flash presenters. Really, I found all the flash presentation to be really exciting, and I was amazed by how much you can present in 3 minutes. And I was really very glad that we had the opportunity to hear both young scientists and senior scientists come together in this. And last but not least, I would like to thank the European Chemical Society and Anna Robinson in particular for facilitating the Zoom platform and for recording all our webinar. This will be online in a special channel devoted to our division in the European Chemical Society YouTube channel. You will receive this information by email. I would like to thank the Hungarian Chemical Society for giving us the platform of the website to host all the registration and abstract submissions, and to the Biomedical Research Foundation of the Academy of Athens for additional support during this organization. So again, I would like to close the conference, and thank you everyone. You will be receiving email updates from us for the European Conference on Computational and Theoretical Chemistry, and we hope that we can welcome as many as possible in 2023 in Greece. So again, thank you very much to everybody for your participation. Thanks to our president for all his work, and I would like to close this. So thank you, thanks to everyone. And if any of the organizing committee wants to make any concluding remarks, please, please go ahead. Great. So bye everyone, and thank you.
Bye.
Bye.
Bye-bye.
Bye.
Bye.
Bye.